Yeah. Hello, everyone. Thank you so much for joining today's AIAA Center's section mini conference. We have a wonderful program today. Very exciting. Planetary defense. We have a professional teacher and students. More people are joining here in person and more online. Because we have half of the speaker online and then some speaker will join in the afternoon. Please enjoy it today. Number one for logistics is we have a check-in table on the left-hand side. You can see AIAA through table calls and pick up your speaker badge and then check in. And also we have donut, happy July 4th. There's a donut that was July 4th holiday in Athens. Yeah, it's a national holiday next week. And and the restroom is outside. You need to take a wave to the librarian, to unlock the door. If you need anything, please let us know. Another thing is we don't provide lunch because we are doing this nonprofit, so they don't allow us to collect payment or anything. But if you need, you can order recent nearby. There's a good restaurant. You have Subway, Starbucks, and Banana Bread, and Maruya, and there are many good restaurant nearby. You can order online for delivery, or you can during lunchtime to enjoy a quick break. So without further ado, I'm going to introduce our moderator and friendly today, Dr. Nahum Melamed from Aerospace Corporation. He's going to also be the speaker after the first talk, initially the first one that because schedule, and he's also going to conclude in the afternoon. He's our Jedi Knight, Grandmaster behind the scene. We got all the nice speaker, all the support, that's really wonderful. We're doing this for many years. And by the way, if you are a member of AIAA, congratulations. Please remember to renew. If you need to join, please sign up at AIAA.org or let me know. AIAA is a great family. We provide event, outreach, newsletter, everything goes for you. AIAA is LA is a wonderful family for you. So thank you very much. So let's welcome our AIAA distinguished speaker, Dr. Nahum Melamed.
Thank you. Good morning, online and here, American International. My name is Nahum Melamed, and I've been involved with the topic of planetary defense for about 20 years now, trying to save the world, as we say, and inspire the next generation. I'd love to see young people here who might be inspired to get engaged with that, so that's wonderful. Welcome. I think I'm going to talk for exactly 1 minute and then pass it over to one of the speakers from the East Coast of the US who has some engagement in the afternoon. And so we'll let him speak. And then after that, I'll give some brief introductions to the people who are going to speak. We have a quite program today. So I'm going to let most people speak. At the end of the day, there's going to be plenty of time for Q&A and additional topics of interest. It's going to be open-ended until the kickers are open. So with that, I will transfer the first talk to Andy Rivkin from Johns Hopkins on the East Coast of the US. And if Andy is ready, we can actually start. And I would say that every one of the speakers, instead of me reading a long introduction to what they do, please introduce yourself, describe your way of form. What is the area that you engage with relating to asteroids, planetary defense? And I think we'll cover that. So is Andy online?
Yes, I am.
Hey, Andy, good to hear your voice again. And we just met about a month ago at the conference. So Andy will tell a little bit about that. And I would say, Andy, take it away.
All right. Thank you, Nahum. Thank you for inviting me. My name is Andy Rivkin. I'm at the Johns Hopkins University Applied Physics Laboratory here in Maryland. And APL, if you're not familiar with us, is the facility or the institution that built the New Horizons spacecraft, which is out past Pluto now and visited Pluto. We built the Messenger spacecraft, which visited Mercury and orbited Mercury for quite some time. And among some other things, some solar and heliophysics missions, we also built the DART spacecraft, the Double Asteroid Redirection Test. So I was fortunate enough to be invited to give this give this talk in 2021 to the folks here. A lot's happened since 2021, so I'm here to talk about that. And in fact, NASA made a video, so I'm going to start with, since NASA went to the trouble of making a 2-minute video about what we did, we'll start with that. Maybe, if I can remember how to work my computer. Here we go.
We're embarking on a new era of humankind.
Didymos and Dimorphos make a great target. We needed an asteroid with a moon that you can see from ground-based telescopes around the world.
We're doing this mission to prove that we can deflect an asteroid.
5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss. 4, 3, 2, 1.
For the first time ever, humanity has changed the orbit of a planetary object.
NASA confirms that DART successfully changed the targeted asteroid's trajectory.
Using the ground-based telescopes around the world to watch the system and see how it's affected by this impact event.
This is a watershed moment for planetary defense and a watershed moment for humanity.
Okay, so a lot going on in those 2 minutes. So now let's spend some time trying to explain what we just saw. So and why we did it. So asteroids and material from outer space hit the Earth all the time. Anytime you go out and you see a shooting star, that's basically a little tiny impact from something maybe the size of a grain of sand. Again, those happen all the time, multiple times a day over the course of the Earth. Larger objects don't burn up in the atmosphere like shooting stars and meteors do. Some of them, once you get big enough, can reach the ground. So at the smallest end, things that are like the size of your couch, the size of the chair you're sitting in right now, will hit the Earth a few times a year. The atmosphere stops them. They make very impressive shooting stars, maybe little pebbles make it down to the ground. People collect them, bring them into the laboratory. We learn a lot about the solar system when we do. At the largest scale, they're all the way on the right. When you get to things that are 10 kilometers in size, so I'm going to be using the metric system today. 10 kilometers is about 6 miles. When you get to something that big that hits the Earth, it's bad news for basically all the life on the Earth. That's the size of the sort of object that we think led to the extinction of the dinosaurs, among other species, 65, 66 million years ago. The good news there is that there are very few of these. We know where all of them are, and they're not going to be hitting the Earth, certainly any time that we need to worry about. So it's kind of these middle categories. Let's see if I have this. Nope. These middle two categories that people, scientists in planetary defense have been focusing on. Something 50 meters across, something maybe 150 meters across, certainly big enough to make it to the ground. They're not gonna, make us extinct. They're not gonna collapse civilization, we'd hope. But they are big enough that if they happened over a metro area, they would really cause a lot of devastation. And potentially a lot of casualties if we don't see them coming. So we want to understand how many are out there. We want to find as many as we can. So there are people that are doing that piece. And then if we do find something that is incoming that's of that size, we want to be able to do something about it. That's what planetary defense is about, basically, is finding these objects and then determining if we have to do something about them, what we would do. There's a technique called kinetic impactor. That's what DART was. You maybe got the impression. Basically, the idea is if you have an asteroid that's heading your way, you send a spacecraft to whack into it and change its orbit so it doesn't hit the Earth. It's not exactly like billiards, but it's similar in the sense that you want to move something by hitting it with something else. This is a hard measurement to do in space if you just have one asteroid moving around the sun. One of my colleagues, Andy Chang, realized that the easiest way to do this, the most cost-effective way to do this, was to go to what we call a binary asteroid. That's an asteroid with a moon, and then you hit the moon, because it's easier to measure what you've changed in an asteroid moon orbiting a big asteroid compared to an asteroid going around the sun. So all of these numbers on the left are basically saying that the asteroids go around the sun at something like 20 miles a second. We're probably only going to change the speed by a few inches per second, and that's a hard change to measure. But something like in this animation on the right, an asteroid moon goes around more like feet per second. And so if you change it by an inch per second, that's much easier to measure. So the idea was you go and you send a mission to test out this technique at a binary asteroid. And that is what the double asteroid redirection test is. All of the words mean something. Double asteroid, we went to a binary asteroid. Redirection, we want to change the speed of the moon. And then a test, this was not to save the world, at least not immediately. This was to see that we could do this, that we had the know-how and the technology, and that we saw what happened. So this is kind of a one slide summary. DART was the spacecraft. It came in here on this depiction from the left. It was launched in November 2021 from California. It impacted Dimorphos, which was the moon, on September 26th, 2022. And then the observations were made by LICHA-CUBE, CubeSat here just off the left of DART, which was contributed by the Italian Space Agency, and then measurements made from the Earth and from space telescopes, because DART was no longer around to make any measurements because it just whacked into the asteroid. So this was an international effort. Not only did we have this contributed CubeSat from the Italian Space Agency, but we had a large group of people from around the world who I'll talk a little bit more about that joined the science team, or the investigation team as we called it. And so, we translated this into a whole lot of different languages to support our team members around the world. To put this in scale, so this shows just very, very roughly, obviously, this is just I won't even say an artist's depiction because it was me that did it, not an artist, comparing the size of Didymos and Dimorphos to something that you might find familiar. There's LAX. And so they are very small objects, and they're very close together. You could easily walk between them if they were sitting, in downtown in LA. I assume you'd rather walk than drive because of the traffic, but they're very close together, only maybe a kilometer apart, so much less than a mile. This is the DART spacecraft with various technologies that were tested. The three I'm going to call out in particular. There's LICHA-CUBE up here. This is the CubeSat that was contributed by the Italians. There's SmartNav, which is our autonomous navigation system. And then Draco is the name of the camera. That was the only instrument that the spacecraft carried. We have four things we needed to do in order for NASA to be satisfied with us. And of course, that's what we want. We needed to impact Dimorphos in the fall of 2022. We needed to change the orbit period of Dimorphos going around Didymos by at least 73 seconds. We needed to measure what we did, how much we changed that period to a precision of at least of 7 seconds or better. And then we need to measure this factor called beta over here, this kind of psychedelic looking image. Beta basically is a comparison of how much we changed the momentum of Dimorphos compared to the momentum that the spacecraft brought. So these were the four things that we absolutely needed to do. These were called level 1 requirements in NASA speak. And so everything that all the work we did was trying to make sure that we addressed these four things. We did other things, but we needed to get these four done. So again, we launched in November 2021 from Vandenberg Space Force Base. It was a night launch, beautiful launch, the first launch I'd ever seen, and was just an amazing sight. I don't know if anyone there has had the chance, but if you do get the chance to see a launch, they're definitely worth taking advantage of. This animation shows how DART got to its target, kind of looking down from a bit of an angle and showing the orbits of the Earth on the interior, Didymos on the exterior, and there's DART. DART stayed really actually pretty close to the Earth all told. It never got terribly far. And if you are basketball fans, you might wonder whether this was a block or a charge. DART kind of got into position, and then Dimorphos ran into it, in a sense. From Didymos' point of view, of course, and Dimorphos' point of view, this thing just showed up. But in this point of view, the spacecraft was in position when Didymos and Dimorphos came smacking into it. This shows what SmartNav did because we came in at 6 kilometers a second, which is 4 miles a second, and because we were far enough away that communication was not instantaneous, we could not have someone sitting there with their, I'm going to say, Xbox controller to show that I'm not up on the newest one. I don't know what the newest Nintendo Switch 2 or something. You can't have someone sitting there with a controller and steering in because you're moving way too fast. So what we have here on the left big box is what the Draco camera saw. And on the right box basically is the algorithm for SmartNav saying anything that's brighter than a certain value is going to be white. Anything that's not as bright as that value is going to be black. And then the algorithm goes and says, what are individual things that I think might be asteroids? So in this case, it's picked the biggest one. That's Didymos. The next smaller one off at about the 2 o'clock position is Dimorphos. That's going to be our target. And then the two boxes in between the two large boxes are close-ups on Dimorphos and Didymos. Now I'm going to start the video. And this is basically what the algorithm saw coming in. It would find other spots, but it decided, no, this one's Dimorphos, and it's going to steer until it gets there. So at this point, until about 2 minutes out, this algorithm is actively steering. A little over 2 minutes out, it stops steering and just coasts. And now the jitter is just from not from steering, but just coming in. Here you have the last few frames. And perhaps you saw this live. And then finally, this last partial frame. So watching this live was really an amazing experience at APL with the other folks who worked on the mission. My understanding, people watching on YouTube, on social media, that it was really quite a moment for everyone around the world, not just us on the mission, which is great because that's what we wanted. So here it is again, without the other bells and whistles of the SmartNav. And, you know, we love showing this. We can show this at the drop of a hat. So here again on the lower left is Didymos. That's the main body. It's an interesting object all by itself, but we don't get to dwell on it too much because we're heading for that this guy right here in the middle. You can see Dimorphos was very interesting to the astronomers. It does not look like a simple single rock. It looks like a collection of rubble, as we call it. And then, of course, that last picture. So here again, this last image, this was taken about 2 seconds before DART's impact, so about 12 kilometers or 7 miles away. The whole image is about 100 feet across. And you see, as we'll talk about in a little bit, DART landed very close to impacted very close to the middle of this frame. I don't have a great sense a great internal sense of what I'm looking at necessarily, other than a big pile of rocks. So if you're like me, maybe this will help. This is to scale. This is, again, the LAX parking lot at the same scale. So these squares are the same size. These biggest rocks are kind of the size of these autos and trucks on the right. So this maybe gives maybe a sense of what the surface is like. It's something you could, again, easily hike around or walk through. I don't know if you could quite drive. Maybe if you had a four-wheel vehicle, you can kind of come from this upper middle around. But in any case, that at least helps me get a sense of what the terrain is like. Geologists, again, on the team were very interested in Didymos and Dimorphos both. This is looking at the larger object just to show that there's a lot that can be done, even from those few images, to learn about the nature of these objects. On the right, there are graphs that show the number of craters that were found. On the left, there are these different colors that show these different areas on the surface, like on the Earth, how we might take a map and say, these are mountains, these are valleys, these are river valleys. There are no river valleys on Didymos, but we can say, here's a high region, here's a lower region, and then try to interpret them. Again, the geologists and the impact modelers looked at the impact site in detail and were able to determine that coming in, DART hit first one rock with its solar panel and then kind of grazed this second rock before the main body of the spacecraft hit between the two of them. Let's see if nope, I have to back up. So that's these two rocks, the two big rocks in the middle of this image, and then this hollow in between them is where the main body hit. Once DART hit, it was then the job of LiCiCube, which was this CubeSat I mentioned, contributed by the Italians, to do its job. So DART, we would say, was about the size of a vending machine, and then the solar panels went out to be about the length of a bus. The LiCiCube, the CubeSat, was more of the size of a cereal box, doing its thing. It was contributed by the Italian Space Agency. It had two cameras. They were evidently Star Wars fans, because one was named Leia and one was named Luke. And most of the data, certainly the best data we got was from the Luke camera. But here's what the Leia camera saw with time until impact there. And you can see now 2 points, kind of a brighter, bigger one on the upper left, and then this fuzzy looking one on the lower right. Here now, it's not so obvious, but it will light up at the time when DART hit. And then it gets a little bit fainter. But this is basically what the Leia camera saw. The Luke camera now has a lot more data. And again, we can see here's Dimorphos with this big splash of debris that was caused by the impact, and now it's made its closest approach, and now it's receding away. So I'll let this run 1 or 2 more times. So again, here on the upper left, this is Didymos. Here on the lower right, this is Dimorphos. You're kind of looking at this, again, the splash of debris. And then after getting as close as it gets, it is now looking backward. Maybe you can see this dark piece here. That's where the debris is so thick that the sun can't get through it, and it's throwing a shadow. So there was a lot of debris. This image was made by one of our engineers, one of our optical engineers, and it's maybe a little tough to see what's going on, but now Didymos is on the lower right, and here on the upper left is Dimorphos, and then each larger box is making the contrast a little bit more, so you can see more and more details, or fainter and fainter details. And you can see these streamers just coming out of Dimorphos, all of this debris just being thrown out into outer space. And in that debris, this paper is just coming out shortly. This is one of those images again. You can actually see, if you look closely, little dots. These are boulders that have been thrown off into space by the impact. Here's another little cluster of them with all of this dust. And we now think that, in fact, these two clusters of boulders thrown out into space are pieces of these two boulders that were hit by the solar panels. So we've got these details that we can pull out thanks to all of this great imagery from LICHICUBE and this great work by members of the team. After this impact, after LICHICUBE had gone through, people on Earth and telescopes in space turned their attention to what was going on. The impact happened when Didymos was highest in the sky, kind of in the middle of the Indian Ocean. So the telescopes that got a look at what was going on immediately were in East Africa, were in South Africa, were at these Indian Ocean islands. We also got some data from Israel and from all the way up in Kazakhstan, these images that came immediately. All of these other telescopes were observing in the days and weeks and months afterward, along with these space telescopes, and helped us put together the whole story that I'm talking about for the rest of the talk. But immediately what we saw was this really surprising brightening and then a detachment as this kind of what we were informally calling the big poof here, as material kind of, in this view, came off to the right. And this was observations by folks in South Africa at this one particular telescope, but observers saw it all over. And everyone that was looking, again, in East Africa and South Africa, in Central Asia, saw this. So this was not some weird thing going on at the telescope. And in terms of immediate gratification, this is some shots from the DART team Slack. And I've taken the names out, but you can see, you know, people are talking about the pictures from DART. Here's the time when the actual impact occurred, but people were taking screenshots and posting them. And it wasn't very long before someone said, you know, when's the ground-based telescopes happening? When do we get to see? And just a minute later, people are saying it's brighter in Kenya. And then here, this image was taken from South Africa. So within 2 or 3 minutes of DART hitting, we were getting these images from the ground here on Earth. So proving that whatever we'd done, we didn't quite know what yet we had done, but whatever we'd done was pretty big. Hubble Space Telescope images were taken and started to come in over the hours and then days afterward. And what we can see, I'm going to actually start this again. So what we see in these early images is perhaps, I don't know if you can see my cursor or not, but is a streak coming off straight up and a streak coming off at sort of the 7 or 8 o'clock position, if this were a clock. These are the edges of the cone of debris that was thrown out. And then over the hours that passed, that debris started to get thrown or moved by the solar wind to make this beautiful tail. And you can see the debris kind of making its way, being swept back away from that initial cone. DART came in from the left, and the debris being swept by the solar wind off to the right. So this was amazing data, and people are using it to determine how much gravel was in the debris compared to rock, compared to boulders, and compare something like this, which is not a comet, to the way tails form in real comets. Like I said, people saw this big poof kind of immediately all over the world. I'm not going to talk about the text here on the left. Mostly this is to show that in people taking spectra, people trying to determine the composition of Didymos were also seeing it. And so they got to see what the composition of the material coming away in the cloud is. This in the spectrum here on the bottom, moving away upward, is the same as this cloud moving off to the right. So this got the composition of this cloud. It looks like there's a lot of potassium, a lot of sodium, and it looks basically what we would have expected, which is good. The tail lasted for a long time. These are images from November 2022, so almost 2 months after. This is from the Lowell telescope, and the tail was stretching tens of thousands of kilometers away from Didymos at this point. And the fact that it lived so long means we think that there was more material coming into it. The tail persisted really until we could no longer see Didymos anymore because it got too close to the sun. So even here with the Hubble Space Telescope taking a whole bunch of data and stacking it up, you could still make out the tail even in July of 2023. Unfortunately, it looks like it's now gone. We're not necessarily surprised. We were surprised it lasted as long as it did. But last summer, the first time we got to see it since 2023, we don't see any evidence of a tail. But that's the way it goes. We knew it wasn't going to last forever. But what we can say is that here's a picture again of the tail, and this is all made of debris that was thrown out by the DART impact. So Dimorphos itself is only about as big as this building. This is the NASA Vehicle Assembly Building in Florida. And it's big, but it's still just a building. You can see cars. It's not unfathomably big. The tail stretched tens of thousands of kilometers. Even this, this is kind of depicted next to the Earth and Moon. This is even giving it short-changing it a bit. It probably went almost 2/3 of the way at the longest of that length. But in terms of the amount of material that is making up this tail, it's really not very much. It could fit in one of these tanks. Again, this is a big tank, but this is a bulldozer here. It's not unfathomably big. It's just, maybe 10 million kilograms, so maybe 20 million pounds of gravel and rock and dust, which could fit in one of these tanks. So all that is fine and good, but it's not any of those four things I mentioned near the start that NASA really wanted us to do. So it'll help, but it's not the gist of it. The way we made the measurements to give us those things NASA wanted, which is to determine how much we changed the period of Dimorphos, was by using something we called light curves. So from the Earth, this is a depiction of Didymos, the big body, and Dimorphos, the small body, showing what's going on in the system. From the Earth, we only ever see them as one dot. So in those images you saw before with the tail, etc., it's just one dot. But what we can do is measure the brightness of that dot. And as Dimorphos moves into Didymos's shadow, or as it casts its own shadow on Dimorphos, the brightness dips some amount for some amount of time. We can then measure the amount of time between these dips and know how long it's taking Dimorphos to go around Didymos. We made these measurements for years prior to DART showing up. So we got the timing very, very well before DART came in and messed it up. And then we made the measurements again. And so this is real data now. This is not the previous kind of idealized version. But we see these dips in the data, just like we're expecting, when Dimorphos moves in front of and behind Didymos. But they are happening at different times than they would have if DART hadn't impacted. So the top shows all the data we took in the first week or two after the impact. These arrows show where we would have expected the dips if DART had not arrived. And then these other arrows show the dips that fit this new orbit. That suggests that we changed the orbit by something like 32 or 33 minutes. We also have radar data, and for those of you who are not familiar with radar data, what this is measuring, this is not a regular kind of image. The distance from Earth is being measured down, so the farther from Earth you are, the further down you are. And then left and right is measuring the Doppler shift, so a spin toward you or a spin away from you. So this box is what Didymos looks like if you look at with radar like this. And Dimorphos is up here. It's not very big. It's all in one spot. It's not moving. It's all basically one speed toward or away from you. And we can do the same thing we did with the light curves. If we didn't hit Dimorphos with DART, we would have expected it to be here at kind of the 9 o'clock position. But where we did find it with the radar is up here on the left at about 12 o'clock and down here at about 6 o'clock on the right. So these again are consistent with the same kind of period that we found with the light curves. So what we think that means, I'm going to back up, I guess, is that there was a lot of ejecta. We weren't sure if there was going to be any ejecta, but there was a lot of ejecta, and at least at that point, we said that that means that the momentum that was put into Dimorphos was 3.5 times more than what just the DART spacecraft put in all by itself. So most of the work that was done in changing the period of DART was done by the ejecta, more so than the spacecraft itself. We have impact modelers on the team, and they, of course, were very excited to use their computer models and figure out what happened. So they made their model. Here's their computer model on the left of Dimorphos. On the right, here's a close-up, again, with these two rocks, Atabaki and Bauron, and where the DART spacecraft hit. Let's see, I think, do I need to? Yes. On the left two boxes, we have a model of comparing the Lichicube data to some impact modeling done by Katie Kumamoto. And then here on the right, we have a model done by Sabina Radican, again, of these impact, this impact showing how we are matching what we saw with the Lichicube and from the ground with these computer models to learn and calibrate our models with reality. We have a lot of publications. We had 5 that came out first. All of these are available to the public and publicly accessible by our team policy. So you can have these QR codes. I hopefully will put them up again if you like. The one on the left is kind of our pre-impact predictions of what would happen in the Planetary Science Journal. The one on the right is our post-impact results. And we did find some additional things happening after the impact. Dimorphos's orbit continued to change. We didn't just smack it and then it was done. We are not, there are discussions on the team as to why the period continued to change. It looks like it's settled about 30 seconds shorter than we had originally changed it by. We think that either there are tidal interactions between Didymos and Dimorphos that are changing the period, or maybe there was a re-impact of ejecta within the system. That first one basically can be explained that Didymos and Dimorphos, at least Dimorphos, we think was facing, had the same face facing Dimorphos at all times, just like the Earth's moon did. But when we hit it, we took it out of that kind of orientation. So here on the right, you see an animation done by Alex Meyer that shows how we might have started, or the DART impact might have started Dimorphos to tumble around Didymos, which then leads to tidal interactions between the two, which can change the orbit period of Dimorphos and possibly explain what was going on. There's also some amount of debris that stayed in the system for some time. So that tail, again, was long-lived enough that we think material was constantly streaming out of the system. And we think while about 85% of material escaped the system in the first few months, and most of the rest hit either Didymos or Dimorphos, we think some amount maybe remained in Didymos orbit for maybe up to even a few years. So we think that might also have caused an additional change in the orbit period of Dimorphos, I'm sorry. We saw a lot of boulders that escaped the system with the Hubble Space Telescope. This is Dave Jewett who did this work. about 15 boulders that escaped are larger than 4 meters in diameter, so maybe 10 to 15 feet across. The largest one is 7 meters, so more like 20 to 22 feet across. And they are out there. They are moving at the same rate as Didymos. They are not a threat to Earth. All of them would burn up in the atmosphere. We get hit by material that size all the time, like I was saying in one of the first slides. But this is an interesting scientific experiment to track these things and see how they disperse. We think the impact was large enough that we changed the shape of Dimorphos. Rather than making a well-defined crater like what you might see on the moon, we think that Dimorphos was very weak, and instead we just basically changed its shape, which also contributes to its tumbling from a few slides ago. So this is not well understood. It's an entire process that happens on asteroids. But all of these things are hanging together. So in terms of what we've learned, we think that basically we see evidence of Dimorphos tumbling, and in the light curves, when we fit the orbit, we think that also matches the tumbling. We think Dimorphos's shape is similar to what I was just showing, this deformation that we would have expected from the impact. It looks like we have seen it. The long-lived tail suggests that there was debris in the system for a very long time. So there's a lot for follow-up missions and a lot of observations to do. And I can say that we can check all 4 of these boxes. NASA was happy with us. The mission formally ended probably about a year and a half ago. But there is another mission that is on its way to answer some of these questions that we brought up. So this is a mission called Hera. It's the European Space Agency is en route. It was launched in early October, and it'll arrive in late 2026 and carries various instruments with goals to measure the mass of Dimorphos and study the after effects of the DART impact. So this is just a similar kind of single slide summary as we had for DART earlier, although the Europeans have a very different design aesthetic than we do. We are here in this point cruising to Didymos in 2020, late 2026, beginning of 2027. There will be these phases of characterizing Hera, characterizing Didymos and Dimorphos, releasing CubeSats, and at least one of those CubeSats is planned to land on Dimorphos and do investigations there. So it was launched in October, last October, days before Hurricane Milton came in. So we were not at all sure that this launch was going to happen. But luckily we got good weather at exactly the time we needed it. And then the next day, everyone kind of evacuated out of Florida. But we did get the launch to happen. And this shows on the left kind of their little animation. On the right is images that were taken of the Earth and Moon as Hera was on its way out. This again shows the same kind of animation that I showed before for DART. And here they have Earth and Mars. And not just and Didymos, not just Earth and Didymos. There was a flyby of Mars that Hera did just a couple months ago. So these images were taken by Hera. This shows Deimos, the outermost of Mars's 2 moons, with Mars in the back. These images of Deimos are being analyzed right now, and the Hera team will be coming out with results soon, I expect. I guess I already showed this, but this one doesn't have the years on it. So together, DART and Hera perform kind of as bookends of sorts. DART doing the collision and doing the initial pre-impact measurements or images of the system, and then the images at the time of the impact, and then Hera coming by a couple of years later to do the kind of damage assessment afterward, and with its CubeSats. So this is a image of the DART team at one of our team meetings. A lot of our work was done over the start and most intense parts of the COVID pandemic. So a lot of people joined in via Zoom. We only kind of got to start meeting in person near the very end of the mission. It was a great team, and the mission. People ask how we felt kind of smashing the spacecraft, but really the what DART was not the hardware. It really was the people and that put it together, the people that took the data and interpreted the data. So DART didn't get smashed. Just the spacecraft got smashed. So this is my last slide. Really, just to summarize, DART demonstrated that kinetic impactor technology is a viable technique to potentially defend the Earth if necessary. The large orbit period change, 33 minutes, compared to, I think we were expecting more like 10, and then the requirement was more like 1. But the large orbit period change showed that the ejecta contributed a significant amount of momentum beyond what DART carried, which means that in principle, you could use a smaller kinetic impactor than you might otherwise, or at a later time than previously thought. The international nature of planetary defense was matched by the contributions made by people and institutions around the world. And then I didn't really talk about this, but I'm sure lots of people will be talking about this over the course of the day. Future planetary defense priorities include more comprehensive search telescopes, additional characterization of objects, and perhaps testing of other impact prevention technologies, whether that's another kinetic impactor or a gravity tractor or something else. So I know this was a lot. I tried to cram a lot in. We did a lot. We're always happy to talk about what we did, but I've left some time. So hopefully, if you have any questions, I am happy to tackle them. So thank you for your time.
Andy, thank you very much. I learned a few new things myself today, even though we attended the conference just a month ago. And from this talk, I learned a few new things. I have a question for you as well, but let's open it up to the audience, either in person or online, to see if they have any questions for you. Do you have a few more minutes, Andy?
Yes, I've got about 5 or 10 minutes.
Okay. Anybody in the room has a question for Andy? A quick one. Okay, in the back, yes. Let me. My field, but get what Mark said.
How much of a risk these two asteroids pose to Earth?
So how much risk are these asteroids pose? That's the question.
How much risk do asteroids pose? The largest asteroids, this particular asteroid.
Yes, yes.
Didymos and Dimorphos do not pose a risk. That's part of why we picked them. We didn't want to, we felt pretty good about the way the experiment was going to go, but we did not want to have, if we misestimated, we did not want to have a disaster on our hands. So Didymos and Dimorphos they don't come closer than something like 7 million miles to Earth at the closest. And that we did not change that. So these are not risks.
Okay, thank you, Andy. Another question here from the room.
Is there a plan to try a similar asteroid diversion mission, but on a shorter timeline? Say, instead of having a decade to plan, let's say you've got 4 months.
That's a good question. So there's every 10 years, the planetary science community get together and talk about what our highest priorities are for the coming decade. This was last done just a couple of years ago, and planetary defense was included for the first time. And one of the highest priorities was what they were calling a rapid reconnaissance, a rapid flyby reconnaissance. So they did not specify what that meant, what rapid meant. I think the way that you would be able to turn something around as fast as a few months would be people think that you have to have something already built and already on the ground just waiting. In terms of starting something from scratch, it's more like a 2 or 3 year turnaround, and even that would be pretty fast. So that is part of the motivation for the search programs, because if they can give us 20 years of warning, then you have a whole lot of choices. If you only have a few months of warning, then you're really kind of limited to very few things that you can do in response, at least right now.
Thank you, Andy. So we have also a question online, I think from Andrea. And the question, I think if I got it right, is can we use materials extracted from an asteroid for beneficial use, either on the moon, on the Earth, in space?
Yeah, people have been looking at mining asteroids. There was actually about 10 years ago, there were probably 3 or 4 different companies that were trying to raise money to do it. Most at the time, most of those companies were looking at extracting water or things that could be used as propellant, with the idea of refueling communication satellites. That was the business case that most of them kind of went for back then. Nowadays, there's at least one company, Astroforge, I think, that is looking more at extracting metals, precious metals, I think. So people have looked at this. I think the technology is there to be tested. I think the business case is really the challenge for a lot of them, is how are they going to make their money back?
Thank you, Andy. There is another question online from Mr. Patel, but I think he can come on and speak his question. Is the case, Mr. Patel?
Yeah, so have you guys thought about like working with Lockheed Martin or Raytheon for reaching, much more threatening asteroids, perhaps?
Yeah, so aerospace, we work with aerospace companies, and we certainly work with the big ones, depending on the specific thing we need to do. So I guess that's what I would say, is that yeah, the aerospace companies and the places that build the instruments and folks are all talking to each other, and in a case like this, if there were a real emergency, NASA, the government, or whichever space agency would be working with their local aerospace companies for sure.
Thank you. And another question from Nikki, I believe.
Yeah.
Can you come on the line, Nikki, and speak your question?
Hi there.
No, exactly. Okay, let me read it. So question from Nikki: what surprised you most about the aftermath of the dark impact? Was there any unexpected data from the morphos or the ejecta?
Yeah, for the aftermath and the ejecta. So the thing I was calling the big poof there, nobody expected it. We didn't know what to make of it. And there was discussion about whether it was hydrazine, whether it was leftover propellant that we just hadn't burned because we didn't need it. That was coming off. And it was definitely a big discussion for a while. I think right now we believe, well, it's most consistent with we melted vaporized a small amount of material on Dimorphos, and then in the course of that, the sodium atoms and the potassium atoms were hot enough to glow. But that was a piece that nobody expected. I think the amount of boulders that got thrown off was also unexpected. We didn't think we'd be throwing off things that were that big. The tail lasting that long and being that prominent, that one, if you go back and look at the numbers, we should have expected that one. It was hard to kind of visualize. You can see the numbers and go, okay, sure, that's a number. And then you go and you see in the sky what that actually means. And then you say, wow, that's crazy. And you work out the numbers with seeing what's in the sky and the numbers match. So that one we should have done. But I think the kind of the big initial vapor plume and then the number of boulders, big boulders, were the surprises.
Amazing. Actually, I have a question myself from your presentation. I think you mentioned in one of the slides that your minimum expectation was 73 seconds of deflection and you got 33 minutes. That's a huge gap from the expected. Can you speak a little bit about how do you come up with the estimation of by how much you can move the object? I guess it relates to its composition and mass.
Yeah, 73 seconds was, it's a little bit of apples and oranges. 73 seconds was based on what was the minimum that we thought we could detect. So it wasn't necessarily what we thought we would do, because in theory, when you do these things, it should be what's the minimum that I need to detect. And if you do more than that, great. So 73 seconds was based on if we change it by 10% and we give ourselves a month to measure that, then it's 73 seconds. When we actually said, okay, here's the real target, here's the mass of the spacecraft, here's when we're doing it, here's how hard we're going to hit it. At that point, we said, okay, we're probably going to get more like 8 or 9 minutes. So, and then the predictions before the impact were that it would be somewhere between 7 or 8 minutes up to 45 minutes. So we did fall in that range. I think I could take one more if there's one more before I have to take off.
One last chance for anyone in the room. Okay, yeah, one last question.
Can you guys hear me?
Hi, Mr. Rivkin. My name is David. It's technically 2 questions, but I'll ask the first one. What would be a close flyby that would be considered safe for when you do crash with Alicia at the redirection? And the second one would be what asteroids you actually see out there that pose a threat?
I'm sorry, could you ask the first one again?
The first one, what is the closest distance for Alicia cube to consider to be safe? Safe, I mean, not right with the asteroid, right? But to be able to actually take the measurements. So how close could Alicia cube lie next to the Dimorphos to not get impacted by the debris or anything like that?
Yeah, I don't remember offhand, but it was something like 10 to 20 kilometers away, I think. Maybe it was a little more, but we knew that we were sending it in a direction that we thought was not that we thought was going to be pretty safe, and we also knew that the debris was not moving super duper fast, so we were, I guess, taking a chance there. But we passed, I think it was something like 10 or 20 kilometers, maybe it was a little more. The second one, we do not know of any asteroids that are, if I remember your second one, we do not know of any asteroids that have even a 1 in 1,000 chance of hitting the Earth right now. I think everything we know of that has any chance at all, the chances are really remote and are decades or centuries in the future. So it is likely that the next thing that hits us is something we haven't found yet. So that's another reason that we want to go out and make sure we keep looking.
Andy, thank you so much for giving much of your precious time for us today on the East Coast. It was really a pleasure meeting you at the conference again, and hopefully I'll see you again soon in one of those events. And I'd like to have everybody talk to Andy. It's an amazing world. It's literally first in the world. So Andy, thank you so much and have a great rest of the weekend.
Thank you. Thanks for having me, and happy Asteroid Day, everyone. And yeah, hope to see you soon.
Thank you. See you soon. So I think now it's me. How much time do I have?
20 minutes.
20 minutes. Okay. So we switched the introduction to let Andy speak first because we had to move on to other things. So very generous of him to give us an hour of his time. A little bit about myself and about what I'm doing. So maybe I should start with what inspired me as a child, right? When I was a child, my mom came to me and said, turn on the radio, somebody's living on the moon. And that completely blew my mind, right? I went outside, looked at the moon and said, somebody is actually working now on that object. And I said to myself, I'd love to work on those kind of projects. And I ended up doing space kind of projects. I was born in Jerusalem, Israel, and I know it's in the news recently. We won't talk about that. We'll talk about asteroids today. And today we are celebrating a special event, which is called Asteroid Day. Asteroid Day commemorates an event that occurred in the year 1908, where a big object exploded over the Siberian desert in Russia. And estimated about 2,000 square kilometers of Siberian desert, which is bigger than most of the biggest cities in the world. And that raised the concern, are we really protected? What can happen to those big cities? We don't want to lose Los Angeles or New York or DC or Paris. Any of these cities could completely disappear if we don't protect them from even relatively small asteroids. It was about 50 meters. And so about 10 years ago, there was an organization, an advocacy organization that was created in Europe. I think it was Luxembourg, anybody knows? But in Europe, they started this advocacy organization that is intended to increase public awareness to the question of the hazard from asteroids and comets. And every year on that day, or around this day, today we are about 2 or 3 days before June 30, which is next Monday. And so about a week before or after, there is worldwide series of events that commemorate this event and bring attention to the public like we are doing now to do that. The other aspect is that what Andy had shown just a moment ago was a test of a technology to try to stop an asteroid if we find one headed into our planet, right? So we have a technology to launch rockets to space and communication satellites to space and interplanetary space vehicles can be used as a similar technology to stop asteroids. And that test demonstrated that we have the basic technology and it was successful. There is a lot more to learn, but it was a test that was completely successful. That's an amazing achievement of humanity, to defend ourselves from events like the Tunguska land. Right? So we have a little bit better protection from those. So I got involved with the topic about 20 years ago, and like with many people, it started from home where my wife came to me and said, can you come to our son's school? He was something 4th grade at the time, and talk about what you do. And I said, yeah, that's something I can speak to. And I came and gave a talk. Was much less involved than what we are going to hear today, but it left an impact on the minds of both the kids and the parents that attended my talk. And so it reminded me that probably the biggest thing you can do is talk to young people and get them inspired. And some of you might have friends and relatives and maybe children and grandchildren, and talk to them and get them inspired. So
the picture.
Ken, before we go to this page,
Okay.
can you go to the internet page for the Planetary Defense Conference. The link I sent you earlier. It's not in this page, but it is just like the Planetary Defense Conference. It's one of the links. I think it's the first tab out there. Just click on the first tab, no?
Okay, I got it.
Okay.
One second.
Okay. So, what I'd like to do, because we are here just regular citizens that are not involved with the topic of asteroids and planetary defense for the most part, and we want to encourage them to do a little bit of their own research. So we will do it right here, which is Google topics of interest and see what we can come up with that is related to that. So before we do that, I want to talk about the conference that we just attended. If you click the agree part there and just accept the page. Yeah, on the right, there is an agree tab there. Right there.
I was broke.
Yeah. There we go.
You need that.
So I'm one of the chairs of the organizers of those conferences that are being held every other year somewhere around the world. And the last one was held in South Africa. Where Andy and I met again. We do it around once a year or once every other year. There's one more person here that was at the conference and later, very soon, but it was an amazing conference to attend. Anybody who wants to learn anything you want to know about asteroids and about planetary defense is invited to either contribute or attend the conference. If you slide down a little bit on this page, and I'm demonstrating now what any of you could do at home, right? Just go to this public webpage and see what was done. So the first thing to notice here is that the entire conference was recorded. You can almost attend the conference by simply going to this page, click on any of those links and feel as if you were at the conference. So feel free to go and listen to parts of the conference. The conference is 5 days long. Obviously, you might not be interested in each and every topic that was covered, but if you're interested in any particular topic, the recordings are out there for the public. So encourage yourselves and your friends and your kids and your relatives to go and listen a little bit about what was presented there, because it might affect your life one day. And we want the public to get engaged with the kind of hazards that are very, very far in between. But when they do happen, we could lose a big city. We don't want to be in that situation. Also, the whole program is either already available or will be available online, where each and every of the talks is recorded and the presentation material is going to be available to the public. So slide a little bit more down, Ken, please, to see what else is there. So let's see. Oh, the picture. Hey, the picture. Don't skip the picture. So that is the photo of probably the majority of the attendees, about 250 that came from all around the world, I think from at least 50 or 60 countries. The majority of them came from the US and from Europe. The European Space Agency, which is the equivalent of NASA, it's a consortium of about 20, 25 European countries. We came together to work on anything space. Part of it is planetary defense. They sent a very nice delegation from the US. There was a nice delegation. And from all around the world, about 50 countries were represented here. And I'm there on the right side in the middle. It was held. Oh, yeah. Thank you. Oh, I can do it. Okay. And where is the laser? This is the laser. Oh, nice, very nice. Okay, I actually can control the page. Thank you. All right, so that's me and Phil. Where are you here?
I don't remember.
Oh, so Phil was together with me there. He's going to talk after me, and he's somewhere in this picture, I'm sure. But It was an amazing event to be in the town of the city of Stellenbosch, which is near Cape Town in South Africa. Beautiful place and an amazing hospitality from the local people here. So I wanted to cover some of the topics that were talked to at the conference. We talked about missions, we talked about discovery of asteroids. The biggest effort that's going on right now is finding those asteroids. We cannot do anything about asteroids we don't know about. So this is the first topic that is done to try to help with defending our planet from asteroids, right? The second one is characterization. As you have seen with the presentation from Andy, that a lot of the surprises were that the object was made out of probably high-level rubber pipe, and with many boulders on the surface. We cannot tell that detail from optical telescopes from the Earth. We have to go really up close to understand what those objects are made of. And so let's imagine that an asteroid is detected on a collision course with the Earth. We want to know its orbit exactly, so we can determine where it might impact. Is it going to be in North America, Europe, Asia? Very important information to know. We cannot tell it from a piece of dot of light moving across the sky. We have to go and do measurements near the asteroid to know exactly its orbit. Also, we want to know how big it is. Is it something that's going to impact a city, a country, a continent? These are the kind of questions that are critical to know before we put together a mission to stop that asteroid. And, and after we have this information, we start to talk about simulations and building up campaigns, and also talk about the consequences. What happens if the asteroid actually ends up impacting an area because we were not prepared? And currently we are not prepared, right? Except for this one test that showed that we can change the velocity of a very far away asteroid. If an asteroid is discovered with less than a few years or a few months, there is nothing that we can do. We have to take the impact. And so there is a whole group that deals with the participation of FEMA. FEMA is the organization in the US that deals with disaster management. They had panels and presentations of it, and talked about the impact, consequences, and response. Also, how do we communicate to the public a trustworthy information about the situation? There's going to be all kind of rumors and conflicts that could be floated around, and people will be very confused about what's right and what's wrong. We need to build sources of information that are trustworthy, just like in order to go to get information about the weather, about traffic, what about an asteroid that might come around? You need to develop those kind of sources of information that people will trust, the public will trust. So that's the conference here. Let's see if there is anything else. Let's move the page. It doesn't move, but that's okay. Yeah, that's okay. That's fine. Let's move to the next page that I sent you, if you can. It doesn't work now. Yeah, so I think everything else is basically just where the conference was held, and there's not much information. I think we don't want to dwell too much on the detail, but I think the intent of this, the program is here. I'm not sure if you can click it, but it doesn't matter. So the program is here. Here is the committees of the people who were part of it. And another very interesting piece of information is an exercise that we hold every conference. So every conference, there is a group from NASA and from international people who design a holistic simulated exercise, how we would engage the community with the full process of addressing a threat. And so there is a simulated threat that runs through the first couple of days of the conference with decision makers and politicians. What would you do to stop that asteroid? It's all covered in here. But let's go to the other page. Do you have the other link that I sent you?
Yeah. Just give me one
You can bring
second.
up and if no, we can go to. Yeah, okay. So the conference is being held once every other year. We held the conference this time in Cape Town, near Cape Town, South Africa. 2 years ago, it was held in Vienna, Austria, at the UN headquarters. It was an amazing place to hold a conference because it was the place where a real scenario would be addressed by the international community that would have to discuss what to do with an approaching asteroid. 2 years from now, it is going to be held in Montreal, Canada. So anybody who would like to travel to the conference, maybe contribute to the conference, encourage your friends to contribute to the conference, is invited to attend. But the big one is going to happen in 2029. In 2029, there's going to be two major events that are going to occur all in the same year. The first one is that it has been declared recently as the International Year of Asteroid Awareness and Planetary Defense. So communities all around the world will be engaged with activities, just like the one we are doing now, related to the outreach about asteroids and comets and the hazard from those objects. It's going to be worldwide and year-long series of events that are going to be centered on this one topic. This is going to be associated with another special event that on April 13 of that year, there's going to be an asteroid. It's called Apophis. Anybody heard about asteroid Apophis here? You here? Yeah?
Oh, yeah.
And online? I heard that online.
Oh, yeah.
Thank you.
It's Mark.
Thank you. Apophis is going to be an asteroid fairly large, about 340 meters across, that's going to zip by a planet closer than the geosynchronous satellites. So it's going to be visible with the naked eye from Europe and Africa. So there's a few missions that are now designed to fly out and take some measurements from this asteroid on that day. It's going to zip by a planet for just a few hours, and you will be able to go outside and look outside, and you can see a dot of light moving across the sky. And here's an asteroid. That's once in a lifetime type of experience. And so the International Year of Asteroid Awareness and Planetary Defense was created to give attention to this special event and hopefully drive the international community to build additional systems that would stop future asteroids from the hazard from space. So what I wanted to do here is basically let you access to those public resources that anybody can go and simply Google those topics, and there's wealth of information to read about that asteroid and about this international year. It's going to be all over the news as we approach 2029. During this year, there's going to be a lot of news stories and bulletins and documentaries, maybe even movies that are going to be created to cover this event and that year.
Remember, don't look up.
Don't look up. Yeah.
Bad response.
Yeah. So that's a bad response. During that day, everybody is going to be encouraged to look up for it, right? It's a real asteroid. And now, Ken, if you can go to the paper that we presented at the conference, the PDF that was presented earlier. Yeah. Yeah. So you can go to the top of this page. Yeah. So some of the things that we do. So I'm an aerospace engineer, and Andy is an astronomer or scientist, and there is a large group of people who are engaged with the science and technology in engineering and the math, which is called STEM, right? Targeted towards asteroids. And so myself and a few of my colleagues are engaged with various studies that should contribute to the overall body of knowledge related to asteroids. Let's imagine that an asteroid has been discovered on a collision course with the Earth. And I mentioned earlier that the very first thing to do is to try to characterize it, to know as much as you can about the asteroid orbit and size and mass and composition, so you can design a mission to stop it or deflect it away from the Earth. And that's called a rapid recon concept. Rapid recon is rapid reconnaissance of the object. This is one of the emerging topics of interest in planetary defense immediately after discovery of those objects. We feel that it's going to be a question of when an asteroid is going to be discovered on a collision course. And so we would like to be prepared with very rapid missions that could go and as quickly as possible characterize that object for us, so we know what to expect and what are our possibilities. So Ken, if you can slide, can I slide?
Yeah, you can.
Yeah,
Yeah, you can.
nice. So one of the ways, or the common way to do that, is to launch a rocket towards that asteroid with a spacecraft, with a camera and sensors, and take some pictures and send it back to us. But those that are involved with the business of launching rockets to space know that this is a very lengthy process. If you don't have a rocket that's ready to be launched on demand right now on the pad, it takes years to build and test and make sure it actually works. And even if you had it on the pad ready to launch, the launching of a rocket and the time it takes to travel through millions of kilometers towards the asteroid might not give us enough time to characterize the object. And so a concept that we came up at the company at which I work, which is called the Aerospace Corporation, is to use a solar cell. A solar cell is a cell similarly to the cell that is used in the ocean with sailor boats, where the wind of the ocean pushes the boat in a certain direction, and by steering that sail, you can move the boat in different directions. The same concept applies to a spacecraft that deploys a large, what we call solar cell, which is powered by the solar radiation, by the radiation of the sun. The sun emits charged particles that impact that sail and pushes the spacecraft in different directions. Turns out that if the spacecraft is small enough and the sail is large enough, you can move that spacecraft much, much faster than any chemical rocket can do. And so what we said was, well, to characterize the asteroid, you don't need much. You need an iPhone or an Android and take a selfie with the asteroid, send it back to the Earth. That's all you need. So we need a small spacecraft to be deployed with a relatively large sail. Send it towards the sun. The closer you get to the sun, the more power the sun will push that spacecraft. Shape the orbit such that the sensor will fly towards that asteroid as soon as possible and give us measurements that we can use to design a mission to stop it or to deflect it or to break it. And that was a study that we've done and presented at the conference. So what you see on the screen here is an umbrella type of solar cell that is folded just like an umbrella, stuck into the launch vehicle. The launch vehicle shoots that spacecraft out into space. It deploys into this umbrella-looking device, and each of those vanes is steerable, meaning you can turn it around and maximize the push of the solar radiation such that you can shape the orbit to go towards that asteroid. That's the study that we've done with a simulation. I'm going to just show briefly what we've done here. So this is an example. Ken, can you blow up the page a little bit so we can see, make it a little bit larger? Is it possible to zoom in a little bit? This page. I'm not going to use too much of it, but I'm going to just show what we've done here. Disappeared. Please, you can see me. Let's see if we can.
Yeah, it is full screen. I cannot zoom in, so I go to the regular screen.
Okay, regular screen is good.
Second.
Okay, so that's fine. Okay, I think it's good enough. Yeah. So what I wanted to show here in that study is that we have we used several options to launch a device to the asteroid. We take a picture of the asteroid and a few basic measurements so that we can nail down its orbit and its size and maybe its mass. We compared chemical rockets, just regular rockets that we launched from the space, from the surface of the Earth, like SpaceX, and so on and so forth, launched from the Earth, and very small spacecraft that are sent to various distance from the sun, 72%, 50%, 39% from the sun. You're aware that the closer we get to the sun, the spacecraft will be vulnerable to the heat from the sun, so it has to survive. And so it would take different technologies to do that. But there's actually a very interesting mission. It is currently out in space. It's called Parker Solar Probe. It's a spacecraft that was sent very close to the sun, take measurements, and it survived a very close passage to the sun. So we can do that. We have the technology to send spacecraft towards the sun. And we did a comparison of what would be the very best solution to come close to the object. And so we started from about 3 years before impact. So this is a range of launch of the spacecraft before impact. And this is the time it will take to fly out from the initial point to the asteroid. That red arrow here that you see here is just a representative from any point along this dotted line towards the asteroid. And these are the different solutions. In this particular example, you can see that the winner is actually the black line here, which is a launch from the Earth. If we had a rocket sitting on the Earth right now, ready to launch to the asteroid, it will reach the asteroid the fastest before any solar system can do. But some other examples that we ran, I think when there is a message here, it might stop, but let's see if we can come to another example here. In that study, which is published, anybody can download it and get it, or I can send it to the person. Let's see if there is another one. So this is basically the same kind of example, just goes so slowly. There are examples where the solar cell is the winner. Let's see if we can come up with this. Okay, I think I'll just skip that, but you got the message. The message is that in some cases, the solar cell is the best solution. And in some other cases, the chemical rocket is the best solution. So what we would like to do, we want to expand it to a very large population of asteroids that exist in the solar system and create a kind of lookup table so that when a real asteroid is discovered with a collision course with the Earth, on a collision course with the Earth, we'll go to this table and we say, okay, if you have a couple of years before impact, that's your best method of characterizing it. And so we are working on that. Our next phase would be to build up a database that will tell the decision makers and the rocket builders what to do and what's the best solution to do that. So we are building a toolbox of different methods to characterize those asteroids so we know what best to do. I think I exhausted my 20 minutes, Ken, I believe, right? Yeah. And so if you have any questions, I'm sticking through the rest of the day today. At the end of the day, I'm also going to do a wrap-up session where it's going to be completely open for Q&A by anyone. And what we're going to do there, we're going to do something that is kind of a citizen science exercise where you will ask any questions that come up your mind, and we just go and Google those and see what you can do with a simple Google. Right? I'm going to point you to interesting web pages with very interesting information. And we do something that any of you can do at home at the end of the day. I think with that, shall we take a question or just give it? I think next one is Phil, right? Anybody has a basic question for me, either on the room or online, or we just keep it for the end of the day? How should we? Let's do that, right? So let's keep those questions for later, come up with questions that could come up with many of the other presentations that you'll hear today. And with that, I would like to introduce Phil. Phil will describe what he's done and how me and him got connected to the topic of Planetary, which is very interesting to me. So Phil is going to connect.
Closest, where can I put my?
Oh, you can put it on the table. You can.
Oh, the table? Well, I can't reach it. Someplace I can stand.
Maybe you can put here.
Maybe I'll talk a little bit about how we had met.
Okay.
So I mentioned earlier that I got involved with the topic 20 years ago.
Screen sharing?
We have a
Yeah,
collaboration
share
that's
screen.
going on with JPL, the Jet Propulsion
It does not look like it.
Center out here in Pasadena.
I asked you to come in.
I developed a
Earlier you did,
introductory
but I turned it off.
on planetary defense that I instructed in my company for a few years. And it was meant to do a wider introduction, similarly to what we are doing today, but was carried over a full day. And one day, Phil and a couple of other of his colleagues ended up in my class, seeing what we're doing.
I'm not having the feature.
What is
We are
the
making
what's the name?
about
My name?
planetary defense.
You use your name.
So this is
Philip Rose.
in our movie. I couldn't say no, obviously, right? So
Oh, yeah.
I ended
Yeah,
up
yeah.
in that movie. That's what Phil is going to talk in a moment. Him and a couple of other people created a
There we go.
fascinating documentary, an IMAX documentary that was played for a couple of years at the California Science Center about 4 or 5 years ago. And now I'm not sure if it's playing anywhere, but Phil can fill us in on that. Did you have any question? Yeah.
Was planetary defense primarily into asteroids?
Asteroid and comets. Yeah, these are the two objects we are defending. It's a good question because there is some confusion. There is a concept that's called planetary protection. Exactly. So there is a question of contamination by earthly germs that might be sent out to external bodies or bring objects from external bodies into the earth. It's called planetary protection. And primary protection is from germs and things like this that might contaminate the planet, or we might contaminate other.
You gonna switch this to my screen?
Yeah.
So this shows up.
Yeah, so that's a different topic, right? Similar one. But planetary defense is dedicated to asteroids and comets.
Do you share screen?
I've shared it. It's being shared right now.
Hey, Nahum, can I just ask a question while we're waiting?
Yes, yes.
Yeah, have you considered just developing this kind of a sailcraft and running a normal mission just to kind of work the bugs out?
Yes, if, I don't know who's speaking, but if you connect with me, I can connect you with a local company here in Southern California.
You go to
that
the
actually builds those systems.
Oh, this is already Zoom.
And
Yeah. This
would
is,
Oh,
like
just click
to engage with
the
organizations
access for
like NASA,
for the
security.
not
wants me to quit.
with
I'll
NOAA,
be able to
and
record.
an organization
I
that
don't need
is
it
set
for
to launch
Yeah, just
a
So what do I do later?
quit.
into deep space to do a certain mission.
Oh,
They actually
okay.
intend to build it.
Leave?
They exist here in
No, don't
Southern
leave.
California. And we are collaborating with. the
Yeah,
others
this is
of
the
that,
security
sort of
issue.
like startup organization.
Yeah, you probably have to restart.
And touch base
That's
later, and
what
I can
happened.
connect
I have to boot back
you
on it.
and I'll talk more
Yeah,
about
you
it.
enable the setting that.
Okay, it's hard to hear with Ken's got
Enable
his
it.
mic on.
I've never had a screen sharing issue like this.
Yeah.
But,
Says
but
screen
I got the gist of it.
We
Thank you.
want to use the
Yeah,
PDF.
connect with me later,
Wait,
and
let's
tell me
see.
who you are and what the question is. Yeah,
Okay.
My
Ken
screen.
can give you my
Ah,
contact.
here we go.
Yeah, now it's.
Yeah,
Talk more
Mark-
about it.
Yeah,
But I was
some
saying that
laptops
there is a
will also
local
to keep the
startup
permission.
company that is designing and intending to build hardware that would fly on a rocket to do that. That would be attached to a spacecraft.
Right,
So that's
good.
the concept. I think my understanding, they are at TRL 6 now.
Oh, that's good.
Been developed and tested, and intended to actually get funding for a mission sometime. Funding is a big challenge today, as we know, with the current environment. Funding is pretty hard to come by.
Yep.
All right, are we ready?
Yep. Thanks, Nahum. I'm Phil Groves. I spent over 30 years as an executive. I think I'm going to use the laptop. An executive in the film business. When I was a kid, I wanted to work for NASA, but I moved out to Los Angeles, took a hard left into the film business, and made a career out of that. But the impulse to study astronomy and science that never left me. And so when I decided to leave the executive business to pursue my more creative interests, I decided the topic of planetary defense was the perfect one to make an IMAX documentary for. So I wrote and produced the movie called Asteroid Hunters, which has been playing around the world in IMAX theaters since the fall of 2020, which is a terrible time to release a movie into the marketplace, by the way. So I'm giving a presentation on how media can help this mission of planetary defense, and by informing the public about the issues about asteroids, the risks they pose to our planet, and what we can actually do about it, which is what my film is about. So when I put together this presentation, my focus started off as one where how movies help educate the audience because of the assets of using all of the art forms that are out there. But it occurred to me also that there was something that my film did not cover. And it's a really important aspect of helping the cause of planetary defense and having our Earth and our countries prepared for not for an asteroid impact, which is, it's not a question of if we're going to get hit by an asteroid one day, but a question of when. So for me, that made it an important topic. So why are movies important? Well, they're a great way to teach the general public about the issues. It uses your sight and your hearing to teach you whatever there is to teach and your eyes and your ears are the portals through which 80 to 90% of everything you learn pass through. So movies are a powerful tool to put ideas across. It allows for an intuitive understanding of very complex issues that you can represent in simple illustrations. Movies show the movement of asteroids when they hit. You see all the ejecta rise from the ground. So you can really quickly absorb a lot of very complex concepts, but in a very intuitive way. So movies are really powerful in this respect. Now, what do you do with that education? Well, my recommendation is that you don't do this. That's not how you stop an asteroid threat. It looks like fun, but that's not the way to go. The way to go is to use your education as a tool to influence policy. And the politicians that make policy, you influence them through the ballot box. So this is ultimately where the rubber meets the road when it comes to how media can help the cause of planetary defense. But here's the blind spot that I ran across when I was putting together this presentation. The government decides how we spend our money, and money is what makes the world go round. Money is what finances our rockets, our space probes, and whatever the mission is behind them. So they decide how the money gets spent. Now, this is an obvious statement, but it's not one that's really understood well enough. And the reason I would say that is because you're dealing with such incredible amounts of money with our national budget. $7.3 trillion was the budget for 2025 that we're in the middle of right now, or actually towards the end. The fiscal year is different than the calendar year. But you're dealing with such huge amounts of money that, you go, well, why aren't we spending more money on planetary defense? So yeah, that's a legitimate question, but you don't know these amounts of money that are needed for planetary defense. You don't know how much money is, how it fits into the overall landscape of the budget. So when you're talking about $7.3 trillion, you may be saying a gazillion, because, we don't really, most of us in the room don't have much of a perspective of how much money that is and how that compares to the sort of money that you've got to spend for various initiatives. So NASA gets about $24.8 billion. That's 1/3 of a percentage point of the overall budget. And of that, planetary defense gets about 300 million and a ball of string. I added the ball of string as a bonus. So, is that enough? Well, it really isn't enough. And that's where the public's understanding of the issue can have a powerful influence on how Congress decides where the money goes so that we're doing the things necessary to protect our planet. So how do we grasp these ideas of these enormous dollar amounts, et cetera? Well, I decided to kind of have everyone look at it through the lens of your average median household income of about $84,000 a year. So, if you live in a household that's making $84,000 a year, that you're probably not going to get that Lamborghini this year. And buying that beach house in Malibu is probably not on your future, in your future as well. So you need to have context for the amount of money that things cost. So this is the way to do that. This is the way to frame what planetary defense costs. So forget about Social Security or Medicare and these sorts of entitlement programs, because they're a fixture, but you start to get into the more optional ways of spending money that are more open to debate, let's say. But one of the biggest items of our budget is our defense budget. Now, for that $84,000 a year household, that defense budget is basically a 2-week cruise in the Mediterranean, airfare and drink package included. Okay, well, so now you have a sense of what that defense budget is costing your household. That's the amount of money, relatively speaking, that we're dedicating to national defense. So there's another important issue out there called climate change. So climate change right now is getting about a week's worth of a hotel resort stay, maybe in Hawaii or someplace like that. So that's how much climate change is getting. 200 billion is the actual number, roughly that, and it's being spent in various ways in various programs. Okay, so it was, I think, if someone mentioned something earlier about finding the asteroids before they find us, which is a critical first step in planetary defense. So we have this mission called NEO Surveyor. This is a space telescope that's been in discussions since I could spell asteroid. And it's been, they finally have this NEO Surveyor as a plan, is partly financed. They keep pushing back the launch date. This is a really important mission. So defense was a 2-week cruise in the Mediterranean. Climate change is a week at a nice resort. All right, so here's NEO Surveyor. It's the thing that finds asteroids before they find us. A medium-sized pizza with one topping. That's planetary, that's a key, one of the most key aspects of planetary defense for that $84,000 a year household. Hey, honey, should we protect the planet from a potential asteroid that we don't know about? Oh, I don't know, sweetheart. Let's get that medium pizza with one topping. That's what our government is doing right now. That's what it's deciding. That's what the politicians are effectively deciding. They're choosing to spend that little bit of money, relatively speaking. It's a lot. It's 1.2 billion for that NEO Surveyor, but compared to everything else, that $7.3 trillion, that's what we're talking about. Now, there was a great presentation by Andy about the DART mission. That DART mission illustrated that we actually have the power to deflect an asteroid, which is what you do once you find an asteroid that poses an issue to planet Earth. You want to be able to push it out of the way. So that DART mission showed that we can actually do it. What does that DART mission cost? Well, the DART mission, a Starbucks tall drip, which is like the cheapest coffee drink you can get at Starbucks. I probably, on a weekly basis, am spending enough money for about, I don't know, 15 DART missions just by myself as an individual. So that $84,000 household, when they buy that drip tall, which is the smallest cup at Starbucks language, they're in their household, they're buying the equivalent of a DART mission. So in conclusion, this is a mercifully short presentation. In conclusion, media like my film, which does a lot to talk about the science of planetary defense, but one of the things that needs a lot of attention to give context to the issue and how we actualize these ideas that are in the abstract and turn them into action. We need to understand the politics and how the politics controls the money, which builds the assets that protect our planet. And all of that is to get the general population interested in the topic of planetary defense so that everybody can have a hand in protecting our planet. Thank you. So Ken, I don't know if we have any time for questions or we save them for later. I'm fine for either one.
I would say let's go with the questions now. A couple of questions, if anybody has any quick question.
You have a trailer for your film?
Yeah, I'll bring the mic so for people online.
Do you have a trailer for your film to show us?
Oh, yeah, you can go to YouTube and YouTube Asteroid Hunters, and it'll bring up a trailer online. I didn't have something queued up for the presentation, sorry.
But we'll bring it up at the end of the day.
What's that?
At the end of the day, we'll bring it up.
Yeah, we can show it at the end of the day for sure.
What would be the best course of action to increase awareness on planetary defense?
What's that?
What would be the best course of action? What do you think would be the best course of action in order to increase awareness for planetary defense?
Well, the best course of action to increase awareness would be to show people films, I think, so that they can understand the issue at hand. And of course, you have to choose the right film. You know, movies like Armageddon and Deep Impact did a great job of sort of alerting us that there's this thing called, you know, asteroids, and they can wreak havoc on our planet. Although, when a Hollywood film does it, the audience immediately thinks, okay, this is not really a concern. They're just kind of making this up. This is like a monster that they're making up in cosmic space. And whenever I introduce my film, which shows this is how you would actually do it, I usually start off with the promise that no oil rig workers were harmed in the making of this film. That's because we don't send oil rig workers to go stopping an asteroid, nor would we ever have to. But informing the audience, and the next course of action, as I mentioned, as I sort of discovered on my own, putting this together, that people need to have a sense of context on how money is being spent in our government. If you don't have an understanding of that, then you're just simply barking at the moon, and you don't have the sort of pointed tools that would help really push a decision through the sort of amorphous process that we call politics.
Well, there's a comment from online, if you can speak out.
Hang on, I put my reading glasses on.
You cannot speak out. Yeah.
This is the, where is the spectrum?
There's no question, it's a comment.
Oh, it's a comment. All of this?
Yeah, basically, it's a comment to the White House.
I think that extinction is more expensive than all of the planetary defense program. Yeah, you know, our life on planet is definitely worth the effort, that's for sure. But it somehow gets lost because protect life is the objective. World War II Japanese Navy attacks Pearl Harbor, US Navy base, killing and destroying everything. An asteroid over the White House is more expensive than asteroid extrusion. Politicians are humans too. Yeah, they are, believe it or not. An asteroid that hits White House is dangerous, more dangerous than Pearl Harbor. Yeah, I would agree with that. And you know, asteroids, they're not trying to cause harm. They're just these rocks that go around the sun just like we do. But every once in a while, our paths converge, and that's where the trouble lies. So I think that's, any other questions?
Gross, Xavier, what is the biggest bottleneck you see in terms of funding?
The biggest bottleneck in terms of funding is really the lack of will. It's you know, it's people themselves having to choose one priority over the other. And you know, the bottleneck is influenced by what the public feels about something. So if the public feels strongly enough about an issue, the bottleneck that's in Congress that maybe stops that money, that's like taking money away from NASA as we speak, is the sort of bottleneck that can be opened up by enough people voting for the right, you know, congressman to advocate for planetary defense and what's necessary. And it's a worthwhile expense. You know, I put it in context a moment ago. And I don't know. I think that Neo Surveyors is worth the medium-sized pizza. I think another dark mission, sure. Tall Starbucks, no problem. That's
You
right.
mentioned the 300 million a year that we're now funding on that. Where is that? Is that going to the Space Force or to NASA or to something else?
It's a little bit of both. You know, so NASA has some of their own internal programs. They have their own Planetary Defense Coordination Office, where they're doing a lot of research and a lot of tabletop exercises to come up with protocols on what we would do if an asteroid was headed our way. And if it was too late to stop it, how would we, you know, clear out? And FEMA is often a part of those discussions. The Space Force, some of that money is going towards things in the way that they can contribute as well. So it's sort of a rough figure on what goes towards the effort. Was there another? Okay. All right, I think we're good. Thank you.
Thank you, Pete. Pete, did you make this cartoon?
I actually had artificial intelligence create that.
Very, very nice, very nice. Thank you, Phil. It's really amazing to be a friend of him because it put me in IMDb, right? So, so I say if you stick long enough in the Los Angeles area, some stardust will settle on you. But I wanted to touch one of the questions here, a little bit about what are we doing? What's the kind of bottleneck in terms of what they're doing? And the key problem is that those events are very, very far in between. So even if we had developed a system and put it on the pad, ready to go, in all likelihood, it would just be sitting there for 5 or 10 years, become obsolete, thrown away maybe a few $100 million. And we have to put a new system on the pad that will probably get thrown away. So even though an asteroid can be discovered and collide with us in 5 minutes, the likelihood of this is very, very small. So how do you create preparedness against those objects in that type of uncertainty? And one of the studies that we've done a few years ago was build a system that can be launched on demand and move it on to another mission before it becomes obsolete and replenish with a new rocket and new system every maybe 5 years or 10 years. And this way, you don't throw anything to waste. So the rocket will be sitting on the pad, let's say, for 5 years. No asteroid was discovered. We take out the payload that it was intended to deflect the asteroid and replace it with a communication satellite. So we did not get a total loss out of that investment. And every 5 years, we put a new rocket there that will be ready to go in case an asteroid is discovered with a very short one. So this is one of the techniques that possibly might work as an optimal way of dealing with a situation in which asteroids don't come by every single day, right? Not like hurricanes and earthquakes where we know what to do with them, right? And so there is a whole mechanism that was designed to deal with hurricanes, and we know where to escape and what to evacuate. All of the stuff about asteroids is relatively new. The last maybe 2 or 3 decades is when the topic got into attention of the public. And the intent of this talk is to increase the outreach of the public, to educate them about the hazard, so they can talk about it in the community and do the Google searches that will lead you to more information about it. I think with that, Ken, do we have a break now? We're going to a break. We want to say a couple of words about the rest of the program, or are we good?
Yeah, we're good.
Okay, we are good. So how much time do we have for the break?
We're supposed to gather at 1.
Now it's 12:30, so we're a bit behind time. Can we give another 10 minutes or something, or is it not so good? So anybody is now free, to do what you want. You can stick around here. We'll resume around. Looks like, yeah. There's a couple of meters up and down the street here. I think that's about it. Thank you very much. If you have any questions, you can reach out to me, and we'll resume in about half an hour. Cody, can we start now?
Yes.
Okay, great. So we had the fabulous talks in the morning, and now we are switching to the afternoon session, which will talk about disruption of asteroids, right? How do we break them, or not break them? And we have 2 experts from NASA, Brent, Barbee, and Adrienne, Rudolph. I think Adrienne is actually from university, right? And Brent is a professor at University of Maryland. So again, it was great seeing you at the conference, and it's great seeing you again now online. And so the floor is yours, Brent and Adrienne. Please take it away.
Okay, great. Thanks, Nahum. I'm Brent Barbee. I'm the lead planetary defense applications scientist and community liaison at the NASA Goddard Space Flight Center. And I'm also an adjunct professor in the Aerospace Engineering Department at the University of Maryland. And I'm here with my PhD student, Adrienne. Adrienne, go ahead and introduce yourself.
Hi, I'm Adrienne Rudolph. I am a PhD student at the University of Maryland, and I also recently just became a student researcher here at Goddard.
Yes. So today we're going to be talking to you about two topics. We're going to talk about asteroid disruption for planetary defense, and we're also going to talk about a mission concept that we're working on at the University of Maryland to visit Apophis called TERP Raptor. So as has been discussed earlier during the session today, we live in a cosmic shooting gallery. This plot here shows the orbits of several thousand potentially hazardous asteroids all overlaid on top of one another here in our inner solar system. And it also highlights the orbit of the asteroid Didymos, which Andy spoke about earlier when he told everybody about the DART mission. So the discovery rate for near-Earth asteroids has been increasing ever since the late 1990s. The discovery rate's been steadily going up. The discovery rate for the very large asteroids, 1 kilometer and larger, has essentially leveled off. We think the majority of those have been found. But the discovery rate for the 140 meter and larger objects is still staying pretty steady. And the discovery rate for all objects, including those smaller than 140 meters, is actually gradually increasing. We also work with other government sources to integrate the sensor data available for atmospheric fireballs, explosions in the atmosphere caused by small asteroids that explode at high altitude and have energy releases on the order of several kilotons. And so this data goes back to 1988, and it shows that our planet is struck very frequently by small objects that are fortunately small enough for our atmosphere to shield us from their harmful effects. The large red object, or the red event that you can see on the upper area, just a little bit right of center, is Chelyabinsk, which was the roughly half megaton explosion that occurred over Russia in February of 2013. So far, as Andy also pointed out, only approximately 45% of the asteroids 140 meters and larger in the near-Earth object population have been found. But the Rubin Observatory is coming online now, and the INEO Surveyor Telescope will be launching by early 2028. And those things, as you can see in the plot on the right, which is an estimate that's shown in our National Planetary Defense Preparedness Strategy and Action Plan, you can see that the discovery rate goes up quite a lot right around now because of the Rubin Observatory. And then the discovery rate increases again as we approach 2028 and start to bring in the INEO Surveyor observations as well. So as this is happening, this is giving us a much better picture of our inner solar system. It's showing us where these near-Earth objects are and helping us identify the ones that might pose a threat to us. And so in the meantime, we have to continue the work that has been underway for quite a few years now to become better and better prepared to send reconnaissance missions, and if necessary, missions to deflect or disrupt any hazardous asteroids that might be discovered on Earth impacting trajectories. This plot here was generated by Paul Chodas and Mary Berkey and Katie Kumamoto in their presentation that was given at the recent Planetary Defense Conference last month in Stellenbosch, South Africa. And so this plot here shows on the horizontal axis warning time, number of years before Earth impact. And then on the vertical axis, you have the asteroid size going up to a value of 500 meters. And this plot shows the estimated regions of efficacy for several different techniques for preventing the Earth impact. So you have nuclear deflection, you have kinetic impact or deflection, you have ion beam deflection, and then you have two forms of so-called robust disruption. You have the nuclear robust disruption, which can theoretically handle asteroids up to approximately 150 meters in size. And then you have kinetic impact or robust disruption, which can handle up to approximately 80 meter size asteroids. Now, of course, these are estimates and it depends on things like asteroid strength and composition, but they're good working numbers to give us a sense of scale as to where these two different types of robust disruption techniques might be applicable. Clearly, from this graph, we can see that robust disruption is a critical capability to have when the warning time is short. Because when the warning time is short, the amount of push you would need to give an asteroid to make it miss the Earth becomes large enough that the asteroid is likely to start to come apart, even if you intend for it to be deflected as an intact object. And therefore, it's appropriate to shift gears and instead design deliberately for robust disruption. And it's also worth pointing out that the Earth object population, like everything else in nature, follows a power law, which means that the number of objects that are on the smaller size range exponentially outnumber the larger objects. It should also be pointed out that objects as small as 50 meters do have the ability to penetrate deeply enough into the atmosphere to cause a lot of damage on the ground. And there are quite a few objects in the 50 to 100 meter size range that have not been found yet, even more than the number of objects in the 150 meter and above size range. And then on top of that, these smaller asteroids are more difficult to detect, which means that we're less likely to have significant warning time for them. And so for all those reasons, we want to be ready to robustly disrupt them if we need to. Now, robust disruption basically means blowing the asteroid up, but perhaps we can provide a bit of a more technical definition. So here are 4 elements, and I should point out that this is all research that's happening now. The book is not closed on this topic. It's something that we're actively researching. So I'm going to tell you what I think about what this definition should look like, but it's something that's evolving within the technical community. So the 4 elements that I would put forward are first, that the object is forcefully broken by either kinetic impact or nuclear explosive device into many fragments that are all small and widely scattered. Second, the largest remaining fragment should be no larger than 10 meters because we have high confidence that our atmosphere can protect us from something around that size. I mean, if you have a 10-meter piece of solid iron asteroid, that is probably going to make it to the ground, at least mostly intact, but it wouldn't be a severe event. Also, third, the majority of the fragments should miss the Earth. And finally, in the event that you can't make all of the fragments miss the Earth, especially because there's going to be a lot more small fragments and large ones, if there is some sort of transient micrometeoroid flux through the Earth-Moon system that's caused by the post-disruption debris, then we want to be able to characterize it and demonstrate that it will not pose intolerable threats to assets, either in Earth orbit, lunar orbit, on the lunar surface, or anywhere else in cislunar space. Here are some images from an AGU poster that Katie Kumamoto, myself, Jason Pearl, and Megan Sayal did in 2024. On the left-hand panel, you have a simulation output image showing an asteroid that's undergoing disruption. And you can see that the asteroid, even though the simulation time shown here is very short, it's expanded beyond its initial size, notably all around the perimeter. And this is important because at present, it's very difficult to run high-fidelity computer simulations of fragmentation and disruption out to long run times. And so for now, as a placeholder, we have to develop techniques to extract some information from the visual output of these simulations at early simulation times, so we can make some judgment calls about whether the object is indeed undergoing disruption or whether it's essentially hanging together. And so Katie ran a very large array of kinetic impactor models shown in the center panel, varying the sizes of the objects, their masses, their strengths, structures, and shapes. And I provided several different kinetic impactor sizes and velocities. And then we applied a number of different heuristics to each of these cases I'm not showing all four of the heuristics, but in the left-hand panel, I'm just showing one of the heuristics, which is the ratio of the delta V that was imparted to the asteroid's escape velocity. So delta V divided by V escape. And what we recognized when we plotted the data points for this heuristic across all the cases that we ran is that there were no cases that we categorized as either not disrupted or borderline if the delta V over V escape was greater than 1,000%. And furthermore, there were no borderline or disrupting cases for all of those for which the delta V over V escape was less than 10%. So for those reasons, we decided to adopt those two heuristics to help us understand and predict the onset of fragmentation and the threshold required for robust disruption. And these were heuristics that had been proffered some years ago, but this was the first time that we had ever taken a really hard look at them, supported by a wide array of simulation outputs. So to summarize, if we want to deflect the object without unwanted fragmentation, we designed the deflection mission to keep the delta V over V escape less than 0.1. If we want to deliberately robustly disrupt the object, then we design the mission to impart a delta V to the asteroid that's at least 10 times the escape velocity. And so this raises some questions. So one of the first ones we can think about is, well, what's the largest asteroid that we could robustly disrupt for a given kinetic impactor? So a kinetic impactor is essentially characterized by its mass and its relative velocity to the asteroid at the time of striking the asteroid. So if we take our robust disruption heuristic, delta V over V escape greater than or equal to 10, we have the equation for the asteroid's surface escape velocity, square root of 2 gm over asteroid radius. We have the spherical equation for asteroid mass, assuming it's a spherical shape. And then we've got the delta V imparted to the asteroid by the kinetic impactor. Delta V equals beta times the mass of the kinetic impactor times the impact velocity divided by the mass of the asteroid. And if we combine all of those terms and rearrange, we can solve for the largest asteroid size that could be, in principle, robustly disrupted by a particular kinetic impactor. So we have to specify the mass of the kinetic impactor, the speed at which it's hitting the asteroid, and the beta factor that Andy talked about before, which is the so-called momentum enhancement factor. So if we can specify those things and we plug in a delta V over V escape value of 10 for F, then we can calculate the largest size asteroid that we can robustly disrupt with kinetic energy. And Adrienne is going to show some results for this later on in our presentation. Isaiah Santistevan from Lawrence Livermore is also presenting with us today. And I know he's going to talk in a lot more detail about nuclear robust disruption. So I'm just going to say a few words about it here and just point out that one of the ways that we can reckon it using fast running, relatively simple analytical algorithms is to use a model for the delta V imparted to the asteroid. That's an analytical model that runs very quickly. This was developed by Rob Manigan and Mary Berkey at Lawrence Livermore. This was a poster presentation they gave at the most recent Planetary Defense Conference. You have the link to their poster over there in the lower right, as well as the link to their GitHub repository for their code. And here you can see a sample output that shows the delta V imparted to the asteroid as a function of the standoff distance, which is also referred to as the height of burst. So the height of burst is on the horizontal axis in meters, and the delta V imparted to the asteroid in centimeters per second is on the vertical axis. So in the lower left-hand corner, you have a numerical example to give a sense of scale. So suppose we look at a 67-meter spherical asteroid, which is the upper end of the JWST size estimate for the asteroid 2024 YR4, which we will also talk about a little bit later in the presentation, and assume a bulk density of 3 grams per cubic centimeter. That results in an escape velocity of 4.3 centimeters per second. And so we can see from the delta V graph on the right, which is for a 200 kiloton NED, that we would want to have a height of burst of about 46 meters or less above the asteroid's surface in order to do a robust disruption according to these heuristics. However, I have to point out this is only an approximation. This analytical model is really only intended to estimate the delta V imparted to the asteroid. It's really not intended for disruption modeling per se, but it does give us a fast-running starting point. Okay, so a little bit more about 2024 YR4. This is a near-Earth object that currently has a approximately 4.3% chance of hitting the moon on December 22nd, 2032. As I mentioned before, the James Webb Space Telescope made measurements earlier this year in March that allowed the estimation of the asteroid's size at 60 plus or minus 7 meters. These measurements also confirmed taxonomic typing that had begun with other telescopes, which indicate that the asteroid is S-class, silicaceous, stony composition, and it's got a 4-year orbit period. You can see it's got a very elliptical orbit in the right-hand panel, and that makes it challenging to observe from the Earth, makes it challenging to get to it with spacecraft, either for reconnaissance or robust disruption. On the right-hand side here, this plot shows the asteroid relative speed of a spacecraft that arrives at the asteroid as a function of launch date on the horizontal axis and time of flight in days on the vertical axis. In the color scale is the asteroid relative speed. So blue, dark blue is low speed. Green is medium speed, and yellow is high speed. And so high speed in this case means up to about 33 kilometers per second, which is very fast. Remember, DART hit the target asteroid Dimorphos at 6 kilometers per second, to give you a sense of scale. So you can see that there's several dark blue regions with launch dates in late 2028. Those would be ideal times to launch a mission to rendezvous with the asteroid. Rendezvous spacecraft could stay with the asteroid, could characterize the asteroid's mass, shape, size, composition rather precisely, and then stay with the asteroid to provide persistent situational awareness throughout any subsequent attempts to disrupt the asteroid if that were deemed necessary. We could also do a flyby reconnaissance. There's a number of different opportunities to do that. And for those opportunities, the flyby speed varies quite a bit. Some of the opportunities require rather high flyby speeds. I should also point out that this particular asteroid is one of those that I mentioned earlier, which is too small to tolerate the delta V that you would need to deflect it. So there's no way to deflect YR4, at least not impulsively, with like a kinetic impact or a nuclear device. An impulsive technique can only be used to robustly disrupt the object, should that be desired.
I got this.
And now I'm going to hand it over to Adrienne.
Okay. Hi, everyone. Okay. So on this train of 2024 YR4, let's say that we actually want to design a mission to intercept it using a kinetic impactor, and try to robustly disrupt it. So what would a mission like this potentially look like? So this was actually a homework that we did in my class with Brent last semester. I would say it was relatively realistic, and that's why we're presenting it to you guys today. So the requirements and assumptions are listed here for this mission. We would assume that some kind of rendezvous mission would come first before sending something to blow up YR4. So our earliest launch date would be late 2031 in December. Our latest possible launch date, just to make sure that we're actually impacting it before it gets to us or it gets to the moon. And then our max arrival date would be about a month later than that, so no later than 3 months before any lunar encounter. Our assumptions were based off of using a SpaceX Falcon Heavy expendable, assuming a large spacecraft mass delivered to the asteroid, so like greater than 500 kilograms. The Sun-Earth spacecraft angle larger than 3 degrees, just so we can actually track and see the asteroid from Earth. And then Approach phase angle, assumed beta is 3.5, which is relatively conservative. It's based on the DART mission, but with our kinetic energies for this type of mission, that would probably be larger. And then we assume an asteroid density of 3 grams per cubic centimeter. And this is on par with, I'm going to botch this again, silicaceous?
Mhm.
Yes. Asteroids, which is what YR4 is. And then we used a Lambert solver grid scan in order to find like the optimization for this mission. So what's the best time to launch? How much mass can we actually deliver to YR4? And then what even is the largest size asteroid that in this scenario we could disrupt? So these were some of the outputs from this mission analysis, and the plot on the left shows a bunch of departure dates versus the amount of time it takes to get from launch to the asteroid, and then the size of the asteroid that we could disrupt with that time frame, that specific scenario. So again, this is assuming that we were doing a rendezvous mission first to make to scope out whether or not we need to disrupt the asteroid. So in this case, if we wanted to 100% well, I won't say 100%, 99.99% positively completely blow up 2024 YR4, our best launch date would be like early-ish 2032, so April. Our best arrival date was calculated to be around September 2032. Arrival V infinity 21 kilometers per second. We could approximately deliver 10,000 kilograms of mass, and the plot on the right shows a shortwave result from the Lambert solver. And so in this scenario, the largest diameter that we would be able to robustly disrupt using this method is 96 meters in size. And YR4 is believed to be roughly 60 meters on average across. So in this specific scenario, we should be able to blow it up. Okay, so, well, budget and things have changed now, but again, this is theoretical based on homework. So assuming NASA received approval in May or June of this year for a rendezvous mission with YR4, they would ideally need to launch sometime in late 2028. So that's 3.5 years from concept to the launch pad, which is a little scary because I think the average time for like these missions is 5 years from concept development to launch. So if we win and the rendezvous mission yielded that we do in fact need to disrupt YR4, since I think the last time that we reliably get information about it is in 2028, that's right. That would give us 2 years, maybe almost 3, to develop this kinetic impactor concept and get it on the launch pad. Also, yikes, that's not a lot of time. So the bottom line is we either need rapid capability technologies, which are ready to roll onto the launch pad, or we'll be forced to develop some kind of interceptor mission without knowing much about what we're going to hit. And that puts a lot of things at risk, that puts life on Earth at risk. Maybe we could accidentally put it on a trajectory that makes things worse. So again, bottom line is we need to make sure we know what we're looking at before we try to blow it up. So that kind of follows into some of the work that we're going to be doing and what I'll be doing for my PhD over the next couple of years. So like in the event that we need to disrupt using a nuclear device, if that were the right course of action, are we ready for that? And so the current models that have been used or that are in use, especially for the fragmentation and actual disruption of the asteroid, They take a long time to run, weeks to months, even just on supercomputers. So if we want to understand how you blow up a model of Bennu, what is that going to look like? Are those fragments actually going to impact the Earth eventually? Are you going to disrupt it enough that you won't have to worry about any of that? We want to know where all those fragments are going. So it takes a long time to run those models. I feel like I'm going in circles here. So essentially, we need to develop better heuristics for approximating these fragment fields post-disruption, and we also need faster but still sufficiently accurate propagation models, which again is what we'll be investigating over the next couple of years, and hopefully incorporating those various asteroid characteristics, so using different sizes and shapes of the asteroids, different compositions, and then testing out various nuclear detonation scenarios. So what's the right height of burst? Where exactly do you impact the asteroid, and with what speed? So those are kind of the things that we need to be prepared for if we're going to be able to make these decisions. Okay, so speaking of asteroids that are scary, if you all haven't heard about this yet, coming soon to a planet near you on Friday, April 13th, 2029, we will be dodging a galactic bullet, essentially. Apophis is a roughly 350-meter asteroid that will pass us closer than some of our own geosynchronous satellites. And it will be a massive event. People all over the world will be watching. It'll be naked eye visible to almost 2 billion people across parts of Europe and Africa and West Asia. If you haven't really seen a whole lot of information on this yet, you are going to, because something like this happens only once every 7,500 years. So your children and their children won't even get to see it again. So the reason why this is particularly exciting, other than the fact that it scared a lot of people back in 2004, whenever they first found it, is that as it gets so close to Earth, it will experience Earth's gravitational field, and this might alter different things about the asteroid. So its rotation, it could stir material on its surface, and it might look a little bit different before and after the encounter that it has with Earth. So what we are interested in at the University of Maryland is who exactly will be seeing this thing, who will have eyes up there to actually capture and witness Apophis coming by. And then with that, we also want to make it known that Apophis will miss the Earth. Apophis will miss the Earth. Apophis will miss the Earth. Say that 5 times fast. It will not hit us. So for those of you, if this is your first time hearing about it, do not fret. It'll just be really, really cool. So this is kind of what Apophis's trajectory will look like as it approaches Earth on the left-hand side. And then the right side is a little GIF thing that shows just how scary this thing is, how close it will be getting to us over time. And then the bottom picture is what an artist rendition, or the closest image that we have, a model rendering of Apophis. So the closest thing that we think it looks like, but we're hoping that after Apophis comes by and people will be watching and we'll have missions and telescopes, that we'll actually know what this thing looks like. And that almost leads into some of the more specific science questions that we have, which I'll get into their importance later on. But these are some questions that we have derived from the latest decadal survey, as well as the SBAG, Apophis Specific Action Team report. So Apophis, we want to know how it has collisionally and dynamically changed over time, and how its surface and structure has also changed over time. So we want to look at its size and shape, weathering history, relative age of the craters, because that is how we age certain regions of asteroids. And then, like I mentioned earlier, we want to understand more about its effects, or the effects that Earth's gravitational field will have on the asteroid. So will there be any tidal resurfacing due to this encounter? Will there be any mass wasting events or landslides? Will we see boulders moving from pre-encounter to post-encounter? So these are some of the things that we want to keep in mind when we think of a big rock coming next to us that we might get to study. And now comes in our project, Terp Raptor. This is a mission, a flyby mission to Apophis that some of you have probably seen these slides before, that we are making at the University of Maryland. So the leftmost picture is kind of our CAD rendering of the Terp Raptor spacecraft. And then over on the right are the 2 payloads that we want to have on board. So we want to perform a close-up flyby roughly 10 kilometers away from the asteroid during its closest encounter. And we want to capture images of it in the visible and near infrared using these 2 cameras. And then on board, we also plan to have a high-frequency antenna. So we are working with the University of Alaska and the Naval Research Lab and the HARP facility up in Alaska to do some interior measurement experiments of Apophis. So HARP has done this before in the past. They have a great big bistatic transmitter in Alaska, and they have been able to beam signals at asteroids in the past and understand more about what their interior composition looks like, or what their interior structure looks like. And so we want to help them do that for Apophis. And then we've also determined that our mission is relatively low cost, which I would, with our timeline that we've come up with, I would say is probably, if it works, a pretty good proof of concept of a rapid, low cost capability, which I'll explain later why that's also important. So that was pretty brief, but what exactly does an Apophis mission like this have to do with planetary defense? So basically, knowing the size and structure and behavior of these asteroids will allow us to evaluate future impact risk to people on the planet, as well as improve all of our deflection and disruption models like I was talking about earlier. And then this is just a quote straight out of the NASA Planetary Defense Strategy and Action Plan, which basically says the same thing, and just highlights how important it is that we gather this data so that way we're ready for the next thing that comes at us in the future. So there are around 25,000 objects that are larger than 140 meters in size that we believe to exist. Remember, Apophis is roughly 350 meters. And less than half of those have actually been detected and tracked to date. Now, asteroids of Apophis' size can cause mass casualties on a continental scale that would be absolutely devastating for parts of the Earth. And the reason why it's such a great case study is in large part due to its size, but also because of its composition. So the Estoni-type asteroids tend to be, or are the second most common in the solar system. So the more that we learn about Apophis, potentially the more we learn about other asteroids that may head our way in years to come. So as I kind of mentioned earlier, rapid reconnaissance capabilities are a must. Our Terp Raptor mission would take roughly 3 years to develop and deliver to the launch pad at this point. Whereas, like I mentioned earlier, the traditional mission timeline is roughly 5 years. And then, so on board, we're also planning to have like a bunch of commercial off-the-shelf components, which would seriously take years off of the development and build timeline. So I think that that's also what we'll be looking for in the future from other companies, from industry, from NASA, having these rapid capabilities ready to go. And then another reason why this is important is because some asteroids don't give us a very long warning. Sometimes, like the Chelyabinsk asteroid that hit, they come from the sunward direction, and they may present us with even more concerning or shorter timelines for launch, or to be able to disrupt them completely. So in these events, now that Apophis is coming by in 2024 YR4, I think more people are being exposed to the truth of what's happening. So these are capabilities that we're going to have to focus on. So that pretty much brings us to the end of what we were hoping to talk about today. Do you want to take this slide?
Sure.
Okay.
So to wrap up, there's a significant number of potentially hazardous near-Earth objects in that 50 to 150 meter size range that we haven't found yet. The discovery rate is going to soon be increasing, so that underscores the need to get prepared to defend ourselves against them, and as Adrienne pointed out, develop rapid response reconnaissance capabilities. Robust disruption, either kinetically or with a nuclear device, is an important technique that we need to have in our toolbox in case we need it, especially for that size class of near-Earth object, and most especially when we have a short warning time. 2024 YR4 is emblematic of such objects in such situations, and it currently has a 4.3 chance of impacting the moon in 2032, so we're going to be keeping our eye on YR4. And we need to do more work, which is fortunately in progress, to better understand disruption phenomenology so that we can design robust disruption missions that will be effective and reliable. And for that, we need improved heuristics on the mission analysis side to help us confidently predict the onset of fragmentation and the thresholds necessary for robust disruption. And we need to understand those things so that we can design our planetary defense missions for deflection or robust disruption. And as Adrienne pointed out, that's a topic that she's going to be delving into quite deeply with me and some of our colleagues. So finally, as Adrienne pointed out, Apophis is going to be making a very narrow miss of Earth, April 13th, 2029, once in 7,500 years type of event, naked eye visible to, up to 2 billion people worldwide.
And I just want to mention really quick that the universe has a sense of humor because April 13th is a Friday.
That's right. Imagine that. And so the kinetic energy carried by Apophis is equivalent to about 50,000 World War II era atomic bombs. And when people around the world start to realize how close we're coming to something like that, it's bound to capture the world's imagination. And Adrienne also pointed out that Apophis is emblematic of potentially hazardous asteroids writ large, particularly those that could cause continental scale damage. And so studying Apophis helps us become better prepared to defend against objects like it that could actually have us in its crosshairs. So who's going to have eyes on Apophis in space during this incredible natural event? As Adrienne pointed out, at the University of Maryland, we're working to bring our TERP Raptor mission concept to fruition. We're in the process of advancing the concept design, which is already pretty far along, and seeking additional funding so that we can make the mission happen and get to the launch pad in time to provide eyes in space on Apophis for the entire world. And that's our last slide. And so now we're happy to take questions.
Thank you, Brent and Adrienne. I think it's an amazing presentation here. All of the eyes of the audience are focused on your presentation. I think we have a couple of questions online, but let's see first if there's anyone in the room that would like to ask something about this approach for Brent and Adrienne. So while you are thinking about it, there was a question online, I think from Nikki, about will the data that will be gathered from the Apophis mission that you are planning inform in any way any mission to YR4?
That's an interesting question. Apophis and YR4 are both S-type asteroids, and so When we gather data on Apophis, we might learn some new things that might indeed have some applicability to YR4, but we won't know that for sure until we study Apophis.
Thank you. Any other questions from the audience here? So I have a question maybe that will challenge you a bit. If YR4, which was discovered, I believe, in December of 24, if it had been determined to be on impact course with the Earth 2 years later, 4 years later, or 8 years later, what would you do to defend from that situation? Or not you, but what the international community or the scientific community would be able even to do in case that object actually had been determined to be on impact course 2 years after the discovery, 4 years after discovery, or the current 2032 original date, right?
Yeah. So my answer to that would be that we would do several things. So the International Asteroid Warning Network would be activated, and the Space Mission Planning Advisory Group would be activated. And our NASA-led U.S. interagency team would become active and start working on understanding the problem. We would take the data that was available about the object and run Earth impact damage risk assessments that's run out of the Asteroid Threat Assessment Project group at NASA Ames Research Center to understand the potential risks that the asteroid could pose depending on where it might hit. And then we would also work with our partners at Lawrence Livermore and Los Alamos and Sandia Labs to understand kinetic and nuclear mitigation options. And then we would follow the process that we've exercised most recently at the 2025 Planetary Defense Conference to pull all those data together and take a broad view of the problem. Where might the asteroid hit? How much damage might it really cause? What would the damage radius be? We'd engage with FEMA and other disaster management organizations local to the affected area to understand how would they protect people on the ground? Would they need to do some evacuations? These kinds of things. It's a very multifactorial problem. And so, the reason I'm laying all that out is because we'd have to go through that process before making the determination that we would need to either deflect or destroy the asteroid, because if it's as small as YR4 is, being at most maybe 67 meters, it's about an 8 megaton impact. If it's happening in a very remote area or over the ocean, we might just let it hit. But if it's happening over a large metropolitan area with millions of lives at stake, then that might be a different story. In that case, we might instead want to, rapidly try to build a mission. Nahum, you were saying, what if we only had a few years to work with? And, we'd have to, race against the clock and burn the midnight oil and try to do something very unprecedented to rush and launch a mission either to reconnoiter the asteroid, because even if we are going to let it hit, we might want to know more about it, so we might still want to reconnoiter it. Or if we determine that it should be stopped, then we'd have to probably, build that spacecraft under a lot of pressure, in just a couple of years to get it off the ground. And that's, as Adrienne was pointing out, that's a situation we don't want to let ourselves get into. And that's why we really want to develop operational rapid response capabilities where we have pre-built these kinds of spacecraft and where we can ready them for launch on very short notice.
Yeah, great information here. And in terms of those three scenarios that I mentioned, is there going to be any distinction between the use of kinetic impactor versus the nuclear option for these 2 years, 4 years, and 8 years options?
That's a good question. I think, Adrienne, you said the kinetic impactor was what, 10,000 kilograms? Mm-hmm. So that's a big spacecraft, and it's certainly bigger than any interplanetary spacecraft that we've built and launched to date. on the other hand, a nuclear device carrying spacecraft would probably be much smaller than that, and perhaps easier to build and launch. And so those are some trades that need to be studied further, I think, to understand which we would want to do.
Okay, thank you so much. Any comments or questions from the audience, either online or in the room?
We love questions. Nikki?
Nikki? Can Nikki speak? Can you see it? I cannot see the comments.
Can you guys hear me?
Yes.
Oh, great. Oh, my goodness. All morning long, I try to get through here. First of all, thank you so very much, Brent and Adrienne. It's, I got in a little bit late after lunch. But yeah, it's fascinating to hear all of these things. 760 megaton near miss is a wake-up call. So my question, I don't know if we already danced around this answering. How will the Apophis flyby in 2029 will help calibrate future deflection missions, especially when there's really no room for failure?
That's a good question. You want to take that one?
So I touched on it a little bit in the presentation. So Apophis, its composition, what it's made out of, is very similar to a lot of other asteroids that are in our solar system. And knowing its behavior and how it, moves and changes as it gets closer to our planet, what its structure is, that'll help us update our current models, or like our disruption models. So if we get data back from Apophis and we know what it looks like and we know what it's made out of, maybe one day I could chuck that into a model that I worked on for my PhD or something and be able to tell you, okay, if we have another Apophis come by in however many years, this is where you want to hit it. This is with what you want to hit it, what direction you want to either move it or if you want to blow it up. So the more time that we spend at asteroids, the more we will know about them and the better prepared that we will be for ones that come in the future. Hopefully that answers your question.
Thank you.
Yes, thank you.
Can you hear me?
Yes.
Can you still hear us?
I'm Henry Garrett. I was deputy program manager for a program called Clementine. We basically already did everything you've discussed here, except we had a problem with our computer and lost the mission on the way to Tutatis. We did that in 2 years, and we did it for 80 million. So you can do this, but the only problem is we did it with the military, if you understand what I'm saying.
Can you repeat the last sentence?
We did Terry. Did you hear me?
Sorry, you keep cutting out right at the end.
One more time.
Okay. Yeah. We did it with the military space. It was Star Wars.
Right, a military spacecraft. Yeah, I understand.
And the reason I was the NASA rep to that, and if NASA had done it, it would have taken 3 to 4 years. The problem is, I think here you're going to have to go through the military. NRL was the people that slapped the satellite together. It worked perfectly around the moon and stuff, but then we had a problem with communications and lost the satellite. By the way, it's still active. We didn't put a turnoff button on it, and every so often JPL picks it up again. It's lasted 30 years.
That's fantastic.
Anyway,
yeah, that's a good point. I mean, so that's an existence proof that with the right processes, we could build a spacecraft faster and cheaper than we're used to, but we'd have to practice that.
I think what would be really great is if private companies were able to do this. They don't have to go through all of the bureaucracy that NASA does. And the problem with that is that making CubeSats or satellites or kinetic impactors or whatever specifically for potential missions is not something that is profitable to a private company. So you have to find a balance. You have to find some way of enticing these companies to help you make these rapid response missions.
Right.
Yeah.
That's right.
Well, yeah, maybe with the Golden Dome, we may be back in this business again.
Right. I mean, planetary defense will hopefully continue to be a priority for the administration, and if that proves to be true, then that would provide the funding that Adrienne was talking about to allow us to engage with some of these really high performing companies that could do something like this much more rapidly and for less cost than it would require otherwise. So, yeah, Henry, I agree. You lived through a real life example that demonstrates that we can build reconnaissance spacecraft faster and cheaper than most people would suppose. And even on top of that, we've thought about ideas where you build a reconnaissance spacecraft like this, and then you put it in the warehouse so that you got it ready to go. You put an expiration date on it, and I don't know, 5 years or something. I'm just making that number up, but you know what I mean. And then you put it in the warehouse, and then you immediately start building the replacement, or at an appropriate time you start building the replacement. You get to the expiration date, no threat has appeared. Now you've got a fresh one ready to go in the warehouse. You've got one that's in the warehouse. You launch that one on a mission of opportunity to go learn more about some asteroid that is convenient to get to, and then the next recon spacecraft just slides right into the warehouse, and then you just keep cycling that. So you've always got a round in the chamber.
Well, guess what? There is a Clementine 2 sitting in RL somewhere.
Okay, well, maybe we should go talk to our friends.
I don't know if they threw it away or not, but they had the original Vanguard sitting in there in one of their buildings. This backup to Vanguard. So I think they keep things a long time.
I do
Thank
think
you
it would
very
also.
much to you, Henry, to Brent and Adrienne. Brent is the lead organizer and chair of the Planetary Defense Conferences, and me and a few others are helping him to organize and run the conference. And Brent is also educating and inspiring the next generation of planetary defenders. One of them sits just next to you, that's Adrienne. So good luck with your studies, fascinating topic. And we are very happy that you took your time to support the event here to inspire our local audience and online. We'll be in touch very soon, and many, many thanks to you. And now we are going to move to our next speaker, which is Marina Brozovic. And Marina, if you can just introduce yourself, and with you we'll be in touch. Thank you, Brent and Adrienne.
You bet. Thank you.
Hi, everybody. My name is Marina Brozovic. My name is Marina Brozovic, and I work at Jet Propulsion Laboratory here in Pasadena. And I work with planetary radar to observe near-Earth asteroids. So in this talk that I'm going to present here, I have one over here. I have my lapel.
I'll steal this one.
So we're going to go back to the basics, and we're going to look a little bit at the kind of science of the asteroids. And that is going to, I think, complement well to all these nice engineering talks we heard before. So let me start sharing my screen, and if we can get the lights down. So somebody else is sharing, I can send requests.
Yeah, go ahead. Yeah, it's there.
Well, I got my comment in. They're talking about asteroid intercepts and stuff like that, and I pointed out that Clementine already did it or was supposed to do it. They didn't do it. But
Okay, I guess we are ready now to start with this next hour of discussion and presentation. So I'm going to start by showing you this picture of the solar system as we knew it 45 years ago. This was in 1980. And in 1980, in particular, these small bodies, so you're seeing these blue objects between Mars and Jupiter. So these are main belt objects. And in 1980, we knew less than 10,000 of those. And then regarding our near-Earth objects, so these are these little dots in yellow that are closer to Earth. Earth orbit is in white. We knew less than 50 of those. And so the near-Earth asteroids, just to give some background, is once upon a time they were main belt objects. But then under the gravitational influence of Jupiter, Saturn, and Mars, and over millions of years, their orbits ended up migrating into the near-Earth space. And we learned a lot in this last 45 years, especially since NASA really started tracking down these asteroids. So now we went from knowing only 10,000 objects in the main belt. Now we know 1.4 million. And we went from knowing only 50 objects in the near Earth space, and now we know 39,000. So yeah, you're going to see that solar system becomes a very busy place. You're going to see these white dots flash. They flash white as they're being discovered. And if you pay attention among these yellow dots, this population of near-Earth asteroids, there's some red dots. And that is what we call potentially hazardous. And that is kind of, sounds like a very loaded term, but it basically just means that something is large enough and can potentially come close enough that we need to pay attention in the future. So far, we didn't find anything that really we need to worry about, but as Brent and Adrienne mentioned, we still have a way to go regarding our discoveries. So what always kind of fascinates me is that, this main belt, so the true number, I said we know 1.4 million in the main belt. The true number of these objects in the main belt is in hundreds of millions, if not billions, if you count really small sizes. But if you were to sum up this entire big torus of blue, you would end up with only 1/25th mass of our moon. So there's a lot of empty space there. And we know that because we fly our spacecraft all the time there. When we are going toward Jupiter and Saturn and outer planets, we have to go through the main belts, and there's a lot of empty space there. And if you notice, just in the last couple of minutes, there were two objects that whizzed by from out of nowhere. They were yellow, and those were two interstellar objects. First one was Oumuamua, and then the second one was Comet Borisov. So not only do we have our own space junk, these asteroids everywhere, we also have other solar systems. Actually, at this point, they're orbiting galactic centers, so they're kind of galactic center, galactic junk that also happens to transpass through our solar system from time to time, but very, very interesting objects. So I mentioned that NASA started really intensely searching for asteroids, really starting with the first congressional mandate in 1994. So that's when Congress ended up tasking NASA to find 90% of objects of NEAs that are larger than 1 kilometer in size. And that is, we are doing pretty well regarding that. We found more than 90% of those objects. Then the second congressional mandate in 2005, that was George E. Brown Act, requested NASA to find and characterize everything larger than 140 meters in size. And we have a way to go. So you see that we have less than 50% of this population found. And then situation is even more complicated with these less than 140 meters in size. We only know a few percent of that population. So why did I kind of break it down in these three groups? Well, this is kind of 1 kilometer and larger. That is kind of really bad. And then greater than 140 meters is bad. It's regional damage. And then smaller than 140 meters, it's like potentially serious, potentially bad. So luckily, statistics is on our side, and I really want to mention this. So something, the odds of something very large hitting us, something larger than kilometer, we are looking into, millions or tens of millions of years in between such events. Even something larger than 140 meters, again, we are, these events are very rare, hundreds of thousands, a few millions of years. But however, these smaller ones, 140 meters and below, well, first of all, we know very small percentage of that population. We found, it looks like a large number. So it looks like, 26,500. That's a lot of asteroids. But this is just a drop in a bucket of our population models are showing that there are many, many such objects out there. So these would be causing very, very localized consequences, like something citywide. But nonetheless, we don't want them to happen. So Earth's atmosphere is very effective of shielding us from asteroids. So everything that is smaller than about 30 meters and that it's stony in composition is going to burn out. So it's just, you're going to have with the airburst. So that is something that Brent was showing you in one of his introductory slides. We have these, fireballs in the atmosphere, and even the large one that was Chelyabinsk in 2013. That object was about 20 meters in size, stony, and disrupted about 18 kilometers above the surface. However, you still have your shock wave and pressure wave to worry about, because that can end up, shattering windows and still injuring people. So it's again, even these small objects, they are, it's not trivial. And if we have technology to find them, we want to find them. So we've known asteroids for more than 200 years, with the discovery of really asteroid series in the main belt in 1801. And but NASA really, we have first time saw an asteroid from the close-up only in 1991. And that was Galileo's spacecraft was on its way to Jupiter. And it happened to be passing through the main belt and snapped images of asteroid Gaspra. That was the very first image. And this is going on a loop, so you're going to get to see it again. And so far between, all the space agencies from NASA, ESA, JAXA, and Chinese Space Agency, we have close-up images, so spacecraft images from 16 of these objects. So we even have samples collected from 2 of them. One was done by NASA's OSIRIS-REx mission that went on asteroid Bennu, picked up samples and brought it back. And before that, it was Japanese Space Agency, JAXA, ended up on asteroid Ryugu and collected samples and brought it back to Earth. Actually, so when I think about it, there was also Hayabusa collected a little bit of samples from Itokawa. So the bottom line is that we are really starting to kind of understand better what asteroids are. You see, these are these piles of rocks. These are, the building blocks of the solar system. You're looking at the material that's been unchanged for the past 4.5 billion years. You're seeing the surfaces poked with craters. So these are, you're looking into a collisional history of our solar system. You're looking into how the terrestrial planets were built. And really, by studying them, we are really studying the kind of formational history of the terrestrial planets and all the subsequent processes, because our solar system is not static. These are not static objects. Their surfaces are still, they're evolving, their orbits are evolving. Everything in solar system is, on our maybe lifetime, they seem static, but on the long time scales, they are not. So nothing comes close having these great, spacecraft images, but space missions are expensive. They don't happen that often. So kind of what's the next best thing? And so what can we do from ground? And that's what I wanted kind of to tell you a little bit about. That is the work that I've been doing at JPL. So we're using this very large planetary radars to observe and characterize asteroids. Now, I want to point out that with radars, we don't discover asteroids. That's the job for optical telescopes, because we are seeing a very, our radar beam is very narrow. It's a pencil beam. It's 1/16th width of the full moon. And so it would be very inefficient that you go there scanning moon with this very, very tight beam. But optical telescopes are doing a great job. And when they find an asteroid and we know where to point antenna, we can go there and get a whole bunch of information on this asteroid. So yeah, so you're seeing this dish is really huge. This is currently the most powerful radar. This is a DSS-14 antenna. DSS, this is part of DSN network, Deep Space Network. It's a communication network for NASA. This antenna is usually talking to spacecraft. But when they are not using it for spacecraft, we end up using it for science. And it's really huge. It's so you see the cars here compared to the size of the antenna. This is 70-meter in diameter dish. It's equipped with a 0.5 megawatt transmitter, and it's fully steerable. It covers 80% of the sky. So it's a very powerful radar. However, we're still far less, we're about 20 times less sensitive than maybe you heard about Arecibo, that it was in Puerto Rico. That was the world's most powerful radar until December of 2020, when the whole dish suffered structural failure and Arecibo was no more. So this is our next next big thing. We're really observing quite a lot with this. So this is kind of what is really, how does radar work?
Excuse me, can I ask a quick question?
Go ahead.
Is this at the 8 gigahertz
Yeah,
transmission?
we are 8560 megahertz. The Goldstone is 8560, so we are X-band. Arecibo is 2380, so Arecibo was S-band.
Are you capable of going to the Ka band for any of the
No, we
radar
cannot.
observations? Okay.
No, we can't. That is, our klystrons are not designed for that. That is maybe a topic of the future radar. It would actually be Ku band. Ka band would be, well, we can discuss that later, but yeah, it's the future radar would probably go to Ku band. Good point. Yeah. So
Are you considering the Green Bank perhaps upgrade now for capabilities for transmitting and then conducting
yes.
bistatic sort of observations?
Yes, there is there are proposals, there are plans. There's no funding for that at this point. So yes, but the idea is to put a transmitter at Green Bank, which is a 100-meter dish. So we are a 70-meter dish. They would be 100 meters. If you would put something like a 0.5 megawatt transmitter, that would definitely be more sensitive than Goldstone is, and perhaps be close to what Arecibo used to be. So yes, so that is we can all hope. Let's say that, let's put it that way.
Absolutely. I know they've already done a demonstration of a very low power
Yes.
imaging of the moon's surface, and that was really pretty spectacular. Anyway, thank you very much for your
Yes, they
response.
did. They're working with Raytheon, and they did some preliminary work with a very small, like 20-watt transmitter, and they obtained some super high resolution images of the moon. But going back to this slide, so radar. For those of you who are new to this kind of field, it just stands for radio detection and ranging, and in essence, it's kind of describing how radar works. Radar is like a flashlight. You illuminate the object with microwaves or radio waves, and so the echo that comes back is carrying a whole lot of information about that object. So not only does it really pinpoint in space where exactly the object is, but it is also telling us how large it is, how fast it's rotating, what is its shape. We can even derive the surface properties, and we can even figure out if it has companions. A lot of these near-Earth asteroids are actually binary systems, and we're pretty good. Radar has discovered more than 70% of satellites of the binary systems. So all this is sounding really, really good. So, kind of always, what's the catch with radar? Well, the catch is that your signal drops really fast. So you can't observe very far because you're losing r to the square transmitting, and then the signal again drops r to the square back. So in other words, if an object from day to day ends up being twice as distant your signal drops by a factor of 16. So that means that most of the objects that we are observing are within about 15 million kilometers. So that would be 1/10 of distance from Earth to the sun. And these asteroids have to be at least, usually they are several hundred meters in size. If they're larger, we can detect them when they are further away. And if they're small, they need to come close. So that's kind of the catch with radar. It's a great instrument, but they need to be relatively close. And that's why our SIBO was powerful enough to reach all the way to main belt. But with Goldstone, we really are only observing near-Earth asteroids. And so I'll be showing you some radar images. And I just want to kind of mention that they're very different than your images that you would take that you would see through a telescope. So here on the right side, this would be your view through a telescope. And then on the left side, this is how radar sees it. So basically, telescope sees plane of sky. It sees your X and Y coordinates. In the case of radar, always imagine that radar is illuminating this object from the top of the screen. And so you're seeing these things that are being illuminated by radar. And so vertical dimension is your spatial dimension, but it's not X and Y, it is Z, it is the depth. It's how the object looks like as a function from the radar. As you're illuminating it and things come back, you're building a picture of the depth profile of that object. And then on horizontal axis, this is Doppler frequency. Now that is only just kind of really telling you how fast parts of the object are moving towards you or away from you. So something that's rotating very rapidly is going to be wide in Doppler frequency, and something that's rotating very slowly is going to be very narrow. So very quickly, we're going to see kind of some examples. We do have a software that goes from these, sometimes non-intuitive radar images and inverts them into 3D shapes. And I have a full box of 3D shapes at my desk. I forgot to bring it. I'll maybe show it during Q&A session. So Phil, there is a white bag. Okay, thank you. So yes, so this is what we can show later. So this is one such model that we got with the inversion, and so yes, so we have we are the only kind of ground capability that can see the details of an asteroid surface as small as surface boulders. So here's a side-by-side comparison. So to your right, this is Asteroid Totatis as it was imaged by Chinese Chang'e 2 spacecraft. And you see its surface full of boulders. And then you see on the right side how radar was seeing it. These are, as I said, radar images. So the thing is that, so it was an interesting story with the Chang'e spacecraft, because that originally was a lunar orbiter. So when the spacecraft ended up finishing its prime mission, it ended up kind of taking off from the moon and getting parked in L2. So it's this gravitationally stable point. And it was just kind of station keeping there. And nobody knew why is it being parked there. And then when in December of 2013, we had a relatively close flyby of asteroid Totatis, came relatively close to Earth. So amateur astronomers are always kind of looking who is doing what, and they notice that, and they can actually spot a spacecraft because it's pretty close. So they saw it taking off, and very quickly they realized they're going on a flyby. They'll be intercepting. They'll be doing a flyby of asteroid Totatis. But everything in space is a moving platform, and if you don't have enough fuel and enough time to match the velocity of the approaching asteroid, you end up with a super fast flyby. So their entire flyby of this asteroid was, they got 15 seconds of high resolution data. That was it. And their best resolution was from about 18 kilometers away. They have a few meter resolution on top of asteroid. In the meantime, we were observing a few weeks, and asteroid was 7 million kilometers for us as opposed to 10 kilometers. And we were still getting comparable resolution, and we collected 65 hours of high resolution imaging data. So we got, after some work, we could actually go and invert this to get a comparable quality shape model, and we got it, from Earth as opposed to from space. And we have our limiting resolution with a radar is few meters. So we have actually one smaller antenna that has a higher imaging capability. It's about 2 meter resolution. And then with our big antenna, we are about 4 meter resolution that we can do. And if you're looking at really big objects, that means tens of thousands of pixels. You're resolving how it looks like. So this is example of a very big object. This is a kilometer size. You see it peanut shaped. They're very common in near Earth population. I'm going to play that again. You're seeing many details on the surface of how the asteroid looks like. And this is something that is slightly smaller. This is about 330 meters. It's a binary. So here is, it looks like it has this tiny little satellite. The satellite is not so tiny because what you have to remember is that only vertical dimension is really your spatial dimension. So their sizes you're comparing vertically. What is horizontal axis telling you is just how fast they're rotating. And that means that the primary that looks something like this is just spinning very rapidly, probably something in the order of 2.5 hours. And this satellite, it has this smaller satellite that is orbiting around its primary with a period of about 12 hours or something like that. So a lot of features on the primary of this object. And then finally, on the small object, if you have something that is sub 100 meters in size, well, the images start being grainy. And we would love to have more resolution, but we are limited by hardware. And so, but it's still enough. I mean, these are very numerous. So this asteroid over here, the long axis is about 60 meters. The important stuff for planetary defense is there. How large is it? Well, in radar, it's very simple. It's a matter of you just count the number of pixels vertically where you see the echo, and you multiply by your 4 meter resolution. There is a proxy for kind of half for radii of the object. So you get a very quick ballpark estimate of its size. And because in optical telescopes, you are just observing a speck of light. And optical telescopes cannot tell you the size. You don't know whether you're looking in something that's optically very dark and large, or that you're looking into something that is optically very bright and really small. So that's why you need kind of the only two kind of really direct methods is either radar, and you go count your pixels, do your shape model, and then you can really get a fine estimate of how large it is. Very important, you need to know what's coming your way. Or occultations, stellar occultations. So those are much more tricky because you have to have a lucky event that asteroid is passing over a really bright star. And then when you have objects that are this small, relatively near asteroids are, relatively small. We're talking about, events that are happening super fast. So you have to have millisecond resolution in order to get that star, measure the star dimming. So it's not an easy technique, and it's not something that you can do on a wide sample as we can. So we are observing at this point about more than 50 of near-Earth asteroids every year. This is kind of some statistics in the past 3 years. Last year we had 55 of them. This year we'll probably have the same number of objects. And with each one of them, each one of them is a kind of little space mission in itself, because going into our radar experiment, and we know to observe like 2 weeks of the month. Every track knows to last 5-6 hours. So we observe a lot, and it's really exciting when you have that very first track when you don't know what you're going to get. Roughly, you only know the visual brightness, and that's kind of within factor of 2 in size. So you don't know what size it is. You don't know what type of the object it is. Sometimes the optical observers get the light curves and they tell you how fast it's rotating. So that helps. But going in, you really, you can make every single one of these objects is a kind of, potential for a discovery. So it's really kind of, you always get a kick out of things. I mean, even, it never gets old. Let me put it that way. So this is a nice example of a peanut-shaped asteroid. Again, I keep showing you these peanuts, and peanuts are very common. So based on our radar data sets, we're estimating that at least 15% of asteroids in a near-Earth population that are larger than 200 meters in size are of this size, of this shape. And the reason why I say at least is because we cannot always resolve. They don't come close enough, so we can't resolve all of them. And that's why, we can do lower bound on, well, at least we see at least 15% of them. It probably is much larger, but we can't resolve every single one of them. And the same amount is the binaries. Yeah, another 15% is binaries. So that is kind of really significant because based on the sample, we know what's coming our way. So even if something is, completely unknown and you end up with some kind of initial impact risk, well, we can guess what kind of object is coming our way. And another kind of, I keep showing you these names, these acronyms, 2024 ON, and there is a method to the madness. There is a method to decipher this. So 2024 always just stands when it was discovered. And then the first letter, in this case O, they're divvied up in bi-weekly periods. And letter I is being skipped because it's too similar to 1. So letter O in that nomenclature is the 14th. And that means that this object was discovered in the second week of July. So 2024, it was discovered in the second week of July. And then letter N is the 13th letter. And that means this was the 13th object, small body, small solar system, a small body in solar system that was discovered in that bi-weekly period. So that's how it works for all of these things that I'm throwing at you. So again, this was our target of opportunity. It approached relatively closely. It was less than 3 lunar distances. So we like to talk about lunar distances. Lunar distance is 380,000 kilometers. It really is our, we consider it very close when something is within, say, 5 lunar distances. And we get extraordinary strong radar targets and get all kinds of really nice imaging. And this one, so the sequence is starting in top right corner and it ends in the bottom left. This object was rotating with about a period of 6 hours. And as you can see, we almost completed, I have it right here. So we almost completed one full rotation of this object. We covered it in radar images. And this bright speck on a surface, that for sure is a surface boulder, and there's more than one of them. And the long axis here, this object is in the realm of 450 to 500 meters, so pretty big object. And here is an example of a really nice binary we observed in November of 22. So if you're looking at the, how the primary looks like, it looks obviously this is a rubble pile. So if you remember those in the opening sequence when I was showing you close-up spacecraft images of various asteroids, there were these things just full of boulders of various sizes, from smaller than the grain of sand to something tens of meters in size. And it really is in essence what the asteroids are. These are piles of rock that are loosely held together by self-gravity. And I mentioned that about 15% of them end up having a satellite. And why we like binaries in general? Well, binaries are a way to figure out mass of the system. Otherwise, it really is not easy to figure out how massive an asteroid is. But here, it's actually pretty simple because there's something called Kepler's third law. So if you end up measuring, you image where your satellite is, you measure that separation, use it as a proxy for semi-major axis, and you estimate how fast how fast the satellite is revolving around the primary, well, you get a system mass. You get system mass, and then because you know the size, because you count your pixels and multiply by resolution, you can figure out densities. And from densities, you know what's inside these objects. So I mentioned these are the bricks of the solar system. And if you have binary systems and you know the sizes of the components, you have a direct insight in how their interiors look like. And the answer is a lot of empty space, because we are seeing they're pretty low density objects. So these objects are about 1.5 grams per centimeter cubed, maybe up to 2 grams centimeter cubed, which means you have a lot of empty space. And that is exactly that description. A pile of rocks all the way through that is just kind of, hanging in there and, kind of is being loosely held together. And these are the small objects that we know to observe. So this is something, again, that population that we currently discovered like less than 3% of. So objects smaller than 140 meters in diameter that are not even considered, but like potentially hazardous, but they can be, because you don't want to if you've ever been to Arizona on Meteor Crater, well, that's what 50-meter iron nickel asteroid does to you. You end up with a 1.2 kilometer wide crater. So the reason why we are interested even in the small rocks, despite us not getting, we are getting limited resolution on them, but we need to understand them. We need to understand their densities, because they are the most abundant population. And we need to know what to expect if one of these things ends up on impact trajectory. So this one is, they have some themes in common. The big ones, they tend to be roundish, and they have satellites and their contact binaries. And then these small ones, they're just irregular. They don't have satellites. They know to have this very, very angular shape. They know to tumble. And what we are noticing is that we think that something is really happening in that magic number of about 200 meters in size. Objects larger than that are piles of rocks. Objects smaller than that, some of them are still piles of rock, but some of them are spinning so fast that they definitely need to have some cohesive strength to hold it together. And we have found objects that are a few tens of meters in size that are rotating with a period of 10 seconds. So, or even faster than that. So that is extraordinary. And those objects are probably monolithic. So that's why I'm saying, there is the kind of this ongoing debate. What are the densities of the larger ones with respect to smaller ones? And the smaller ones are just now, we are starting to have tools to study them. And radar is one of the really good characterization tools to understand how the small population looks like. But there is what I want to kind of now talk about is there is no shortage of really neat targets coming up. In this animation, I'm just showing you large ones coming within all of these are coming within 3 lunar distances, so really close. They're all larger than few football stadiums. So all of these are potentially hazardous asteroids. You see them in all kinds of orbits around the sun. Some of them are, fairly circular. Some of them are really elongated. All of them are intercepting Earth's orbit. And this is just what we know of. If you're looking at their designations, so you're seeing 2024, 2025, there's 24 again, 2023. This means they're constantly being discovered. So that means this is not static. Every single time we look at the list, we kind of like, okay, there goes another one on our radar schedule. So because we are already planning for these. And yes, in the end, this is going to culminate in the really close approach of asteroid Apophis. But I'm just saying, I'm really excited for many of these other ones, because some of them could be more interesting scientifically. Scientifically, Apophis is definitely very close. But some of these other ones have, are larger. We'll get to see much more on their surfaces, at least from ground. Their spectral class is more exotic, for carbonaceous or something rich in water. Those are scientifically perhaps more interesting objects than Apophis. But I want to go through just a few of them, my favorite kind of ones. Okay, so this is a kind of family portrait of what we know is coming that is large and within three lunar distances. This is 10 statues of liberty on the left side. This is 10 football fields. That's what NASA always does in their press releases. That's apparently the universal measure of stuff. And I kind of plotted just what is coming our way. And you see Apophis in 2029 doesn't really stand out. They're bigger objects coming our way. And I want to kind of highlight some of them. So this one was notorious object when it was discovered in 1999. This one was the one that briefly reached, high impact probability was not negligible, and it caused a lot of media commotion. And of course, as more data came through, it was very obvious that this object is just passing by, but we have no impact probability in the foreseeable future that we can calculate the orbit. And at this point, we have even precovery measurements. So this data arc is like 65 years old. So 65 years long data arc is giving you very, very good orbit for something that has maybe 2-year orbital period around the sun. It is large object. We don't know how large. It can be anywhere from 650 meters to 1.5 kilometers. And it will be approaching exactly at 1 lunar distance in 2027. We should be expecting really phenomenal images from ground. So the optical telescopes, now it's coming this new generation of adaptive optic systems that can perhaps start getting plane of sky resolved images of closely approaching near-Earth asteroids. It is not easy. Even with you can have a class of 12 to 14 meters mirror, but these objects are moving really fast across the sky, and you have to keep exposing and tracking. And that's not something that optical telescopes are designed for. Our radar is designed to track a spacecraft. We can move super fast. We're moving like a quarter degree a second. So we can track it. Optical telescopes have trouble. So this one is a great one. My second favorite would be 2001 WN5. This one is coming with 1 lunar distance, but notice it's not always going through the plane of Earth-Moon orbit. This one is going slightly, it's still approaching Earth within 0.65 lunar distances, but it's kind of below the plane. That's the approach. Again, it's optically dark, so this is very interesting, scientifically interesting spectral class of object, because it has carbonaceous, it has probably all kinds of really complex organic chemistry, water. So this object has been already observed twice by Arecibo. Its orbit is in a very good shape. So again, something to definitely be excited about. And finally, yes, everybody, Apophis, everybody is really anticipating Apophis. It is, this is the geosynchronous ring of satellites. Apophis on April 13th, yes, it's Friday, is approaching from the southern declinations. It's going kind of above the plane, the geosynchronous satellites, and then it's going toward, northwards and toward the sun. It is a very rare event. So I was hearing once in 6,000 years. That's something that Paul Chodas was calculating. I heard that Brent was saying once every 7,500. It's rare. That is the bottom line. Something this large approaching this closely. It's approaching only 4.9 Earth radii from the surface. That is 31,000 kilometers. And it is going to be, yes, observable with a naked eye. In 2004, when it was discovered, it was actually an interesting story, because it was discovered, observed for 2 days, and then lost for 6 months. And then just accidentally recovered from the Siding Spring survey in Australia. And that's when that probability of impact briefly reached 3%. But then very quickly, there were more observations. Also, Arecibo observed it, pinged it it got very precise measurements. And then that any chance of impact was eliminated in 2029. There were some other later options, but we again observed it with radar in 2013 and 2021. We even have very tight occultation point on it. The bottom line is that, unfortunately, this object is now completely banished from our Sentry list. So JPL has something that's called Sentry. It's this automated software that is constantly going through the latest discoveries, latest data. They are publicly posted on Minor Planet Center. Our page is also public. So this is kind of, constantly changing table, calculating impact probabilities for the foreseeable future while we can reliably calculate orbits. So it's usually a few hundred years in the future. And yes, the Apophis for that time, it's not even more on the Sentry list. So so it's just kind of one of those enjoy the show in 2029. This is a very kind of dramatic view of its flyby. What I'm showing you here is a kind of ground track, and you will see it. Yes, it's coming from the from the south. You'll see the ground track will start. So that's the point where it's closest to the Earth's surface. It is coming on Australia. You're going to see sweeping across Africa. And at the moment of closest approach, that 4.9 Earth radii from the Earth's surface, because you also hear number 5.9, that's from Geocenter, that is going to be in mid-Atlantic. And the best views are going to be from the west coast of Africa and Southwest Europe. Unfortunately, we have still late afternoon in the northern United States. So we will not be seeing it with a naked eye because it becomes daytime object. And optical observers, next time they see it, this object is going to be November because you can observe when something is flying, is very close to the sun. With radar, we don't care if it's day or night. So we already have plans to start observing about 6 weeks before closest approach and going probably 6 weeks after the closest approach, as long as we can detect it. So yeah, and there's going to be, Europeans are planning a mission called Ramses. NASA has Osiris Apex currently in flight. It's adjusting its orbit to be on intercept course to meet up with the asteroid after the closest flyby. There will probably be others. So definitely a great opportunity to study another near Earth asteroid from close proximity, both from the ground and from space. So with that, this is my last slide. Thank you all for your attention, and I'll take your questions.
Do you know if Parks has radar observing capability so they could observe it from its southern approach?
So you're saying you mentioned Parks, right?
Yeah, correct. All right.
So Parks is a radio antenna, so it does not have a transmitter. It has only receiver.
Oh, okay.
However, yes, we have Goldstone. So our DSS, our big antenna, 70 meter. There is also another DSN network antenna, DSS 43, that is in Canberra, Australia, and it does have a small transmitter. And Parks currently doesn't have a receiver in the right frequency. It has to have the C-band. And so, but they're in the process of getting receiver for C-band. And that's going to be it's going to be, on top of my head, I don't remember. It's not going to be obviously not as powerful as Goldstone, but I want to say it's going to be 10% of our DSS 14 antenna. So yeah, Parks is 64 meters. Radio dish.
So this will be like a bistatic detection system? Okay.
They're already doing it. So DSS 43, it's a small but emerging capability for extraordinary close approaches. They're using their C-band transmitter, and currently they are receiving at the ATCA, that's Australian Compact Array. It's a 4 radio antennas, 4 smaller radio antennas. So they know to be receiving either with one or more than one of those. But that is as I said, that significantly gets their signal down. That is they they are in like a few percent sensitivity of what we have.
Hello, Marina, are you able to hear me?
Yes.
Oh, great. This is Madhu Thangavelu from the University of Southern California. This was a fantastic presentation. And I wonder, were you at Goldstone when the fires were raging in the down the hill from us here in the Pacific Palisades?
So you were asking how did Goldstone fare?
Yeah, how did Goldstone fare?
No. It was okay. So there was we didn't run radar at the time. So, but what was interesting is that, we have a spacecraft control center in the on site. So
Yeah.
from JPL, we end up communicating with spacecrafts all the time, and there's always this readiness exercise that happens once a year where they move all their operations into Goldstone. And at no point, this was the very first year in all these, I think, more than 65 years they've been preparing for, that they had to move all the spacecraft operations to Goldstone, and it went without any problem. So it really was kind of, the lab was, the fires were very close to the lab. It was very serious. A lot of colleagues, lost their houses. Lab was closed for a week. And so anyway, but it was kind of, they did manage to, they completely moved all the spacecraft operations to Goldstone at the time, and it was successful.
Excellent. I put out a little chat note saying that Dr. Eb Rivkin was my mentor at USC and told me the stories about how the Deep Space Network came into being. And it's a fascinating story on how deep space communications slowly grew up at JPL. And I'm so glad to hear the wonderful things you're able to do with this nearly, the current thinking is that DSN is on its way out. Can you tell us anything about optical comm, please?
Yeah, so I'm really not involved in optical comms. But yeah, they have a test facility on the 34-meter antenna, our DSS-13. So bottom line is, okay, so currently spacecrafts are working with radio communication. Yeah. And there are severe limitations of how much data you can uplink and downlink. So the next thing is to do these optical comms. So you are communicating pretty much with laser, and then you pretty much move into optical bandwidths. So you really kind of have optical telescopes receiving, looking for signal from spacecraft. I know it's an ongoing project. So they have mirrors set up on DSS-13, yeah, I know that. I think that so far they say it's running on track, that everything is on track, but a lot of effort JPL is going into DSOC at the moment. So because that will really kind of, if you're going to Mars in a big kind of serious way, you need to start your data. You need to start getting data in a much more efficient manner than in radio frequencies.
Thank you.
Thank you. We also have a question in the room here.
Hello, and I love your presentation. Are there any viable alternatives to radio communication for asteroid detection?
Or so are you asking me if we can search for asteroids with radar?
Because from my understanding, I have limited understanding on this, but radio frequencies are being used to pretty much detect and study asteroids, correct, for this project?
Yes.
Are there any alternatives to radio frequencies? Like, for example, I think you just went into using lasers and optical?
I mean, yeah, I mean, you can go through higher frequencies. You know, you can go, like we were discussing at the beginning of this talk. There was a question regarding, can you go to KU band and make a radar? Yes, you know, you can move to different. Each one of these comes with their own advantages, technical challenge. You know, the next big thing is probably also getting these adaptive optics working. So instead of getting, you know, kind of radar images in parallel, getting these resolved so that you don't anymore have just a speck of light on the sky, that you have a adaptive optic image of how it looks like. So for that, again, that is going to be a new class of telescopes. Atmosphere is always a problem, but they're managing to pretty, you know, they have their ways of getting rid of you know, problems with atmosphere and stuff like that. So there are many ways to study asteroids. Spectroscopy is an important thing to, you know, to understanding what these objects are made of. We have colleagues working on kind of, you know, we are kind of attacking this problem from with all possible instruments, and each one of us is kind of getting a little bit of what's out there. And so yeah, it takes a village to do science.
Thank you very much.
Mm-hmm.
Thank you. Any other questions from anyone online or?
Yes. Well, optical comms are fantastic, except on a cloudy day. I have a question. Has there been any radar observations of cometary objects? And I'm
Yes.
thinking, oh, there has. Okay, that's fantastic.
21 of them, yes. So this is the kind of tricky thing with comets. They don't come close enough. So you know, you need to. So Arecibo was the one that really observed most of them, because Arecibo had wider reach than we do. But you know, every once in a while there is a comet that comes close enough within that magic 1/10 AU, and that is large enough that we can detect it with radar. And it's really interesting because you can detect coma. So you can detect those particles from the coma. It's kind of, you know, you are seeing the echo that comes from the cometary nucleus, but then you see this wide skirt that is coming from all the particles. And you can derive a lot of information about how large these particles are in coma and how fast they are moving. And also another thing that we see, we don't maybe see comets, but we see dead comets, because a lot of times you have, you look at kind of this orbit of an asteroid and you see that it's really coming close to Jupiter. And you look at that, what's called Tisserand parameter. There's this kind of combination of orbital parameters that whenever it's smaller than 3, that means that is probably could be Jupiter family comet that did one too many trips around the sun, exhausted all the volatiles, and now you're just looking at the really dead cometary nuclei. So that's we know to observe those.
Are any of the gases that being the effluence from comets that are ionized sufficiently where the radar will
No
bounce
particles.
off
For us, you know, we are really looking. You can detect those particles, but not gases. You go to the radio. You do passive radio kind of telescope stuff if you are looking at some of that ionization and stuff like that.
Thank you.
Can you hear me?
Question online. Is John online?
Yes, this is John. Can you hear me?
Yes.
Yes. So I believe you said, based on the calculations from the binaries, that the average density was something like 3 grams per centimeter square cubed. Is that right?
They're smaller than that. They're at most 2.2. They range from like a little bit above 1, like 1.5 to about 2.2. So yeah, and the rock, as you know, is a 3-4 grams centimeter cube. So the only way to explain that is empty space. So basically it's a void. It's a, imagine pile of rock that is kind of loosely held together, and you have a lot of obviously a lot of void between these rocks are not closely packed together. So that's why you get that density.
Well, what I wonder is whether it could be water ice, which only has a density less than 1, that could be there instead of just empty space between the rocks.
Well, I mean, we don't know what is exactly on the side. We obviously know if if you had it close to the surface, you would end up probably with some kind of process and outgassing, and then we would call it a comet. But that boundary between what is asteroid, what is a comet is a blurry one. But most of the times, water is embedded in minerals. So you have some hydrated minerals inside asteroids as opposed to just water ice. So it's if you grab there are some some companies, startups that are trying to just catch a small asteroid, put it in a bag and heat it up and kind of release the water from the minerals. So evaporate it. So bake it and end up to release the water that is captured inside the asteroid.
Is there any way to detect whether using radar whether there is water ice? Can radar see water ice is different from basalt or some other rock?
Yes, water ice signature. It is more, that work is kind of more on with respect to Mars. Some stuff was done on Mars, some stuff on the moon. I do not regarding asteroids, it's just not these big pockets of ice are not that we know of are on the surface of asteroids. So and we don't know what's really in the interiors. But yes, there's some you can infer if that could be water based on a scattering properties. There are scattering properties of signal that comes back. It has to be well calibrated. You take it slightly different way, and yes, you can infer that perhaps it's not a definite method. So it's not a definite method for detection of water ice.
Thank you.
Very interesting presentation. Thank you.
Thank you. And one last question from Mark online.
Oh, sure. Well, there was a comment. One was that regarding laser versus radio, that presented something a couple of years ago at this mini conference, suggesting using a laser to search an incoming stream, a meteor shower essentially, which is typically cometary debris. That was one comment, and I think that existing telescopes, some of the I guess they're Space Force, not Air Force now, but there's a couple of good telescopes that ought to be able to do that. One is Amos in Hawaii, and there's another one in New Mexico, Starfire optical range. So that would be interesting and I think valuable. It would use exactly the same math as, and procedures, but with a different wavelength that's much, much smaller and without the same dispersion of the beam. So you'd be able to aim very closely to your target, which with an incoming meteor stream, you know what sector of the sky that's coming from. So and you could raster and look for return signals. So that's one comment. The other one was that we had this nice presentation earlier on the DART mission, and it had a comma for quite a while. And it seemed to me that the presenter suggested that there might be some type of outgassing from the interior after the impact, that comma seemed to last longer than you would have expected. The stream of debris that was blown away by the solar wind. So it was quite remarkable to see this long line, in the images that were months after the impact, and I thought that was kind of insightful. So I don't think the question is set yet as to how much ice there might be inside, mixed in with the other minerals. It could be that that some of these are icy. I guess I have one more comment, and that's that, goes with the meteor showers and the idea that they're cometary debris. And some of them, I think Encke's comet is much lower, and it has many bodies that are associated with it from the breakup of the comet, essentially. So that one, I think it's not a Jupiter crossing comet. It's a much lower comet with about a 3-year period, something like that, 3.5. Anyway, just those were the things I wanted to say, and thank you for the insight here, and happy to hear it all.
Thank you, Mark. Thank you, Mark, and thank you, Marina. Always fascinating talk and pictures about observing objects that are out in outer space. I also have a question, but I will defer it to the Q&A at the end.
Yes, thank you.
And now we are going to move to the next speaker, which is Isaiah, I believe. And
Hello.
Are you online?
Yes, can you hear me?
Yes, so just hold on a second here so we can set up the equipment back to the room. And we can start. We good?
Yeah, we're good.
Yeah.
Yes, thank you.
And can we go forward or?
Yeah.
Okay. So Isaiah, please introduce yourself to the audience here and take it away.
Perfect. Yeah, thanks for having me, guys. My name's Isaiah Santistevan. I'm a postdoctoral researcher here at Lawrence Livermore National Laboratory here in California, near the Bay Area. I started the lab maybe about 2 years ago, so relatively new both to planetary defense and to the lab. Before I came here, I did my PhD over at UC Davis, where I got a PhD in physics, mostly in computational astrophysics, where I studied something very different, which was galaxy formation and evolution, and looking at the orbits of small satellite galaxies that kind of orbit around galaxies like the Milky Way. So planetary defense is pretty new to me in general. So I've learned a lot in the last 2 years, and I'm happy to share what we do here at the lab in planetary defense, and mostly focus on some of the stuff that a few of us do in terms of simulating asteroid deflection and disruption with a nuclear device. And so just a couple of things. I may or may not have to turn my camera off later if my computer battery is going to get a little low. And the other thing is just that it's nice to go later in the day, because now a lot of people have done all the interesting introductory material discussion. So thankfully I can probably go through some of the intro slides a little quickly. But planetary defense is one of those fields where it's still really new. We can't really go out and do very many experiments on, for instance, impacting asteroids. We can't do that on a fairly regular basis because it's really complicated and expensive to do so. So it's planetary defense itself is I think a pretty still infantry kind of field. We don't really have a large body of literature to kind of refer back to on specific events that we helped to prevent. And so we rely a lot on computational modeling and simulation work. I think we've seen this slide earlier today in Andy Rivkin's talk that just kind of lays out the different asteroid size and threat scales. And again, kind of the rough rule of thumb that I generally think about is things below 10-ish meters, or things that are just going to burn up in the atmosphere, no threat. Things 25-ish meters might cause an airburst explosion that can kind of damage windows, and then 100 meters and above, and even 50 meters if they're more metallic, can ultimately reach the surface of the Earth and cause some craters and cause lots of devastation. So back in 2018, the Office of Science and Technology Policy released the National Near Earth Object, or NEO, Preparedness Strategy and Action Plan, really to define some of these core things that I think the country wants to focus on in terms of kind of setting up a framework for thinking about planetary defense. One of which is to enhance some NEO detections, tracking, finding them, looking at their orbits and characterizing them, kind of like how we just heard in the previous talk. A lot of what we do here at Livermore is mostly in one of the second goals, which is to work on modeling, prediction, and information integration, primarily in terms of preventing any kind of impact. So doing any kind of deflection or disruption mission. And then also increasing both the international cooperation and routinely going through exercises where we can really benefit from collaborating with other people. And then in 2023, this policy was updated to include a sixth goal, which is to improve the US management of planetary defense through interagency collaboration. And so since starting, I'm still pretty new, but I've already been able to interact with a lot of people from different agencies. For instance, people at FEMA who are interested in kind of developing a framework for, if we had a hypothetical scenario and an asteroid were coming in, how do they think about evacuating people and potentially building new structures to help accommodate that. We heard from some of my colleagues over here at NASA, JPL, Johns Hopkins Applied Physics Laboratory, Goddard, PDCO, and Ames. We interact with people on a very regular basis at these agencies. And then for the national labs, we have a pretty big team working here at Livermore, looking at lots of different planetary defense topics. But we also interact with people from Los Alamos National Lab and from Sandia. And so it's nice when we have some of these larger exercises like the Planetary Defense Conference, where we're able to either work on kind of a similar project and kind of show everybody our newer modeling capabilities, but also learn to see what other people are doing to help push the field further every year. We've also seen this slide both in Brent's talk, so I won't talk too much about it, but there's lots of different ways that we can prevent potential impacts from happening, so different mitigation options. The only two that I was going to describe were the kinetic impactor type mitigation method. This is all related to the type of stuff that both Brent and Andy Rivkin were talking about earlier, and Adrienne, where you have a spacecraft and you have an asteroid and you want to basically impact the asteroid with the spacecraft to either give it a push or to cause it to break apart. Generally, it's good for smaller kinds of asteroids. Larger ones require you to either send a really massive kinetic impactor out there or to send a bunch of, multiple kinetic impactors to subsequently hit to cause enough of a deflection ahead of time. And so either sending something really big out there or sending a bunch of them ends up being a logistical, a larger logistical problem in terms of sending out multiple spacecraft to do that. And so if we had something really massive, we might instead want to go to the nuclear option, where essentially, and I'll talk about this a little bit more in depth of how it works, but we send a nuclear explosive device, or an NED, out into space to either give the asteroid a gentle push or to disrupt it completely. And I just want to highlight that so with the kinetic impactor method, we now have essentially experience doing this with DART, where they sent out a spacecraft. The Dimorphos and Didymos weren't necessarily a threat to begin with, but they exercise the capability of sending a spacecraft out to hit an asteroid and to cause an appreciable detection in its orbit. And so kinetic impactor is appealing in that sense, in the sense of we've kind of tested this once before, whereas with the nuclear mitigation option, we have never done this before. And so it's all purely hypothetical. The US has stopped nuclear testing since 1992. And we've also signed a treaty, the Outer Space Treaty, where we're not allowed to send nuclear devices into space. And so we likely won't ever do this kind of experiment either, to kind of validate against some of these models. And so only, I think, under the most dire of existential human threats, if we were to need a NED to actually deflect or disrupt an object, would we ever do this? And so I'm not really saying that we should do this, but if we ever had to, then it would be good at least to know and have some kind of modeling capabilities to look back on to help prepare for a mission like that. So we've kind of heard a little bit about this during some of the earlier talks, but we can either deflect an asteroid or we can disrupt it. And what that really means is, for a successful deflection mission, we want to give it kind of a gentle push, give it a deflection velocity or a delta V early enough in time so that the orbit that it would hit on Earth essentially misses it completely. And we want to do this in a sense of keeping the asteroid intact so it's not breaking apart into multiple objects. And then on the other hand, we talk about disruption, and in general, we talk about robust disruption, which means breaking the asteroid apart into as many small fragments as possible, such that even if a single fragment were to remain on an Earth impact trajectory, hopefully it's small enough so that it just burns up in the Earth's atmosphere and poses no threat to the planet. What we don't want to do is we don't want to do either of these missions halfway. So we don't want to try to deflect it and accidentally break it apart, or we don't want to try to break it apart and not break it apart enough, because then you just have a bunch of relatively large chunks that are still on an Earth impact trajectory. There are some rules of thumb that Brent laid out earlier. When we think about deflection and disruption types of missions, what we call the 10% rule, if you remember, is to deflect an asteroid, we try to aim for a delta V or a deflection velocity that's something like less than 10% of the escape speed of the object. We want to keep it relatively low so that we don't risk accidentally breaking the asteroid apart. Whereas if you want to robustly disrupt something or safely disrupt it into as many small fragments as possible, then we might want to aim for a delta V or deflection velocity greater than 10 times the escape speed. And Brent showed some simulation work that kind of motivates these two general rules of thumb, but it's still not quite a hard edge case in both of these general guidelines. So it's not really necessarily that exactly 10% is what we need to safely deflect it, or something exactly greater than 10 times the escape speed is what we need. And it's more of, this is something that we basically keep pushing every year as something that we're interested in learning more about, is kind of where safe deflection ends and where safe, robust disruption begins. Here at the lab, we do lots of different planetary defense. We look at lots of planetary defense research areas. We have a lot of people who have contributed to some of the DART mission and in creating simulations and doing some prediction work for DART and also for the upcoming Hera mission. I'll be talking mostly about the nuclear mitigation research that we do here at the lab. And then we also have people who are interested in more of the consequence assessment type work, where if we can't deflect it or disrupt it, or if it's too late, or the asteroid's too small, then maybe we're just gonna essentially take the hit and have the asteroid come to the Earth. In which case, if it's really small, then kind of modeling how this object breaks apart throughout the atmosphere is relatively interesting. Or if an asteroid were to come and impact into the ocean, a lot of people have done some modeling in terms of, what kind of tsunami waves would that produce, and how do those waves travel around the planet, and which areas would be most affected, and other interesting things like that. So there's a lot of interesting work that goes on here at the lab that I won't be talking about, and instead just kind of focus for the rest of the talk on the nuclear mitigation option. So just in general, NED stands for nuclear explosive device. NEDs produce energy along different channels, so to speak. But I mostly just want to highlight this slide to say that the overwhelming amount of energy that's released from an NED comes from the form of X-rays. And so something like 70 to 80% of the energy that's released from an NED comes in the form of X-rays. And this is, I just want to highlight this because if we want to think about using an NED to deflect or disrupt, then modeling how X-ray energy kind of couples to the material itself is going to be extremely important to model a mitigation option like that. So how does this even work? So in space, there's no air, and so there's no medium through which something like a shock wave can push the asteroid away. Instead, what happens is we would send a nuclear device out to space. And again, this is all going to take place, if we were to actually do it, extremely far enough away from Earth so that no radiation or fallout poses any kind of risk to the planet or to the satellites around the planet. But let's just assume that we've sent it out. It's really far away. The NED would then go off and again produce a wealth of X-rays isotropically. A lot of them will be illuminating the surface of the asteroid itself. One kind of convenient thing to think about in terms of nuclear mitigation is we can kind of tune how much energy we want to deposit to the asteroid itself based on how far away the NED is when it goes off. And so very close, we can illuminate less surface area, but maybe give it a bigger push. Whereas if it's farther away, we're illuminating more surface area, but the amount of energy per unit surface area is a lot less. And so we might be pushing it a little bit more gently. And so standoff distance allows us to tune the amount of energy that we kind of deposit on the surface. Once all that energy gets deposited to the surface, all this material, X-rays are high energy photons. If the material absorbs them, then it's going to heat up and it's going to melt and potentially vaporize from the surface. And so if the material has enough energy to escape from the local gravitational field of the body, then the asteroid's essentially going to be losing some of its mass. And you can kind of think of it as we have the asteroid and we're kind of vaporizing surface material off. It's kind of acting like its own rocket. And so that's kind of effectively how we would deflect it. Basically vaporized surface material, which causes an equal and opposite kind of reaction in the other direction. And if we wanted to, disrupt it, we would just use a larger device and potentially put it a lot closer so that we can kind of induce a shock wave that goes through the body and cause it to break apart that way. So that's kind of the big picture idea of how nuclear mitigation would work. Actually modeling this is extremely difficult. And you can kind of think of this in two main regimes. On the one hand, we're very interested in getting that X-ray energy deposition correctly. And so to do this, you need simulations that account for how photons are absorbed into some material and how they move around and deposit energy, what I'm going to refer to as radiation hydrodynamic simulations. The main gist is that they're extremely computationally expensive because you need really small length scales and really short time scales for your simulation, which means they take a really long time to run. And then in the other half of the regime, we kind of only care about the body itself. So we mostly want to see what happens to the asteroid after the fact. And so in this sense, we're kind of interested in on these larger scales of the whole body, so tens to hundreds of meters in size. And we want to think about this much later in time. And so there's not really any single computational code that does both halves of this problem well, which makes modeling this extremely difficult. Thankfully, another staff scientist here at the lab, Mary Berkey, has kind of addressed the first half of this problem. So what Mary did was she ran many simulations that do that very computationally expensive part of the problem. So actually modeling how radiation transports through the body. She ran a lot of simulations over lots of different asteroid parameters and NAD parameters, and developed an X-ray energy deposition model.
Hi, quick
Yes.
question, please.
Yes.
Is there any significant deflection force from the detonation as imparted on the object from light pressure, X-ray light pressure? Kind of
Yes.
like light sails sort of an effect.
Yes, I imagine some of that momentum from the photons themselves also would have an effect. I think the actual stronger effect is more so from the material that's getting jettisoned from the surface. So I think it still probably would contribute to a deflection, but I think it's probably a lot less in size. But then this is just kind of my initial kind of guess, because I haven't actually looked at actual numbers, or I haven't looked into this phenomena itself. But I imagine it would have some effect, but it's probably not the primary driver to adding a significant more amount of deflection.
Okay, thank you.
Yeah, no problem. And yeah, feel free to just ask questions throughout the talk if you guys have any. I can't really see the chat, so feel free to jump in. But yeah, so what's really nice about this X-ray energy deposition model that Mary developed is we can use this analytic model in simulations that don't do the computationally expensive radiation transport, and kind of set our initial conditions with this model. And you can kind of think of it as we use this function to add all the energy to the asteroid itself before we even run the simulation. And then we press go, and we're able to just watch that second part where we get to look at the material response. And Mary ran a lot of comparisons, both looking at the differences in the deflection velocities of simulations that account for radiation transport and those that are just kind of initialized with this analytic model, and basically sees agreement in the deflection velocity to less than 10% or so. And so again, it's really nice because you don't have to run as expensive simulations, and you get roughly the same kind of answer. And to do this, we have a code here at the lab called ARIES. And if it means anything to you, it's a hydrodynamic mesh-based kind of simulation that wasn't using any radiation transport. This is an image from one of the simulations where this is kind of a cutout from the asteroid itself, this big gray semicircle. And all this material is material that's above the escape velocity and vaporized from the surface, color-coded by the material velocity. Brent also mentioned earlier that we have an analytic model that was built from another staff scientist, Rob Manigan, and simulations from Mary. They both ran a lot of these ARIES simulations, and very different, I think someone's mic is on a little loud, but they varied lots of different NAD parameters as well as asteroid parameters to generate a function to basically approximate the deflection velocity that an asteroid gets based on whatever parameters you feed it. And again, this is kind of nice because it's just a function. So you just put in parameters, you press enter and it gives you a delta V of what the asteroid would get. And so this was a picture from Rob and Mary's poster over at the Planetary Defense Conference, showing deflection velocity on the y-axis and the NED height of burst on the x-axis. This is for a 100-meter object for an asteroid made of silicon dioxide, which is kind of a rockier type of material, and an NED yield of 1 megaton. And so depending on how close or how far away you set the NED kind of determines the delta V that you kind of expect. But like Brent mentioned, this is this kind of function is mostly beneficial for like a deflection kind of case and less so for a robust disruption case. So yeah, we've heard about the Planetary Defense Conference. Nahum did a nice presentation on that. And again, the goal was kind of to talk about this. The goal of the conference is to have an international exercise where we're able to kind of discuss different mitigation options for a hypothetical asteroid scenario or the consequences of an impact. So there were a lot of really good presentations on kinetic impactor deflection, NED deflection, other methods. If we can't deflect it, you know, how does it break up in the atmosphere, and lots of other interesting planetary defense and astronomy topics were held during the conference. Part of the planning for the conference, we were doing a lot of work to kind of set these scenarios, and I had shown some previous work where for these particular hypothetical asteroids, we were able to deflect them with a single NED for asteroids of different sizes. And initial approximations from this analytic model suggested that we couldn't robustly disrupt the object. But again, this analytic model is just a function. And so what I wanted to test was, can we actually robustly disrupt this by doing some high fidelity robust disruption simulations that account for material damage and strength. So to do this, we have another code here at the lab called Spiral. And if it means anything to you, it's a smooth particle hydrodynamics code. The asteroid is made out of a bunch of particles, so to speak. It's not really part of a mesh. You kind of build things based on a bunch of particles. But again, we're kind of initializing our system at the beginning with this energy deposition function. And then we were able to just press go and watch the material response to the energy. So we want to use Spiral for this because there's been a lot of validation work in terms of the material strength and damage models that we're able to implement for the material itself. And we want to use material and damage models because we're interested in how, you know, rock is essentially breaking apart. And so that's kind of why we want to do this in a code like Spiral. For the conference, I looked at two main things. One of which was, does disruption depend on the NED height of burst? Or basically, again, kind of how far away the NED is. So I looked at two cases where we have an NED at 10 meters versus 25 meters. I also looked at how does disruption depend on the parameters that we're putting into the damage model. So we modeled the object as mostly rocky material. We modeled it as forsterite, but we used damage parameters for material that was harder to damage in a case where we modeled material that's easier to damage. And these are kind of damage viable parameters that were derived from experimental data from actual meteorites, meteorite data. So one of the things that I saw was I ran three 3D simulations.
Excuse me?
Yes.
Hi, I have a quick question.
Yeah.
Is there a way to access the energy that's created from these NEDs?
In what sense do you mean?
So once after impact.
Do you mean so once we I guess
So like
just to
once the NED impacts the asteroid, and then it's almost like what I was picking up was that it's almost like part of it is dissolved or shifted or changed, like the parameters shift. In that energetic shift, how can we access that energy to produce more? Like, how can we access that and not just let it go away?
So I guess maybe a couple of things. The first is we wouldn't actually impact the asteroid with the NED, and instead what happens is we would detonate it above the surface itself. And we kind of want to do that because we want to expose as much of the surface area to all of that energy so that we can kind of vaporize some of the material from the surface. Whereas if we were to actually impact and kind of, I guess, put it below the surface, it would release energy, isotropically, but less of the surface area would be affected, and it would kind of get dampened to some extent. And I think we can give the asteroid a bigger push if we are able to dump more energy over a larger surface area. In terms of getting some of the energy back, it's not necessary. I don't think we would be able to do that. Most of the energy from the NAD, again, it's going to be kind of emitted in all directions. So we're going to be losing some of the energy, for instance, in this direction. A lot of the energy is going to go on the surface and cause some of this material to eject. And then I don't think there would really be a way for us to really kind of capture any of the energy from this ejected material to do anything with. So it's almost kind of like a very impulsive method where it's kind of up very quickly, and then we're just kind of watching what happens afterward. Does that answer your question?
Yeah. Yes, that was actually great. Thank you so much.
Cool. Yeah, no problem.
I have another question.
Yeah.
You're modeling basically on your slide, for example, your silicon dioxide or sort of more solid rock type material. And I'm just curious, and I don't know that this has been addressed all that much in the subject matter today, but in terms of potential comets and not necessarily asteroids that could be an impact or danger. And I'm thinking of something like, for example, the whatever the object was in Tunguska, where it was a massive explosion with, I don't believe it was hardly almost anything recovered in terms of any solid material. I mean, even Chelyabinsk, that was that air burst, there was solid material that was recovered. So that was obviously some solid composition, but perhaps something more of a gaseous frozen gas object that could have been, for example, the Tunguska type object. Has any modeling been done as to how the different reaction would be for this type of deflection with that kind of material, where it's more of a gaseous vaporization of gases and not necessarily solid material, and how that could alter the calculations as to what delta V could be imparted and so forth?
Yeah. So in the sense of, so this is all, so nuclear mitigation is all pretty new, but for Mary's energy deposition model, she did account for, I guess, silicon dioxide and forsterite for the more kind of rockier types of bodies. She developed the model for iron for kind of a more metallic-like composition. And then she did account for, she has a model for pure ice. And obviously, you know, asteroids aren't either pure silicon dioxide, pure forsterite, pure iron, or pure ice, but they kind of give us at least a first kind of a first approximation of what if something was made from, you know, either a rocky, a more metallic, or a more comet-ish like composition. This is as much as we have now, but at the end, I have a slide from another postdoc here at the lab who's working on updating this energy deposition model for kind of combinations of materials. So looking at the opacities and how the opacity of combinations of materials. So for instance, like opacity of some fraction of silicon dioxide with some fraction of ice, how that affects how much stuff gets blown off. And so looking at more realistic compositions is something that's kind of being addressed from other people here at the lab. But I could say that, you know, the blow-off momentum for pure ice, so I guess asteroids that, I guess in our simulations of things that are pure ice are a lot easier to either push or presumably to disrupt, given that the density is so much lower than some of the other materials. So that's as much as I think I could say about that. But I can show, at the very end, I have the slide that shows some of the new work on the more realistic compositions.
Oh, okay, thank you.
Mm-hmm.
I have a comment about the previous, this is Nahum speaking, about the previous question. If you can go back to the slide where you showed the different standoff distances that you showed a moment ago.
This one?
Yeah, so it's different from that, but I think a few years ago, there was a group led by Professor Bong Hui from Iowa University, where he was looking into some hybrid device where a kinetic, I think, device would impact the object physically and create some sort of a crater or something. And then the nuclear device will embed itself into the crater, and most of the energy will be deposited inside the body instead of at some standoff distance. It's different from what you do, but I think it kind of relates to the question from the previous lady. I forgot, I didn't catch her name, but this is where you would capture a lot more of the energy by exploring it inside the body.
Mm-hmm. Yeah, that's true.
I remember Bong Wee, Nahum, and I was thinking of Riley's question too. Given some of the activities of the past few days, it appears to me that if you can deeply bury the device before detonation, it will have some very interesting consequences. One of which is I'm reminded of Edward Teller's Thunderwell project. Are you familiar with that, folks? Where he had a nuclear device deep inside a shaft, hoping to contain it. But the detonation sent the cap in hypervelocity into our cosmos. So there is a possibility that we can contain it. Interesting thought from Riley. Thanks.
Yeah, very interesting.
Carry on, Simon.
What was that?
Carry on.
Ah, okay, cool. Let's see. So yeah, for the conference, I looked at how the different heights of burst and how the different materials affected a disruption. And then, so one of the takeaways is that so I ran 3 total 3D simulations. For the 2 that had the same height of burst but different material, we were getting essentially the same deflection velocity. And again, the different materials is mostly just modeling how they damage, not necessarily material property differences. But for the two types of simulations with the same material, different heights of burst, we're actually seeing that with a smaller height of burst, we're getting a smaller deflection velocity. We think it's because, you know, we're illuminating 40%. We're illuminating about half of the surface area, and we're only depositing, you know, about 60% as much energy compared to the 25-meter run. So we're not depositing as much energy to give it as big of a push, which is interesting. But all three of them had deflection velocities that were well above the 10% rule. So they are going to be disrupting, but they're not necessarily as large as the 10 times v-escape for robust disruption. So we can't really say from this, from the 10 times rule, they're probably not robustly disrupting. But there was other things that we looked at. So in the two simulations with the same height of burst, but different materials, again, the material that's harder to damage shows less damage overall. So maybe that's not as insightful. But for, again, the two, for the same material and two different heights of burst, even though we're depositing 60% as much energy, we're still damaging the object as much as the other simulation. And so the material that's color-coded here is color-coded by the trace of the damage tensor, if that means anything to you. Basically, anything that's not blue is damaged material. And so, yeah, even though we're depositing a lot less energy, we get comparable amounts of damage. And in the 10-meter case, even though it has a smaller deflection velocity, we're actually inducing a much larger crater compared to the 25-meter run. And so even though we're depositing less energy, we're still kind of depositing, I guess the amount of energy per unit surface area is a lot higher in the smaller case. And so we're able to really form larger craters with the smaller heights of burst, which I think is interesting. And then if I just color code the material based on its motion itself. So on the left hand, I'm showing what the X component of the velocity looks like for the material. And so essentially both halves of the object are moving away from each other at over two times the escape speed. The same thing is true in the other direction, so in the VZ, and then lots of material is moving up at extremely high speeds as well. So you can kind of think of this thing as it's essentially like pulling apart from all of this energy deposition initially. So it's, again, we're not really hitting 10 times v-escape, but from all of this material motion, we know this thing's going to disrupt. We just don't know how robust it's going to be. Unfortunately, you know, we would like to run this out so that we get a full, I guess, kind of like fragment population. It's just extremely difficult. So I ran the 10-meter height of burst case for 60 days, and it only got to about 150 milliseconds. And this is over about, 1,700 processors. So it's just a really computationally challenging problem. And these are really kind of the more, state-of-the-art, robust disruption nuclear simulations that are around right now. To get something like a fragment field, we'd probably want to run this out to like a few seconds or maybe a minute. So we're we would have to run this, 10, 100, or 1,000 times longer. But it's just actually, running this on the supercomputers for that long would take a really long time. And so even though, it's kind of state of the art, it still remains a computational challenge to even be able to determine robustness. And so yeah, I think there's still a lot of work to do, and potentially looking at different definitions of how we can define something is robust, that we don't have to run very long, or there has to be some kind of advancements in kind of modeling capabilities to be able to run these to even longer times. Mary did, so Mary was at the Planetary Defense Conference in person. I presented remotely, but she was there in person, and her poster was focused on whether or not we could use Ares to kind of look at asteroid disruption. And she ran a lot of simulations. So this is showing the deflection velocity as a function of asteroid diameter. And if you just focus on the individual points, the circles, those are all individual simulations. And she showed that, most of them with a 10-meter height of burst, 1 megaton NED, are able to hit that 10 times V escape rule. But the main takeaway, or the main caution, is that with Ares, they don't necessarily model material strength or damage. And so they're kind of like over approximations to what disruption would be like. And so it would be like, if you're not modeling strength or damage, essentially, if you were to just push on it, you're kind of already starting to deform the object. So it's, again, kind of an over approximation, but at least gives us an idea of these kinds of simulations in this code. She looked at lots of different things. I might get to some pictures later, but I think one of the interesting things is when you're not accounting for material strength or damage, the depth at which the craters are forming over time are roughly self-similar. And maybe that makes sense if we're not accounting for that kind of pushback from the material itself. But I thought that was kind of interesting. Whereas the shock wave itself kind of tapers off at a certain depth based on how big the object is. And I have a link to her poster here on the bottom for everybody. I can send the slides out later. This is a couple of snapshots of what the disruption of a 50-meter asteroid would look like over time. And with Ares, the Ares simulations are kind of like 2D spherical equivalent simulations. And so you can run these a lot farther out in time compared to the full 3D simulations in Spiral. So she was able to run these out to like 500 milliseconds. I have a couple of movies. This is for the small 50-meter asteroid of what that looks like with a 1 megaton NED at 10 meters. And then the 150-meter object would look something like this. And again, this is kind of, I'm cautioning again, there's no material strength or pushback from the material here. So this is kind of just like the best case scenario. If the object was all fully damaged, this is kind of what a disruption would look like. And it kind of peels away, almost kind of like an onion, I guess. Some comparisons from her Ares simulations to Spiral. We have 2 different comparisons. The top row is for a 50-meter asteroid, and the bottom is for a larger 150-meter object. And again, Ares kind of gets the larger craters forming because there's no material strength. And we see larger craters. We see kind of a larger discrepancy between the two because more massive asteroids, when you account for material strength and damage, are harder to damage or harder to disrupt, I suppose. And then finally, here's a quick slide on what I was talking about earlier in terms of another postdoc here at the lab, Thomas Onyango, was also at the conference, and I have a link to his poster contribution here, where he's looking at different combinations or different fractions of materials. And so in this plot, he shows the blow-off momentum, which is basically just the momentum of the material that's getting blown off of the surface. You can kind of think of that as being close to the deflection velocity. For different fractions of material, where we have 100% ice in this purple line here versus 100% iron on the bottom. And we see that we're able to blow off more stuff in ice type simulations compared to the iron. But when you kind of mix and match different fractions of materials, it's not necessarily like a linear transition between the two, and it's a little bit more complex. Whereas, yeah, he's able to simulate different mixtures of materials and looking at different opacities and how material, I guess, playing around with how material absorbs and re-radiates some of this X-ray energy. So lots of cool things, lots of things to think about in the future, like accounting for actual boulders either on the surface or mixed throughout the body, because all of the simulations that I've shown here have been for a purely large monolithic rock, where we know that's not the case. We know that asteroids have boulders on them. There's a fine grain, surface layer. We don't really know exactly how boulders might be distributed throughout, but they're definitely not big solid chunks of rock. And so doing more realistic shapes and topographies is something that's kind of, in the future. Thinking about, how do we better quantify robust disruption? Is it really 10 times? Is it really a different number, or are there different metrics that aren't even related to the deflection velocity that we can think of to better quantify robust disruption? Is, I think, something that we should be thinking about. And then, is it more efficient to use multiple NADs to blow this up in different ways? I think that'd be an interesting simulation to run. But yeah, I think that's my last slide. So the main takeaways I just want to leave you with are that, asteroid impacts, as we've been learning, are rare, but the consequences, I think, are large enough to where we should continue doing research either with kinetic impactors or with NADs or IBDs, ion beam deflection options. Nuclear mitigation might be the only single mission option if the asteroids are too large. Again, if something's large and you have to send a bunch of kinetic impactors at it, it might be logistically difficult. We can either deflect or disrupt the asteroid robustly, but we don't want to do either mission halfway. And because we can't actually do nuclear deflection or disruption experiments in space, furthering our modeling and simulation capabilities, I think, are a big must for the field. So thank you.
Thank you, fascinating talk, powerful talk, I should say. Let's see if we have any questions. Let's start online first. So we have from Mark and Adrienne. Okay. Adrienne, okay. So Mark,
Sure.
go ahead.
I typed something in, if that's me.
Yeah, Mark, go ahead.
Yeah, so I'll just read it, what I typed in. Somebody answered online also. But I was asking, what are the regulatory hurdles to using a nuclear device for planetary defense from an asteroid or comet? And that's one question. And then, I kind of know some of them, but you probably know more. And can you comment on potential use of an ICBM as an airburst as kind of a last-ditch effort to break up a large impactor, which is, on a trajectory to create a big crater? That would be maybe a comment without a lot of prior warning, so you don't have time to go take other means. And I don't know if you can comment or not, but it's one of those science fiction or movie scenarios that the layman would often ask that question, and it's not a ridiculous question.
Yeah, definitely not ridiculous. I can only speculate So a couple of things. Yeah, we're not. We've stopped the nuclear test. We stopped nuclear testing in 1992. We've also signed that outer space treaty where we're legally not allowed to send NEDs into space. And so those are kind of the hurdles. Then you kind of start to think about, if the threat was big enough and we had to do it, then there's also the logistical troubles of, if we were to make a spacecraft that held it, then who takes ownership of that and who's the one who takes care of it and goes through with the mission. I think there's a lot of, it's classified material. And so getting people to collaborate on classified types of things ends up being very difficult. That's as much as I can kind of speculate. But in terms of like late mitigation with something like an ICBM, I think if the asteroid were that close enough, it would probably already be a problem.
Oh yeah, I'm sure it's a problem. It's just, is it a worse problem? They have to have a scattered, if you have 100-kilometer wide cloud that hits instead of a pinpoint, crater.
Yeah. That's a good question. I'm not sure, but yeah, you're definitely gonna, I guess, spread out the amount of initial damage, I'll say. But yeah, that would be also an interesting simulation front to think about.
Thank you. And I think there is a question from the room here. So a couple of them actually. So let's see.
You had mentioned early in your presentation, much of the energy deposition comes from the X-rays. Do you plan on adding physical experiments? I know there are test facilities within, well, I don't know if it's at Los Alamos or if it's there at Livermore, but conducting irradiation experiments to help back your models. Is that part of your plan?
Yeah, I think that would be really important. In terms of X-rays only, actually Sandia National Lab did an experiment where they exposed a small portion of, I forget exactly the type of material, more rocky material, to what they have is called the Z machine, which is something that produces a lot of X-rays. And they backed out, they extrapolated from their model where they have, so they had, a small chunk of rock, they exposed it to all the X-rays. They were able to actually, cause some vaporization and cause this to move. And they kind of extrapolated out numbers for asteroid sizes. And they claimed that you can deflect a 1-kilometer asteroid with a 1 megaton NED. I think doing a simulation of their actual experiment and kind of validating either our models or new models against that experiment would be interesting. And I think there are other people who are interested in doing X-ray experiments. Neutrons is a whole different thing, and I think it's more of a classified issue, but it definitely would be nice to have more X-ray experiments to kind of validate against.
Thank you. We'll take one more question from the room and then another one from Brent and Adrienne online. So first from the room.
What kind of technology would need to be developed for the kinetic impact devices? Or do we have anything already kind of in play that would facilitate that?
Yeah, so for a kinetic impactor, things like DART, like just generating a spacecraft and sending it on a rocket out into space. I think people, you can either generate a new spacecraft and send it out, or maybe repurpose something that's already out in space to hit it. In terms of with the NED, the nuclear mitigation option, I think we would have to generate new technologies of rockets that can hold single or multiple NADs inside of them to send out, and even generating those spacecrafts, it'd be something new, and it'd have to be a new classified problem as well. But yeah, I think a lot of work would have to be done in actually developing a spacecraft that holds NADs and holds them safely, so that if nothing would happen to them on the launch pad or in travel.
Thank you. And from online, Brent and Adrienne.
Hi, Isaiah. Great presentation, by the way. I have
Thank you.
kind of two questions for you. So have you tested out an iron asteroid model, and do you think that it's more likely to completely disrupt since it's not quite as high in porosity as like rubble piles?
Yeah, so we do have the analytic model does have the option to account for iron in it. And you're right, in iron, a purely iron thing would probably have less porosity than something that's more rocky. The only problem is that iron is a lot more dense. And so when you look at, maybe if I go back to Thomas's slide, when you look at simulations that account for pure iron, the amount of stuff that gets ablated from the surface compared to rocky material is a lot less, because it's so much more dense and it's harder to essentially vaporize. And so it ends up being, I think, harder to deflect or disrupt iron asteroids than rocky or ice type.
Thank you. I think I saw a few comments from Marina that popped up. That was before, unrelated. Okay, so everything's answered. Okay, thank you very much, Isaiah, and very informing and fascinating talk. It generated a lot of interest around the room here. So many thanks for that.
Yeah, thanks for having me.
Thank you for taking the time to present to us. And now we're going to move to Joe Carroll to talk about solar cells. And John, please take it away. He's in the room here with us.
So you have to phone this one. This is the source.
Oh, okay, yeah. Good afternoon.
You want to use
Oh,
this mic?
I don't need it.
But online, they don't.
Okay, online, right, okay. Yeah. Okay. No, real close, okay. I got interested in this subject, well, I gave this is a revision of a talk I gave in 2010 to the University of Maryland group that did the deep impact, okay? And at that point, I was thinking about trying to talk them into thinking about cheaper by the dozen. Now, after thinking about it a lot more, I think that you want to do tests of probably at least a dozen, but with the intent of flying a gross or 144 or some large number, okay? The idea is in the next 10 years, we may know 10 times as many NEOs as we found to date because of the Vera Rubin Observatory and the NEO Surveyor as it flies. There will be many more opportunities to fly things, and the value in understanding them is great. So let me go to the next slide. Okay. Why consider nanosats for NEOs? We have a mission model for planets. Okay, every planet has distinct issues. It's a custom ride to a different delta V. The radiation characteristics, the amount of solar energy, everything's different. So you build a different spacecraft for each one, and it ends up being expensive enough that you fly them every few years if you're lucky. Okay, now Mars is beginning to change that model. They're flying things fairly frequently. But missions to NEOs are different in some important ways. Okay.
Sorry.
Yeah. Okay. Unlike planets, NEOs aren't just resources, but also threats. Here's a Chelyavan's picture. There are already many reachable NEOs, and they have mostly similar mission needs. The distance from the sun doesn't vary much. The radiation doses don't vary very much. We're going to find a lot more, and that means a lot more objects that are easier to get to than the ones that we could get to now. So what might we do with this difference between planetary missions and potential NEO missions? It seems very useful to get data that we can only get locally that will help us interpret data that we get from Earth for future NEOs. So data that you can get from Hubble, Webb, or ground-based telescopes, knowing better how to interpret that so that you can figure out if it's a threat or a resource or both. We need statistical data. We're not going to capture every of the 40,000 NEOs that we found to date, or the 400,000 we may see in 10 years, but we can get statistically useful data. And that's why I'm talking gross rather than dozens. Okay, we have years, the fact that the number of objects that we can find is likely to change just from Vera Rubin, a factor of 5 in the next 10 years, and comparable amounts or maybe even more with the NEO Surveyor. So we've got years to figure out what it is, how to design and test and use a series of satellites that are really optimized for mass production. Okay. Oops.
No.
Nope.
Which one?
Oh, it's, yeah.
You won't, right?
Yeah. I want to go back. Actually, can I control it?
Yeah, sure.
Yeah.
Use the arrow key.
Okay.
Yeah.
So this. Okay. Okay, what are the main design drivers? For small spacecraft, and the further you go, the more this becomes an issue. The comm link is king. The further you go, the less data the harder it is to get data out, and the smaller the spacecraft, the harder it is to do that. And I go into more detail later. Another challenge is NEOs all have different orbits, so they need different rides. Okay, and if you're going to fly 100 or 200 or whatever, you got to fly rides to escape or a bunch of different objects. That's expensive. And then nanosats, if you say they're in the 1 to 10 kilogram range, they can't afford much radiation shielding. And one of the keys is that, in the Apollo missions, most of the radiation data the crew exposed was in going out in less than an hour through most of the radiation belts. Okay, the time they spent on or near the moon was not a problem by comparison to less than an hour coming and going through the radiation belt. So skip the spiral out from Leo to escape, buy a ride that gets you to escape, and then deal with much lower radiation dose. Okay. Okay, how small can a nanosat be? Well, downlink rate and distance drive small spacecraft design. And image data can swamp any downlink. You really have to compress. And when I was doing this, I stumbled across JPEG 2000. It's really beautiful for this. I have a backup slide on that if anybody wants to hear more about it. Smaller satellites have smaller antennas, smaller gain, smaller beam power, and they can't justify big ground stations typically if you don't have a big budget. Even 1 kilogram CubeSats have viable comlinks in low Earth orbit, but at 1 AU, even large satellites can be marginal. And this is the distance part of the story. Is Leo went straight overhead, 400 kilometers away, signal strength of 1. And if it's out near the horizon, about to go down, it's 0.01. Geo, it's 10 to the minus 4th. Moon, 10 to the minus 6th. 1 AU is 10 to the minus 11 signal strength. Okay. Power is a problem. The distance is a problem. Okay, what comm option is better, laser or RF? RF does require far less power, about 20.25 EV per data bit. Laser takes about 100 times as much power. RF receiving antenna area is much cheaper for RF. A 20-meter dish is probably not much more expensive than a 2-meter telescope dish. But the real killer is that you can get laser nanosatellite telescopes to focus the beam into a few arc seconds. And that can give you 50 million times more gain than 1,000 gain that you might with a nanosat deployable RF antenna. So 100 one way, 100 another way, but 50 million strength to advantage on beam focusing. The problem is that you have to aim the beam very precisely. Now, there's another wild card in this, which is a telescope is a more useful thing for other purposes than downlink than an RF link. You can do interesting RF science more for planets than for asteroids. But a comm telescope, if you're smuggling it in as your comm link, may be quite useful. Okay, and what can a nanosat telescopes do? The laser beam can be 1,000 times brighter than the sun brightness of a 100-meter neon. So you can see these things accurately from much further out. So you can get better orbits and better orbit predictions with this than you can with others. Laser pulses can also allow extremely good precise ranging. And if you see the object spinning in a certain way, and especially if you have some thermal sensors, you can figure out the Yarkovsky effect on the orbit, which, as I understand it now, typically you can't do decent predictions more than 100 years. With Yarkovsky acceleration included, you should be able to do much better than that. A telescope that can have a way of splitting the different parts of the spectrum into different things you can include some hyperspectral imaging data that tells you a lot about materials. This may be more of interest to resources, but also to figuring out what kind of characteristics the material has that it may affect a diversion problem. JPEG 2000, there's actually been work on this that you take the JPEG 2000 compressed data and run it through something that allows you to do terrain classification. And they found it's something like 96% efficient terrain classification using just the processed compressed data. Okay, that seems really powerful. There's another thing about JPEG 2000, which is you can do iterative download where you get the thumbnail and you say, I want to just see the top left corner of that in more detail. The total increase in data to get it in pieces is just the command. The data is processed in a way where you can say, I want more resolution or full resolution of this part of the image. And so once you get the thumbnail, you've got something you can say, well, if you're downlink, down limited, just select the parts of the image that you're interested in. You can also do flybys en route. And if you're doing this with a solar sail and you can't aim very well until you throw the sail away, you can do flyby and then keep the data until you get to the final destination, throw the sail, release the sail, and then you can point accurately to download the data from the flyby as well as the final destination. And then you can map the gravity field if you throw some retroreflectors. And when you can't, like if you're halfway around the sun from the Earth and you can't talk, you can do other things during that time. Okay, let's see. How to fly to 100 NEOs without buying 100 launches. That's missing from the top here. Each nanosat needs a high delta V, and you can get it with solar sailing or ion thrust, or you can do something else, which is get to escape and then build up some delta V that allows you to come back and do an Earth gravity assist, okay? And in the days before you come back for your pass, Earth can tell you where you missed the Earth. You move to that to get the best gravity assist for anything that's been recently found near Earth, and it's of interest to send you to go, okay? So the idea is using solar sailing or ion thrust, the kind of delta V that you can get using an Earth close to Earth gravity assist is 6 to 7 kilometers a second, okay? The solar sail design that I think is reasonable can get you about 7 kilometers a second per year. An ion thruster, you probably, after 10 kilometers a second, it takes too much propellant to want to do more than that. But the point is that if you combine solar sailing or ion thrust with possibly repeated Earth gravity assist, you can get all sorts of changes in your orbit to pump out of the ecliptic to get to objects that are harder to get to.
Yeah.
Solar sailing. Spinning disk designs, there are the most common thing that's flown has a truss structure that gets out to the corners of a square sail. The truss structure is most of the complexity and most of the mass and most of the failure modes. I really like centrifugal force, okay. You still do need some rigid structure, but it's just that part of a hub and something to offset so that you can move around to cause a torque that causes you to sail in the direction that you want. Okay, gory details TBD. But the delta V with a 2.5 micron sail, I actually have enough material, 1.2 micron polyethylene naphthalate, which is kind of in between Mylar and Kapton in terms of properties. I've got a 1.2 micron film, but I happen to get it, and I'm not sure that they're actually making that film in that thickness anymore. But with 2.5, there are several materials that you can get Kapton, you can get Mylar, you can get pen film at 2.5 microns. And that's 5 grams per meter with joining and with the coatings. A 300 square meter sail might add 2 kilograms to a 2 kilogram telescope. You assemble it pre-folded, and the delta V that you should be able to get from that is about 7 kilometers per second per year. You combine that with Earth or other gravity assist, you can get a lot of delta V to get to anything interesting. Now, if the solar sail development ends up being too challenging, try it with an ion thruster. There are many ion thrusters out there, but they tend to be in the hundreds of millinewtons or more, or in the micronewton range. And really, we need something that's of order 1 millinewton thrust. Okay. And that would take 20 or 50 watts of power, and that would end up perhaps weighing more than this. Okay, a little bit more on solar sail properties. The force that you get it's a reflection. Now, there are some gory details that you may absorb 10% of the light, and then most of that is reflected or emitted on the infrared in the backside. You'll get a little bit of 1% diffuse, but it's good approximation, and you get a force that's almost identical to normal to the local sail. Well, if you're facing the sun, that gives you the maximum force blowing you out and changing your orbit time at any given distance from the sun, because you're partly counteracting the sun's gravity, and so it changes your orbit in a weird way. Okay, the punchline. But as you tilt to an angle, you get this side force that's maximized at about 35 degrees tilt away from the sun. And that's what gives you the 7 kilometers per second per year. And by changing the direction of the tilt, you can get a tangential force in any direction. Okay. There are constraints. When you get further from the sun, the force is less. If you get close to the sun, the sail may overheat. But you can probably get down to about Mercury's distance. And this is puzzling and frustrating. The thrust is always on. You can't turn it off. You can turn almost edge one, but there are some subtleties that make that perhaps a difficult thing to recover from. So my thinking is you use this to get to the orbit of the NEO and then throw the sail away. Okay. And one variant on that that's gutsier is to use that to deliver a sample collector to the NEO. And then you throw the sail away, the sample collector gets its sample, kicks itself off, and deploys a new solar sail to go back home. Okay. There's a tendency to think of solar sails as very expensive things that will live forever. But there are times when you want to think of it as more like a Kleenex. You use one, then you use another one later in the mission. Okay, possible additions to a NEO-nanosat survey. As reliability grows, you can invest in more challenging scenarios than just getting there, taking pictures, and sending them back. If you find 10 times as many NEOs, there are 100 times as many flyby chances. So on the way to somewhere that you're gonna hover and take pictures for a long time, you can do a strafing run by another one and get some good pictures. You could release tiny impactors, fly by one side and get impact images. The real question for this is, to me, if a NEO is possibly a dead, like coated over with dust, dead comet, small impactors may cause much more explosive impact results than if you're hitting just a rocky object. But I don't know if there are other ways to get to answer that data that's better than throwing small impactors. Release a tiny lander and serve as its relay from Earth. And then landers can get samples, leave, deploy a new sail, and come home. So these are things to do after you found the basic mission protocol, design, operations, software. Then you can try these as more challenging things. So key questions for NEO-scientists: what spectral regions should nanosats focus on? I recall somebody at Goddard saying you want to get out to at least 2.5 microns. Basically, the tail end of the solar illumination spectrum. What other small sensors and kinds of data should be considered? Okay, I'm not an expert in this area. What else can improve surveys of Earth protection and resources? I don't know. If you regard this as an attempt to take a downlink telescope and turn it into a useful spacecraft, that's what I'm trying to do here. Okay. Now there are more questions for development engineers. What's the best size? If it's too small, you can't pack enough avionics and controls, and you may not be able to point the downlink laser accurately enough to get enough data. How useful can Earth gravity assist sails and other gravity assists be? How well can we downlink the laser while solar sailing? That is a perturbation on the spacecraft that makes it harder to sell. But on the other hand, it's roughly 1 millinewton force on the telescope itself, because it's roughly 2 newtons, 2 millinewtons total, but half of that is thrusting the sail, and the other half is pulling the payload. What other gotchas occur? In the telescope, the sail, or other thruster, and the operating concepts. And here's an interesting one. If you learn how to do spinning disk solar sails, you can scale them up. How many of you are familiar with the concept of a gravity tractor?
Yep.
Okay. That's typically regarded as something that you do with a large nuclear electric or solar electric high thrust ion system. And you have to have a lot of mass in that system so that it can hover near the asteroid and fight against its gravity and pull the thing in a non-contact way. Well, if you use a large solar sail and the place you're going to has large rocks on the surface, You can get there quickly without any mass, payload mass, pick up rocks and use that combination as a gravity tractor. Key conclusions. A few nanosats won't make sense. It'll take too much money developing suitable ones to justify themselves. But if you are considering wanting to do 100 to get statistically useful, more thoroughly statistically valid and useful data than we can with larger spacecraft that cost more, 100 is money. And for exploration at low cost, the comlink is king. Get used to it. Okay. Design the spacecraft based on the comlink, minimal comlink, and then see what else you can do with it without adding too much. And plan on several iterations of tests on the ground and in LEO before you try to go to escape. And remember, we have lots of things that we could chase now, but we're going to have 10 times more maybe in 10 years. So you can spend some time working on this. Most of the design may be straightforward, but there are some key challenges. Finding a small NEO if you don't start chasing it soon enough. Okay. Aiming the laser precisely when the aim is perturbed by the solar sail. And the software. The small doesn't necessarily mean simple. Okay, or cheap or reliable. Relevant missions, imaging, orbit refinement, diversion planning, release micro impacts and watch impacts, prospect on regularly accessible bodies. There are things that come by once, very close, and then don't come back for 50 years. Those won't be as interesting as prospecting candidates as things that come by every few years, where you've got a delta V capability that's reasonable to go get there, survey it, go back on the next pass, collect stuff, and then the next pass again, you bring your booty home. So that's it. I'm 77 years old. I'm retired 99%. But this, I think, needs to be considered as something that's a way to get different kinds of data on many more NEOs more affordably than with larger spacecraft. Questions?
Do you see the use of the higher frequency transmitters as being key? If power is going to be your... Yeah. Do you see the higher frequency transmitters being key if you're going to go with a nanosat with a power budget that's necessarily limited?
The laser option with a telescope, the fact that you can crowd the beam into a very small, 50 billionth of the steradian, 12 steradians, you can get more data to Earth with less power than with anything with radio.
So you can point.
If you can point, and you have to point, and there are issues, but I think that for example, Planet Labs knows how to point 3U CubeSats accurately so that they get paths. Now, that's in Earth orbit, in low Earth orbit, and that magnetic fields are wonderful in low Earth orbit. Once you get out of Earth orbit into the sun, it's 50,000 times less. And in fact, some of these pictures, okay, you need flaps at both ends because the main torque on when you're in solar orbit is the solar torques from offset masses compared to where the area is that's shining. And the difference between a black surface and a reflective surface. You then end up needing to take advantage of the solar torch because it's the only beam in town other than thrusters or wheels, spinning wheels. Yeah.
That's the problem with nanostats is many of them don't even have propulsion systems, and many of them have very low reliability wheels.
Well,
which is being kind.
CubeSats get you to orbit cheaper, but that doesn't help you if your satellite doesn't work. And the question is, are you lucky this year? Is this team lucky and good this year? And, you know, JPL and other NASA centers believe in nines. The CubeSat world seems to believe in 3 or 4 is a good number, you know. But these things can be solved, but you have to solve them and solve them right. And my own experience is iteration is wonderful. If you can test something and refine it, you'll eventually know what you're doing. Okay.
Well, the Marco CubeSats that followed the InSight mission to Mars were fairly reliable, and they functioned perfectly well all the way out to Mars, pretty close to 1 AU. So if designed properly, these things can be quite reliable, and that was demonstrated in that mission.
Yeah. The question is that if you don't have much of a budget, most CubeSats don't, they're CubeSats because they don't have a budget to fly something more expensive. And if they don't have a budget, and especially if they're training students, that's a problem, but you can do small sats very well.
Under the right conditions.
Under the right conditions.
Challenge.
With a little bit of luck even there. Okay. Yes.
Hey, Joe, can you hear me?
Yeah.
Yeah, it's Mark Henley. If I knew you were there in person, I would have driven in.
Okay.
Yeah, I thought your presentation was very interesting. Hope to get a copy. You know, I think there's a lot of there's a lot of fertile ground to you know, figure things out for this, probably the biggest nanosat ever conceived in size. You know, I think of all sorts of different options and questions, and I can't get to them all. But I guess one of them would be: have you considered using something like a Fresnel reflector to be able to focus the beam and use that as to focus the sunlight, as opposed to just reflecting it? And that, you know, might be to illuminate the object that you're looking at, or to, you know.
I've heard of diffractive solar sails, but I don't understand what they're trying to do with it. Reflective sails are probably as much as you can get with a small amount of material of a few microns of plastic and fraction of a micron of aluminum and chrome.
Yeah. Or aluminum.
Yeah.
All right. Well, I hope to talk later. Thanks.
Nahum here.
Yeah, it's Marina Brozovic, JPL. So, yeah, I mean, the technology you're talking about is nowhere near available at the moment.
Can you be a little louder, please?
Yes, so I'm saying the technology that's being discussed here is really nowhere near being a reality. So I just have kind of a few comments. Well, first of all, there was a JPL had a mission called NEO Scout, and it was a solar sail. It was a 6-unit CubeSat plus 85-meter solar sail, which was unfortunately not successful. So another thing is also what you're assuming is that all these asteroids have perfectly known orbits. And, you know, they have, even when they are quite well observed, you're going to have substantial orbital uncertainties, and you're going to depend on either something like your own op-nav, but you will at best be able to do some kind of flyby with a solar sail, and I'm not sure that going into an orbit around rendezvous missions are very expensive.
Let me break in. I used to try to figure out how to orbit a small NEO, and then I realized, no, you throw the sail away and you loiter around it. You're not really orbiting in any, the problem you may have is more the solar pressure is blowing you away faster than the NEO. And so you have to kind of run in place to try and stay near it. But I think it's feasible if you can find it and the trajectory is reasonable where you can come up and throw the sail away where there's just a few meters a second delta V that you can do with cold gas. I think that you can stay with it for quite a while.
Interesting.
But the key issue is if you have recently found something when it's nearby Earth, and you're tasking the next solar sail that's coming by after a solar sail pumping, you have to be able to find it or chase it soon enough that you can keep it in your field of view.
So you have some kind of op-nav. You have some telescopes.
Oh, the telescope itself and wide angle cameras and medium angle cameras. I mean, cameras can be, under 1 cc.
Yeah, very small.
And there's no reason to not have a dozen cameras on something that's this big.
Okay, I think we have to move to our last speaker. Thank you, Joe. Sounds like there's a little bit more to be studied about this.
Oh, yeah, I mean, I'm not trying to get funding for this. I'm trying to get somebody else to consider doing.
Yeah.
Thank you.
Thank you, Joe. And now we are going to move on to our last speaker, Madhu, who is online. And let's see, Madhu, can you hear us?
Yes, I can hear you well, Nahum.
Okay, Ken is setting up the presentation. Are you okay? Yeah, because we haven't seen it.
That's his screen. You already opened the screen.
Oh, okay. So we are showing your screen. I guess.
Oh, great. Okay. First of all, thank you for squeezing me in to this Planetary Defense conference, Nahum and Ken. I think from at least the few presentations I saw, we have a lot of ammo going into the next year and the year after. And it was a pleasure to listen to Brent and Marina, and the comments are always very interesting.
So Madhu, hold on just 1 second. Are you going to present something, or is it Ken? Because what you're seeing is just the desktop.
Is just the desktop is all right? Okay, let me see. Share screening. Share. Any better?
It's a little bit better, yes.
Hold on.
Put it into presentation mode, it will be fantastic.
Yeah,
perfect. Perfect. Carry on.
Okay, good. All right, so let me see. Is it moving?
Yeah.
Oh, great.
You're good to go.
All right. So now I am very interested in the way planetary defense has moved in our community, in particular, and globally. And you may know that all of these things has had its beginnings in California. The policies, alas, were more in the congressional domain where the first questions were, can you do a survey to know how many of these objects are out there? And I think several of you addressed that, and Marina too. And it's a double-edged sword because we follow the congressional recommendations, and there is very little done in the arena of mitigation or avoidance of such a situation. But anyway, this talk is about the moon and how it may be related to what we are doing, and some technologies that may already be rearing its face in other theaters. But anyway, now I come from the University of Southern California, where I have a foot in two schools. My background is in engineering and architecture, as in civil architecture. And Neil Armstrong, you see in the slide, graduated from our school while he was given charge of commanding the Apollo 11 mission. So that is his thesis that you see over there. So we have a larger than life figure of Neil Armstrong, and students come into our school from various corners. My class is in the evenings, and the class is very simple. Imagine an idea, present it to your classmates, present it to the world, and if you're good, maybe send it to a conference, get it peer reviewed, and publish it. And we've been running this for many years. And here you see a group from, I think, University College London, and they came in for a talk. And so these are the things that we do in the class. So whenever they ask me a very hard question, I go to Neil, and he has never given me an answer. But it's a very interesting sculpture we have of him. He resembles the exact same figure we saw when he delivered the commencement speech at USC, which you can pull up on in Google. Just say USC commencement speech, I think 2005, and he says something that's very interesting. Our job is not to worry about inventing something, but to look out all around you to see how you can nurture and how you can support things that are happening to catch on fire. That is the engineer's response. It is not the scientist's response, but the engineer's idea is to help the scientist, to help the public in endeavors that they think are critical to not only our survival, but to our progress. So USC has a program like so, which is gaining steam, and Mike Gruntman tolerates me, and he's the professor. He has a wonderful paper out on Neil Armstrong that was published last year. All of you may like to read it. It traces his history at USC. And for 1 second, if you have your cell phones, go into our studio archives. Yesterday, Jairo, who runs the distance education program, tells me that it's been updated. So take a look at it and see, go on the QR code and click if you have your cell phone, and it'll zoom you right into our archives. And the last team project from spring just went on air, and it's called Time, because this is the term time is an acronym in our last studio. It stands for the immediate moon expeditions. And you may enjoy some of that because it kind of resonates with the agency and the industry happenings right now. So in the other semester, I go into the jaws of the real civil architects who wonder what kind of stunt are we pulling among the global population, talking about space and so on, when there are 8.5 billion people on Earth who really need to know what we can do to support them. So here's my studio. You look at in all universities, you find this. the people come from all over the world. You have French, you have Italians, you have Iranians, the whole world, China, they're all in the classroom. Turkey, they're all here and asking the same questions about our future. So space community, which is all of you in the seats there. I saw a piece of you guys when Ken zoomed the camera on you guys. Space community looks upward and outwards with questions, while most of humanity looks downward and earthward for solutions to things happening right now. And that's what the United Nations is also thinking about. We like to think that space has a lot to offer, space activities. Which brings me to our talk. So I made some slides. Again, school runs throughout the year, and I try to take little gaps off and try to run to places to present. And I was hoping to go to the South African meeting, and it just could not work it. Anyhow, this was our class, and people listened to all the blasphemy that we proposed, and it's been growing by the it's a year-round program, and there we have an audience from all over the world. So this is the wonderful slides I made for Nahum. I apologize I couldn't do it because class was running late. Students will never do their work on time, and we had to cancel so many appointments to get there. But I hope all of you, I know that some of you went to the conference, and I'm sorry I missed Nahum's talk in the morning, but I'm sure I'll be looking over the archives that Ken makes. So the moon, we think of the Earth as separate from the moon, folks, and nothing could be, it could not be so, because the Earth-Moon system, and it's appearing more and more in our literature now, that we cannot discount the moon in the situations that we are going to be faced with on Earth. Of course, in biology, we have known that for a long time, but in the planetary defense arena too, I think the moon will play a tremendous role. It has played a tremendous role. If you look at the backside of the moon, you'll see things that could have hammered us, but our moon took care of us and our evolution. So why do we think this is the case? Because in the past, just the past few years, we got this wise idea that if we looked at the moon and saw watched out for it, maybe we'll see meteorite and micrometeorite strikes. And lo and behold, this is true. But again, our visual sensors are not up to the mark in terms of what it can do. But the fact remains that if you have a large impactor hitting the moon, it can mess up what we call the cislunar domain. And more talks are coming up in that arena of interest. So if you are not engaged in artificial intelligence, you have not missed the train yet. I hope that you will go query some of the beautiful AI algorithms to see how AI thinks about the situation. And in this, I will spend a little more time talking about when I asked AI about what would happen if we got impacted by an asteroid on the moon. So in cislunar space, debris anywhere, I mean, talking natural debris, not just what we generate in Earth orbit, but anywhere. Debris anywhere is a hazard everywhere. And we're going to see this more and more as we extend our travel, particularly human spaceflight missions, out into space. I know Henry Garrett is online, and he probably he's one of his good lectures I've listened to on debris. And to all of you, go on YouTube and pick up those slides. Now, some of these ideas are in our moon book, which is seeing a serious revision this term. You must go pick this up. It's on Amazon. It talks about planetary defense as well. And I hope you take a look at it to see what we've been thinking about. Several ideas about what we can do on the moon and so on are there. But in terms of the term low sol, the line of sight, speed of light, threat mitigation strategies, they're pretty similar to what we have studied in the past. I think there was a term called Odin before, but now we know that, I hate to say this, but, in weaponeering, it's a term that they use in the defense establishment. And there are certain sequences in which you identify the threat, whether it is a friend or foe, and continue on the line. It's very similar in civilian aspects too. You got surveillance, observation, detection, characterization is critical, early warning, alert systems. All these things happened in the last few days. And JEDI stands for Joint Earth Defense Infrastructure. Earth Moon Defense Infrastructure. I dropped off the M in there. And the critical thing is to avoid the catastrophe that can happen otherwise, folks. So line of sight mitigation at the speed of light is not very old. People started paying attention a few years ago. I had a I had a article on it on Space News that's been embargoed, and we don't know why, but I'm happy to send it to you. They are as old as mythology. I mean, if you look at stories in the past, you will see that light, intense beams of light, have been a part of warfighting technologies long in the past, all the way to Hindu mythology, and then in the Greek mythology, and then Archimedes comes along and does something with directed energy of light. Anyhow, all these are stories, but so to get to the point, what would happen if you detect a meteor shower coming at you and getting into the lunar infrastructure with high value assets? So assume that you have something coming at 30,000 kilometers per hour on a terminal trajectory that you've noted, and then you have a module that is integrated into the value structure. So in general, you have the capability to evolve a space situational awareness network that is already evolving. I mean, it's not a new thing. And so there's a new agent in town. It's called AI agent, artificial intelligence. And what we can do with that is we can do all of those, the lineup of activities leading to taking out the aggressor in very short time compared to human activities. And this is a slide that I think is our, the Planetary Defense mini conference put up, and it tells you the activities that go on, and every one of these listed items are enhanced by a factor of 100,000 by the AI agents that we possess today, not tomorrow, but right now. And now these are images you will find in our book about how we would use high energy lasers to mitigate in extremely short distances, because if you looked at the optical physics, you will quickly discern that we can't throw out beams of light very far because of Gaussian losses and so on. But AI is so quick that we can take these out very close to impact. I mean, it's like you escape with the skin of your teeth, but not for the AI. They can protect you. And here you see the image. When I asked AI to show me a meteor shower coming towards a selected high value asset, it gave me this image. And then I put on those lasers, and lo and behold, it shot back at me with these streaks coming off the meteorite shower. And I wondered why. And it's clear that what you're looking at is a high power laser beam impacting some small meteorites, and it blazed on probably a carbonaceous chondrite for all you know, and that's why those streaks appear further down coming to the impact. And to think about this, AI generative visuals are getting very, very spiffy. This is from a earlier work that tells you that at some point in time, we will have to study how to gauge these emergency threat level gates. This is very schematic, but I suspect we'll have to study them. And for the moon, this is how I would think about it. Now, if you're looking at 3,600, 36,000 kilometers away from target, you'll have about 10 hours, let's say. And that's because we are looking at 3,600 as the divisor here. So you can detect something and paint it very clearly using optical technologies at around 10 hours from impact. And about 1 hour from impact, you would arm your system. And then between 1 minute and less than maybe 30 seconds, you would have taken out a shower. I mean, these are the things that are coming online as we speak, folks. And some of these images are real. Of course, everybody wants to know whether it's open loop or closed loop. And all of you have done a little bit of control system, so you know how it works. And, and this here is Sanskrit. It says Hindi. So people are aware how open loops and closed loops work. And once you assign a closed loop system to an AI agent, it will take care of you. Now, in the last term, I mean, in the spring term, this was posed by a student about, wait a minute, but what if AI starts to hallucinate and cause trouble for you? So we introduced the idea of human in the loop for particularly, this was the debate was about what do you do the International Space Station? Can you assign AI to International Space Station operations? And we thought, yes, we can, but to be sure, we would include humans in the loop. So here are some images that show you what we could do while going for, taking out meteorites. And you'll see these in our papers or in the books. There are several several planetary defense projects that we addressed in our archives. And you can take a look at those. I mean, Ivan Becky and others have talked about several ideas of using directed energy beams to not only paint and visually, a target, but also to neutralize these problems. And I hope Philip Lubin comes to talk to us because he's one of those folks who has worked on directed energy. Our class has done some work, and these are some of the technologies that you can ponder. Thin disk laser technologies everywhere, folks, and very, very useful, highly efficient. So what are the difficulties with this? High power lasers are all over the industry now, and we expect this to move on to other things, particularly planetary defense. What are the difficulties? I mean, they have very large energy storage facilities that are needed, and but they're already working in various arenas. And so watch out to see what we can do in the coming 10 years. We can see planetary defense take a new angle. LOSOL, that is line of sight attack in the last few minutes. Scary as it sounds, we can do a lot. Maybe not for the very big asteroids and stuff that you guys talked about. The Moon Village has a problem as a project associated with planetary defense. What happens if you cannot do anything? I mean, disaster. I can't even imagine how terrible things could go. And think about the challenges and merits and challenges. Some review materials. It's a beautiful story that is told. And because of its roots in California, I have nothing more to add except to say that, we've been thinking. And some food for thought. Asteroid Day is coming very soon. And, I always think about what is more important to learn, probability and statistics or differential equations and calculus. I always favored statistics because probability, if you master it, not only can you make well in a place like Las Vegas, but also you can do many things on Earth. So Nate Silver, the baseball analyst who also did some very interesting things in the election, says we need to stop and admit it. We have a prediction problem. We love to predict things and we aren't very good at it, right? So there's another part in his book which says, in the signal and the there is a tendency in our planning to confuse the unfamiliar with the improbable. The contingency we have not considered seriously looks strange, and what looks strange is thought to be improbable. What is improbable need not be considered seriously. It's happening every single time with weather, with rescue systems, with recovery systems. We have to improve in that area. Thank you very much, folks. I'm happy to take any questions if I have any time left. Let's go.
Okay. Any questions online or from the room?
They're all pondering, Nahum. That's good. Please.
Madhu, very fascinating as always.
I truly wish I was with all of you there because we had great plans. That Culver City is a place where there's a lot of good restaurants from the cultural part of India where I hail from. And I wanted to take you all out and have dinner, but we're going to do this another time. No.
Yes, we should get together pretty soon. Let's see, in the Q&A, I see a couple of outstanding Q&As. Is still questions?
No, that's an earlier question.
Oh, earlier.
Oh, there's a question. Let me see.
That's for the morning.
These are questions that were left over for the morning.
I have a question actually.
Okay. Who's speaking?
This is Adrienne. Hi.
Yes, Adrienne, go for it. And before your question, let me tell you what I think about optical comm. I know that you raised a question about or a comment about clouds in the sky. Now, I was in a group when the Galileo mission was launched. And this was a question that was bothering them at JPL. Will cloud cover mess up the link? You know what? They flew, and I think it was a couple of million miles away that they turned on the payload. And there were clouds in parts of Southern California, but they were quickly able to resolve it because you have, right now we have hundreds of optical terminals, but at that time, they were able to grab the signal quickly out from Northern California. So the idea that clouds would cover is old and it kind of ages us, but good. Please go on. Question.
You said Galileo, but I think you meant the LISA spacecraft, right?
No, I think the GoPex experiment that was flown on Galileo a long time ago, I think. Yeah.
Well, there's a current mission that's using light comms that's being quite successful. But I'm sure if you have dense enough overcast, I mean, if it's a brief spotty clouds, and you can find an open, and as you said, because of the high data rate, just a brief exposure might give you the data length that you need.
And also take a look at papers. I think there's one out of China at least, and that says that they've solved the situation in a more direct way, and I need to reevaluate. But please go on.
Well, again, actually, my question is sort of tangentially related to the whole aspect of the laser comms, and that is the transmission of a high energy laser through the atmosphere, and the fact that that high intensity laser ionizes the air, causes a plasma, which severely impacts the transmission of the laser. And so my point again, you're mentioning this defense system. And so I would imagine that it would be really important to have it on the moon without an atmospheric interference, and that would be much more efficient system if you're trying to use high intensity lasers for deflection or ablation of incoming asteroids or meteorites that you would want to sort of control. So
you're absolutely right. And
so that was my question.
Yep, I think the moon, because of the vacuum, is far suited for this technology than it is now. But we are solving. I know there are some astronomers. Are you an astronomer, Adrienne? Because
not optical.
Yeah,
I'm actually an amateur radio astronomer.
Oh, great! I mean, adaptive optics have taken some very good strides on how we can hold a beam together and keep that collimation. And again, I think I made it very clear, and Nahum has been working this as well. We separate these activities into long-term mitigation strategies versus short-term and quick fuse reaction time tactics. And this kind of activity, directed energy, falls directly in the camp of short period and short warning mitigation strategies. And if I remember, I think it was Isaiah, pointed out how energy, when you impact an object, how it reacts. And I think there's a lot more work to be done in that area, how you impact it and so on. And Phil Lubin has done some very interesting studies. I think you want to look at D-Star. Again, it's all published material at the University of California, Santa Barbara. Thank you. You pointed out the right thing, and that is lasers can do magic in vacuum a lot more than in our atmosphere.
Well, thank you. That was a very interesting presentation. I enjoyed that. Thank you.
Thank you.
Thank you, Madhu and Adrienne. Are there any comments or questions online or in the room about anything? We are just about to be kicked out from the room in just a few minutes.
Nahum, I want to thank you, and I want to thank this wonderful man. Can you put the camera on Ken? Because I do not know.
Ken, what did you just?
I really do not know how he propels himself to do these kinds of things. But he is a treasure in the AIAA, keeping us all abreast of all the wicked things we do and keeping us in check and doing, just today, I turned on my old PC and it was hard to come on, and he kept doing some magic to get us connected. And thank you very much, Ken, and keep up the good work.
Thank you.
Thank you, Madhu. I would say that to me, a key advantage of those mini conferences is that we bring top experts.
Yeah.
Those people were at the conference just a month ago, and they were given 8 minutes to talk.
That's right.
Before you wrap your head around what they're trying to say, it's over, and the next speaker is already out. In order to fit as many talks as possible into those 5 days. Whereas here, we bring 6 or 7 people who have half an hour to an hour to talk, and you understand what they're saying, you grasp, you have time for questions. I think that's a huge value of this mini conference here. So again, I think, Madhu, I second what your words is that everything is thanks to Ken. Because Ken works months in advance to organize those events and line up those speakers and
It does.
arrange for the library or the book and so on and so forth. So he's really a planetary defender in his heart.
And I want to say hello to Joe Carroll, my good friend of many years.
Hey!
Hello.
And,
I
I truly wish I could have been with you, Joe, but I'm stuck here under doctor's orders, and I don't want to infect anybody. And John, I think Mark Henley, I saw him at ISDC. He had something to say. Mark, did you have something to say?
Sure. Can you hear me?
Yeah.
I did. I presented a bunch of charts at ISDC that were also interesting, and there's no time for them now.
Well, you can send it to Ken, and he can probably add it to the archives if it works. But
yeah, I did. Ken's got it. But I think there were several things that I can comment on for ISDC. And from
you
that
got to be fast because we're going to get kicked out, right?
I know it. I know. Well, so I'll just comment that one of them is that that climate change is a big deal, and it's both a big deal. That climate change is essentially the result. Well, it is what decimates the populations of Earth after a major impact, for example. And looking back in the historical record, geological record, it looks like the Earth has had rings of dust in the past. So and it's likely from meteor impacts, major bolide impacts.
Something that Carl Sagan describes as nuclear winter.
Yes, it's kind of like a nuclear winter. Yeah, and in some cases, it's caused perhaps ice ages to be created. Yeah. The other side of that is that when I look at the scale of global warming, and I put it on one chart on the there's this Torino impact scale that is used to describe the severity of impact versus the probability of impact, and the impact of climate change so far.
Right.
It's just the 1 degree or 1.5 degrees C. For 1 degree, it's somewhere between. It's in the 9 category. It's almost in the 10 category. The most severe impact as far as the amount of energy that's input into the Earth.
Mark, we got to close up, but
yeah,
I think. But I'm glad you sent the slides in, and Nahum may like to say something.
Yeah, he's got to wrap up. But thank you, everybody, and especially both you and Joe. It would be great to see you. Sorry, we can't do that.
Thank you all.
Well, I think thank you, everyone. We were planning to do a little wrap up, but I think we are really running out of time. So I want to thank those that are still online. Would love to get feedback from you about the day, if you learned something new, if you have suggestions for improvements. We are trying to hold an event like this every year. So we did it this year. And so
Nahum, hope we send this recording to Bill Ayler and to Chodas and to the folks that are part of your Planetary Defense Mafia.
Yeah, I think that Ken can simply provide the link and everybody can go to the website for the AIAA and see the whole presentation today. It's all recorded, right?
Yeah. Oh, one question, is it marked up? Or any no.
Okay. So I think, we can just wrap up by saying thank you to everyone. I was planning to do a little exercise, but most of the people here already left, and I think they're going to tell us too. Ken, by the way, is already all packed up, ready to go because he's come and tell us to leave home in just like 5 minutes. So I think with that, I'd like to thank everyone. It was an amazing day. I learned so many things myself, even though I've been with this area for 20 years. And I'm sure that because we are local, Madhu, once you get back in shape, we are going to plan to get together at one of those Carroll restaurants.
Let's do this.
Let's do that. But for today, I think we are wrapped up. Thank you, everyone, and safe world.
Yeah.
Thank you, and all of you have a good evening, guys. And thank you again to Ken for keeping us all in line. Thank you all.
Something to so we have a couple of people here who stayed the entire day and took some notes I saw and learned a lot. That's amazing. So I hope that we're able to inspire some young people that were here earlier. And I know that at least a couple of people told me they're going to contact me about additional activities. And that's the purpose of those meetings, right? We meet here in order to network and connect some dots and continue the discussion. And hopefully we'll get together soon.
Where is the next planetary defense meeting, Nahum?
Sorry, what was your question?
Where is the next planetary defense IAA planetary defense meeting?
Thank you. Before I answer, Madhu, we get on the notes on the chat here. We get thank you, and it was a fantastic meeting. I'm very happy to hear that. That's the intent of it, to connect people with true research and science about planetary defense. The next Planetary Defense Conference is going to be held in Montreal in May of 2027.
Oh, look at that. How do you get to pick these beautiful places, or does IAA do that?
Yeah, of course, yeah. Montreal was kind of a good natural candidate.
Excellent.
And we actually also know where the 2029 conference is going to be.
These people are very interested in how.
And where will that be?
It's going to be in the city of Nice in France.
Oh, beautiful.
Everybody is going to come out and
Okay.
look at the pockets.
Okay. I think we'll get Catherine involved in that one, right?
Okay, yeah, we need some help for that. Yeah. All right, lovely to see you. Rest of the weekend for everyone else that's still online, and everything is going to be available on the AIAA website very soon. And see you next time.
Let's keep the world safe, Nahum.
Let's keep the world safe. Right. Bye, everyone.
Bye-bye.
Bye-bye.
Bye.